Right, hello everyone. We'll get started. Welcome to the Climate Variability and Change Working Group session. Thank you all for coming. I don't know if we can get the slides up for this one. So I'll give a quick 10-minute update. We've kind of split our updates up into two. So we're going to have 10 minutes now where we'll just talk about simulations that are done or are ongoing. So there's no kind of chance to change those. And then after the first coffee, so this is on behalf of my fellow co-chairs, Aishu Hu and Sarah Larson, who are both here, liaisons, Adam Phillips and Gary Strand. So first of all, I just want to mention a couple of upcoming workshops or hackathons that I think will be of interest to this group. So there's both of these are, I think, hybrid and will be happening at the Mesa Lab. So there's the Forces MIP workshop and hackathon. This is happening in August. The purpose of this is to think about new statistical techniques to try and isolate the forced response in the observational record. And this is going to be a combination workshop and hackathon, so there's going to be lectures by the individuals that you see here, along with a hackathon time where people will be working in groups to kind of figure out these kind of techniques for isolating the forced response. And then we're also going to have this US CLIVAR workshop in March of next year. This is still at the very early stages of planning, but it will be held from the 13th to the 15th of March, and there'll be a flyer and a website coming soon. So the purpose of this workshop is to talk about kind of confronting our climate model trends with observations, given that we can really now start to see the climate change signal emerging in various features, and we can be comparing our models with the real world at this point. So some new simulations available. This is maybe old news by now, but this is the first summer meeting since this data set has been available. So we have the single forcing large ensemble now. So this complements the CSM2 large ensemble, and it gives you the opportunity to kind of divide up the overall signal in the CSM2 large ensemble into the contributions from individual forcing. So we have 4 primary ensembles where individual forcings are evolving in time and others are held fixed. So we've got an anthropogenic aerosol ensemble, a greenhouse gas ensemble, a biomass burning ensemble, and then an everything else ensemble, which contains all the other forcings that are not in the first 3 experiments. So you can look at additivity here. And in the process of doing this, we realized some differences from CSM1, and so we ran another ensemble where we looked at the aerosol forcing, but in a different way. So we did everything but the aerosol forcing, which was the way we ran the single forcing experiments for CSM1. So the description paper for this is accepted in Journal of Climate now, and it should appear on that website any day now. Another ongoing project is this regionally refined North Atlantic AMIP simulation. So this is going to run from 1958 to present day. And we're going down to regional refinement of 1/8 degree in the North Atlantic. So this is, I think, kind of an unprecedented length of simulation for this kind of resolution. And we're running with prescribed sea surface temperatures from the IHESP 1/10 degree forced ocean sea ice simulation. So that gives us kind of realistic variability, but we also can have fine scale features there that you get in this 1/10 degree data set. And so the motivation here is really to look at ocean atmosphere coupling and North Atlantic jet stream variability in this very high resolution to see, do things change when you go to this resolution. The simulation's underway. We've had some setbacks, but it's actually been running since last summer, and we're at 1991. So I'm hoping that, before Cheyenne dies fully, we'll get this simulation completed. Another new data set, which is almost available, is a medium ensemble with the SSP 585 scenario. So the CSM2 large ensemble was run with SSP 370. The working group had already run SSP 245 ensemble, and now we're complementing that with an SSP 585 ensemble. These simulations are almost finished, and you can expect them to appear very soon. So this can allow you to explore forcing uncertainties here. And then another set of simulations that are ongoing are using this 83 level model. So as you may have heard, CAM7 is going to have a higher vertical resolution. Here you're seeing the grid spacing as a function of height, and in the black here is the old CAM grid, and in the red is the new CAM grid minus enhanced resolution in the boundary layer. So CAM7 will have enhanced resolution in the boundary layer, but when you change that, you have to change your tuning and aspects of the physics. And so what this working group is doing here is only changing the resolution in the free troposphere and the stratosphere and the height, which allows us to really look at the impact of just that change alone. We don't have to change any other aspects of the tuning to look at how climate variability changes when we resolve the stratosphere better. And in particular, a key feature that is being aimed for here is the QBO. So this grid gives us a QBO, whereas the current CAM doesn't have that. So we're running a suite of simulations. These are well underway at this point. We've got a pre-industrial control, coupled historical simulations that go out to the end of the century using the SSP 370 forcing, some AMIP simulations, and then there are also some nudge QBO simulations being performed for the QBOI project. So the description paper of this is in prep, and we hope to make these data sets available as soon as we have that together. Another project that's ongoing, led by community members, Flavio Lehner and others at Cornell, is this CAM6 Limtoga project. So here they're using alternative histories of sea surface temperatures based on what could have been if we'd had a different realization of internal variability. So they've used a linear inverse model to come up with alternate natural variabilities over the past. For example, members that give you a cooling in the eastern tropical Pacific versus a warming versus what actually happened, just to explore what could we have experienced in things like North American hydroclimate if the variability had been different. So yeah, then this is the final thing, which is being led by Sarah, that I'll hand it over to her to describe.
Yeah, and so this project isn't being run through the working group allocation, but it is made possible through a grant through NSF and a large allocation through a CESM award. And so in this project, we were really interested in getting a better sense of how changes in the wind-driven ocean circulation impact climate and climate change. And so we've sort of done this by fixing the wind stress on the ocean and CESM2 to the 6-hourly climatological values, and that lets us sort of answer these science questions. So we've completed pre-industrial control runs that are available on Earth System Grid, and I know several of you have already started looking at those. We've completed the historical runs, and we've had some sort of outside collaborations from Yu Chao, who's here, and Sheneng Hu, looking at the Arctic and the tropical Pacific. So there's a lot of irons in the fire, but we don't have enough people power to fully analyze all these runs, so we're making sure that everyone knows they're available. So please check with me after the session if you want to know where the paths are. And our future simulations are also complete. End of the slides. Oh, yep, that is. So for our presentations in the session, so each of you, if you're presenting, we give you 10-minute slots and requested 7-minute talks. So at 7 minutes, Isla's gonna put up this 1-minute slide, so you know that you really need to start wrapping up. And if you're doing this presentation in person, we have this sort of wand here, and there's just a very clear arrow to advance. And if you want to point to your slides, you point it at this screen, not this screen. So we'll be starting with, let's see, Julie Karen. Oh, Caron, thank you.
Everyone. Is anyone else freezing like I am? It's cold. Okay, so my talk today is really just a few quick highlights really, from a paper that we're about to submit to the Journal of Climate on the modes of variability in the E3SM and CESM large ensembles. And I just wanted to be sure and include the author list on this for everyone to see. And then, so the motivation is really just that the modes of variability play a critical role in a number of things that we care about, such as seasonal prediction and climate projections. And historically, they have been poorly simulated by a couple of climate models. So we're using recently produced large ensembles with successive versions of both E3SM and CESM to assess the simulated modes of variability. And so I just wanted to, let's see, that's my, oh yeah, there it is. So this is just a quick list, really, of the number of members and the year ranges for the large ensembles. And for this analysis, we use all of these. And we look primarily at sort of the present day period, so 1920 to 2020. But for just a really quick aside, due to some post-processing issues and things like that, E3SM1 only extends to 2014, right in this moment of the analysis I'm going to show you today. So one of the key questions that we ask in this paper are the observations a useful constraint on the simulated modes of variability? And to look at this, this figure shows the mean pattern correlations. Yeah, so it's a mean pattern correlation for each of the models in the colored bars. So I've taken the pattern correlation between each ensemble member and observations, and then the mean is plotted in the histogram bars. The whiskers or error bars show the 10th to 90th percentile range of those pattern correlations, and the red dots represent the pattern correlations between two observational estimates over a comparable time period. And then along the x-axis here are a number of modes of variability that we get by running the CVD-PLE package. So a few things to note from this are that the extratropical modes are overall well represented. They have large correlations of 0.9 or higher. The error bars are small, and they encompass the observations in many cases here on the right-hand side. For global modes, though, you can see the PDO is much better represented than the IPO. In the IPO, you can see much lower pattern correlations and much larger intrinsic noise between the ensemble members. And then looking on the left-hand side here, we have a couple different modes of variability related to ENSO. And these are the temperature composites that are not well represented by the models. They have, again, low pattern correlations and large intrinsic noise. And the Hofmahlers here actually are quite well represented. So I guess in summary, that it's important to note which ones are and which ones aren't well constrained. So then looking more closely just at the actual patterns for say the Pacific Decadal Oscillation as one example, the observations are here in the upper left. This is what the pattern looks like in the real world. And then I have the ensemble average pattern for E3SM1 and 2 and CESM1 and 2. And this is actually a measure of the ensemble deviation for the latest version of each of the models. But I'm mainly just going to talk about the pattern here to show some biases that jump out when we look at it more closely. So one thing to note is that in the E3SM, the tropical manifestation of the PDO pattern is pretty deficient. And in the North Pacific area, it's overestimated. In CESM1 actually looks pretty good. It does have some biases. This is kind of notable to me. That's not in the observations in the Western North Pacific. But by the time you get to CESM2, it's overestimated throughout most of this area. And the tropical signal for the PDO extends too far west compared to the observed. And then looking at another mode that is well constrained, but looking in more detail at its pattern are these El Nino Hofmahlers. So again, the plots are laid out the same way. The observations are in the upper left, and then we have E3SM1, 2, and CESM1 and 2. And you can see the pattern that I think a lot of us are pretty familiar with. The warm anomaly growth from springtime into the peak by winter and then dissipating, and often El Niños are followed by a La Niña in the subsequent year, but not always, so we see a weak La Niña signal in the observations. And some things that jump out as far as the model's representation of this in the ensemble mean is that it's strongly overestimated warm anomalies. It looks too biennial in the transition to the subsequent year, and it extends too far west compared to observations again. And there also seems to be sort of a sloping to this anomaly pattern that implies a westward propagation that's not in the observations. And let's see. So that's it. I'm at my conclusions. I think I made it in the appropriate amount of time. So in quick summary, as far as which modes are well represented versus not, the ENSO temperature composites and the IPO are not. They have too much intrinsic noise between the members. But the extratropical modes are well represented, and as are the PDO and the ENSO Hofmallers. However, when we do look closer at the spatial patterns, we see a number of model biases, which I've listed here. So that's it. Thank you. You know, I don't. It does have the most members of any of them, which could be part of it. But yeah, you can definitely see, even in the modes that are not as well represented, that there's like this climbing, right, improvement and CESM is doing the best of those modes too. I don't know, maybe another co-author like John has a good idea or something, but. I don't know. Okay. Maybe the microphone's not on over there, you think? Or?
It is on.
Right. Is that, we good? Okay.
Our next 3 presentations are online. We're hoping by putting them all together, we reduce technical issues. So we'll see if that is the case. Do we have Shinlin? Okay.
Yeah, I'm here. So can I share my screen now?
Yes, we can hear you as well. Okay, everything looks good in here.
Okay. Thank you. Okay, so yeah, good morning, everyone. So today I will focus on the Northeast Pacific Ocean and to explore the role of the Pacific decadal oscillation in regulating the variability of marine heat waves in recent decades. And this research is working with my advisor, and also we have 3. We also collaborate with 3 great scientists come from the NOAA and also the UTAS. And first, let's talk about some basic background. So the definition of the marine heat wave is a discrete prolonged period of the anomalously warm water event is occurring at a specific location. Based on the definition, so a marine heat wave it can detect as an event in which the daily SST is higher than the local threshold for the at least 5 days and no less than 3 days interval. Usually, people will use its duration, intensity, and the near average frequency to describe the marine heat wave duration variation. Here are 2 strong marine heat wave events happened in the Northeast Pacific last decades. The 2014 one is a famous event named Bob, and observations show that this strong event come back in this region again in the 2019. Here, I just show the monthly PDO index from the 1891 to 2022 for the average of 4 observations. We found that both of these 2 magnitude wave events, they are concentrated in the period of the positive PDO phase. And also there were no strong warm water events. It has been detected in the previous negative PDO phase period. From this, so we just speculate that the PDO has a modulating effect on the decadal variability of the marine wave in the Northeast Pacific Ocean. And this is our scientific question. Therefore, so we first performed the statistics of the marine wave events in the observations. We choose the OSST version 0.1 daily output. We choose, and also we choose 2 time periods of the PDO positive phase and 1 negative PDO time period. In this figure, so each row represents a different marine wave characteristics. From the top to the bottom is showing the marine wave duration, frequency, and also intensity. From left to the right is the negative PDO, positive PDO, and the difference between the positive and negative one. So this result shows that compared to the long lifetime, this result shows that so the long lifetime and high frequency and strong intensity heat wave events is tended to occur in the Northeast Pacific coast area during the period of the positive PDO. And the changes of these metrics at the different phases, so it can, to some extent, it can reflect the influence of the PDO on marine waves, but there still have some other factors here. This is because there is an anthropogenic global warming effect in the continuously observations, and the extent of this warming effect is different in the different period. Therefore, so we choose the large ensemble simulations of the climate models to eliminate the background anthropogenic global warming, and we want to isolate the PDO effect. We choose 5 climate models with a daily SST output, and as shown in the panel A here, we calculate the PDO index for each simulations. The black thick line here shows the average of all members, and we can find that so this black curve is fluctuates very little, is close to 0. So it can indicating that the average value of the large ensemble, so it can offset the positive and the negative PDO, and therefore it can represent the background warming. From this, so we choose 20 each of these large ensemble simulations with a positive and negative PDO during the 2013 to 2022. And we plan to explore the role of PDO in this by comparing these 2 groups. Here is the model result. So from this is the difference between the positive PDO and the negative PDO groups. So from the difference, we can find that marine wave it will live longer and occur more frequently along the Northeast Pacific coast in the positive PDO groups. And these results are consistent with those we just demonstrated by the observations. And in most of the Northeast Pacific coast, the marine wave was enhanced during the positive period. Since the moderating effect is most evident in the coastal region, so next we will perform the probability density function analysis of the sea surface temperature in this region. And here is the result. So we just focus, we just calculate the PDF in this black box. And the blue line means the negative PDO, the red line is a positive PDO, and the gray curve is the ensemble mean. So because there is no preferred PDO phase in the large ensemble, so the gray curve can represent the neutral phase. And the black line here represents the marine wave at the 19th percentile of the neutral position of the gray line. So the results show that relative to the neutral position, so the negative PDO, it will shift the SST mean state negatively, and the positive PDO, the red curve, so it will shift the SST positively. And comparing the PDF curve with this with this black line here, so we find that the positive PDO, it can significantly increase the likelihood of the marine wave in the Northeast Pacific region. And then, so we want to investigate the physical mechanism behind this. We calculate the difference of the SST trend. the result shows a pattern this is similar to the positive PDO spatial pattern. There is a warming trend anomaly mainly concentrated in the coastal area, and it can spread to the Central Pacific at a lower latitude. And we also calculated the difference in the surface wind stress here. The results show that anomalously southeasterly winds, they are prevalent along the coastal area. And then based on the difference of the surface wind stress, so we calculated the variation of the Ackermann pumping as shown in the figure C here. So the blue part indicates the downward Ackermann pumping. And we can see that the positive PDO, so it can produce anomalously downward Ackermann pumping along the Northeast Pacific coast, which will suppress the coastal upwelling. And it can also reduce the upwelling of the lower cold water, enhancing the rise of the SST. And on the other hand, so we look at the variation of the surface heat flux here. The results indicate that so during the positive PDO, more heat in the atmosphere is absorbed at the ocean surface along the Northeast Pacific coast, and which has a positive effect on the increase of the sea surface temperatures. So here is a short conclusion. So we found that so the positive PDO, it can have a positively effect on the heat wave in this coastal region. And also we do the quantified analysis for the PDO effect on that and got this result. And thanks for your attention today. And I will be glad to answer any questions.
All right, we have time for 1 or 2 questions. One, and let's as a test.
Hi, thanks for that presentation. Is it fair then to say that the blob and blob 2.0 is sort of an extreme version of the PDO, or is that not the right?
I'm sorry, so I can't listen the question clear.
Okay, yeah, try the other mic, and we'll have the other one ready next time. She's
Hi,
gonna try
can
again.
you hear me now?
Oh, yeah.
Okay, perfect. Thank you so much. Thanks for that presentation. I was wondering if it's fair to make the argument or to draw the conclusion that the blob and the blob 2.0 are basically 2 very extreme forms of the PDO.
So actually, so the marine heat wave event it can happen in every ocean of the world, and this too is for it happened in the Northeast Pacific Ocean. So it's not only so the marine heat wave event is not only driven by the single driving mechanism here. So this event are related with the PDO, but it's not the PDO is not the only driver mechanism for these events. Yeah, so this one maybe have also can influenced by like the ENSO or like the NPG also in this region. So they also have the influence on this event. But in our research, so the PDO it has the positive effects for the marine heat wave in this region. Yeah, but it's not the only mechanism here.
She says thank you.
Okay, I'm sorry.
Great. So we'll move on to our next presentation, which is also online by Shangfei He. Shangfei, can you say hi and we can make sure the sound works?
Hi, could you hear me?
Yes, we can hear you.
All right, so could you see my slide?
Yes, we can see the slides.
Okay, so hi everyone. So today I'm going to present a recent study on AMV. So this study is a collaboration with my postdoc advisor, Amy, Mark, and other group members in the University of Miami. So my conclusion is basically the title, the recent tropical Atlantic multicadal climate variability is mostly driven by external forces. Right now, our study is still under revision, and I will be sharing some juicy details with you shortly. But if you are looking for more details, there is a preprint online, so you can check it out there. So some background. So basically, this is AMV. Spatially, it shows a hot stress pattern in the North Atlantic and cooling in the South Atlantic. And temporarily, the AMV index goes ups and downs, and with a cycle of several decades. Actually, the AMV is not just in SST, but also in other climate variables, like the local floral rainfall. We see it is well correlates with this ST change in the North Atlantic. And also in the North Atlantic hurricane, so it shows high and low area, and it well correlates the acid change as well. And even remotely in the North Africa, the rainfall in the Sahel region is well correlated with the SST in the Atlantic. So we actually call this a coupled tropical Atlantic multicadal climate variability instead of the AMV. And even though the AMCV has important impacts, but the cause of the AMCV is controversial. Usually the cause falls into two categories. One argues that it is driven by internal dynamics like the AMOC and the NAO. The other one argues it is driven by external forcings like the anthropogenic aerosols and volcanic eruptions. So this comes to our motivation. What is the cause of the recent AMCV? So to understand the cause, so we use the Sim6 simulations from 46 models. In total, we have 400 ensemble members. And we will also use PI control runs from 31 models to quantify the internal variability. And we also use the single forcing runs from the GAMIP. Each single forcing run has 70 to 100 members. We use them to quantify the role of external forcings. And for observation, we use multiple data set, but the statistics in these data set are very close. The study period for our study is from 1950 to 2014, and all our data are just from June to October because we mostly focus on the summer impacts. So here is the result. We first detrained the low-pass filter and normalized the time series of the AMV, Sahel rainfall, and vertical wind shear. So the vertical wind shear is a proxy for the North Atlantic hurricane activities. The red curve here is from observation, and the blue curve here is the model simulation. Now we see the blue and the red curves fit close. The model, the AMV, Sahel rainfall, and vertical wind shear are highly correlated with observation, with their correlation above 0.9. So this suggests that more than 80% of the variance in the real-world AMCV is forced. Though these time series suggest that the real-world AMCV is false, but it doesn't rule out the possibility that the internal variability could also play an important role at the same time. So next step, we further tested the hypothesis that the internal variability could result in the real-world AMCV. But if the observed tropical AMCV could arise due to internal variability alone, then the statistics in the AMCV system must be similar in both model and observations. One statistics here is the covariability in this system. Basically, it is a correlation between the AMV and the Sahel rainfall, the correlation between AMV and vertical wind shear. We calculate these correlations for the observation. This is the red star here, and it is about 0.8. This is consistent with previous studies. And we also calculate the correlation for each model realization. But before the calculation, we remove the force response in these realizations. So what left is just internal variability. We denote this correlation without forcing. So the shading here is a 2D distribution. The color of each pixel is the number of realizations having this correlation value. The result here is strikingly clear. The observation is at the tail of this distribution. None of the realizations in the historical run with force response removed could produce a correlation value higher than the observation. So this suggests that the internal variability alone cannot produce this real-world AMCV. And we also observed that this distribution due to the internal variability has a large spread. Actually, it is expected because when there is no forcing, the correlation between the AMV and its tropical impacts could be easily interrupted or intensified by other processes like the ENSO, like the PDO. So sometimes it shows a higher correlation, but sometimes it shows a low correlation. Overall, it shows some correlations here as indicated by this green star here. This is the mean of this cluster. So, but it is not as high as in the observation. So to summarize here, we see that this internal variability alone cannot produce this real-world AMCV. Well, we also calculate the correlation between the AMV and its impacts with force response in historical runs. Again, we see that the observation is at the tail of this distribution. So this means that the single model realization is very unlikely to produce the high covariability as well. And even it has force response inside. This further implies that the single model realization is dominated by internal variability. But the correlation associated with the force response, basically this blue star here, we see it is close to the observation. So overall, they suggest this high covariability in the real world AMCV only emerges in the force response. Now I'm going to show you the mechanism of the Sahel rainfall and North Atlantic hurricanes. We argue they are driven by a gill type response. So in a gill model, when we have a asymmetric heating across the equator, like this figure shows, when we have heating in the northern hemisphere tropics, so it will induce a barocclitic mode in the tropics. So in the low level, there is a cyclonic response, and in the high level of the hemisphere, it is an anticyclonic response. And this barocclitic mode is well observed in the observation and the model simulation as well. So we see here at the low level of the hemisphere, there is a cyclonic response, and the westerly transports water vapor to the North African regions, therefore leads to rainfall here. And at the high level of the atmosphere, we see the easterly anomaly perturbs the vertical wind shear, therefore affects the North Atlantic hurricanes. So based on the mechanism here, we argue that the tropical Atlantic SST contrast could be a better index of the AMV for these tropical impacts. And we then quantify the role of different forcings in the AMCV. What I find here is that for AMV, the greenhouse gas, anthropogenic aerosols, and natural forcings, they contribute closely. But for Sahel rainfall, vertical wind shear, and this DSST, they are mostly driven by the anthropogenic aerosols and natural forcings. Greenhouse gas plays a minimal role. So they suggest that this tropical AMCV is mostly driven by the anthropogenic aerosols and natural forcings. And this DSST, again, is more consistent with these tropical impacts than the AMV. So finally, I'm going to show you a big issue in the model. This is a signal-to-noise paradox. Like I said before, I normalize the time series of the AMV, Sahel rainfall, vertical wind shear. Now I calculate their variance in the model and observation before the normalization. In the model, the MOE is the mean of the ensemble. This is the average of the variance across ensemble members. And the EM is the ensemble mean. This is the variance of the force response. Basically, we average ensemble force, then we calculate the variance. So the difference between EM and MOE is the variance due to the internal variability. So we see that in the model, the EM and IV, they are about the same. So this suggests that the signal-to-noise ratio is about 1 in the model. But as I showed you before, in observation, it is mostly false because the EM and observation are highly correlated. So this implies the signal-to-noise ratio in the model is much larger than 1. Then we see the signal-to-noise paradox. And this signal-to-noise paradox is even more extreme in other variables, like in the vertical wind shear, Sahel rainfall, and this DSST. They are much smaller than 1, but in the observation, again, they are much higher than 1. So the real world, the signal-to-noise ratio is high, but in the model, it is very low. And we need a large ensemble to recover the force response. And the cause of this signal-to-noise ratio in the model is not obvious. So this is my take-home message. We found that this tropical AMCV is mostly driven by the natural forcing and anthropogenic aerosols. And this DSST could be a better metric to expand the tropical impacts through the gill type response. The implication is that the hurricanes, Sahel rainfall are more predictable than previously thought. We are able to use the large ensemble to do a near future prediction. But one open question is why the signal-to-noise ratio is so low in the model. So I'll stop here. Thanks for your time, and I'd be happy to take any questions.
We can take one quick question. We have one online. We're trying a new mic. I'm feeling really good about it.
Oh, okay. So the online question is, how did you quantify the EM in observation? This is a good question. We quantify the EM based on the correlation between the modeled EM and observation. So basically, this is R squared.
I had a related question, is there any sensitivity to how you detrend?
Oh, yes. Actually, I didn't show it here. So if we compare the total rainfall and vertical wind shear, the Simple 6 model has a spurious trend. So this spurious trend is related to the SSD BIOS in the model. So we do detrend it because we just want to remove this spurious trend rather than we want to do any like extract the multi-decadal variability here. Because we can do it for like pre-1950, we don't need to detrend it because the model and the data really don't have any trend there.
Great, thanks. We're going to move on to our next presentation. It's our last one online in this session. So we have Wei Lu. Let's see. Do you mind saying hi so we can make sure the sound works?
Hi, can you hear me?
Yes, we can hear you.
Thank you very much. Let me share my screen. Okay, can you see my screen?
Yeah, it's not in presenter mode.
Oh, okay. Let me see how I can make it works.
Yes, looks
Better?
good.
Great, thank you very much. Hello, so I'm Wei Liu from UC Riverside. Today I'm going to talk about EMOC impacts on ENSO in a warming climate. So this work, I collaborate with my students, David at UCR, Alexi from Yale, and Jiang from NCA. So this work is supported by NSF. So first, some background, and we know the EMOC is projected to slow down in the 21st century, and this slowdown of EMOC can impact the Earth's climate, potentially impact the ENSO variability. So there has been previous study showing that in the freshwater hosting experiment, when we see a weakened or collapsed EMOC, and we can see the ENSO variability will increase. So this is the study by here, the two, and also the weakened or collapsed EMOC can cause eastward shift of ENSO SAT anomalies. Recently, there's another study showing that instead of increased ENSO variability, the weakened EMOC or collapsed EMOC can actually reduce the ENSO variability. So we can see some inconsistency here. So now the scientific question is that the above EMOC impacts on ENSO, however, are obtained from the freshwater hosting experiment. So we know there's no anthropogenic warming in the hosting experiment. So in that case, and how can we learn how will the EMOC impacts the ENSO in a warming climate? And also it's not clear how and to what extent the EMOC slowdown will affect future ENSO variability. So to tackle this scientific question, and we use CESM4, 1 degree CESM4, and we use historical and RCP 8.5 simulations by ensemble members. So based on these simulations, and we conducted fixed EMOC experiments. Basically, we started from 1980, and we extract fresh water from the subpolar North Atlantic, showing on the here, red top. So we remove fresh water and then redistribute it evenly to the rest of global ocean. And therefore, by doing that, we can fix EMOC even with RCP 8.5 global warming. So on the right, I'm plotting the EMOC strength, and the black shows the historical, and the red shows the fixed EMOC from 1980 to the end of current century, while the blue one shows the original RCP 8.5 scenario. So we can see a weakened EMOC under the original simulation, but fixed EMOC in the fixed EMOC simulations. Okay, so then we look at ENSO variability, and here I'm looking at the NINO 3.4 sea surface temperature spectrum. So the black curve shows the historical, and the blue curve shows the RCP 8.5, while the red curve shows the RCP 8.5, but with a fixed EMOC. So we can see the projected anthropogenic warming can shorten the ENSO period, and however, if the EMOC slow down, and it can make the ENSO period even shorter if we compare the blue and the red curves. On the other hand, we look at the magnitude, and we can see the magnitude will reduce with global warming. However, if the AMOC is fixed, and we can see the magnitude will further reduce. So that means a weakened AMOC actually can enhance ENSO variability. So what will be the mechanism? First, we look at the sea surface temperature annual cycle. Here, I'm showing the tropical Pacific annual cycle, SST annual cycle, and we can see the difference between the RCP 8.5 and the fixed AMOC case. So we can see a weakened AMOC can further reduce the SST annual cycle in the Eastern Equatorial Pacific, and this reduced annual cycle actually can lead to intensification of ENSO based on the frequency entrainment mechanism, which has been well studied before. Okay, so further we look at the Bianchi stability index, and here is the index, and is equal to the sum of 5 terms: the thermodynamic term, mean advection feedback, zonal advection feedback, Ekman upwelling feedback, and thermal feedback. So on the right, I calculate the difference between different simulations, and basically I want to draw your attention to the gray curve, so the gray bar, which is the difference between the RCP N5 and the fixed AMOC case, which indicates AMOC impacts. So we can see with a weakened AMOC, we can see a positive value for this total BG index, which is consistent with intensification of ENSO variability. And then we look at different terms, and we can see the large contribution from this Ekman pumping term. And we also further look at the different coefficients, the changes. So to summarize, and we can see the increase of Bianchi's index mainly caused by the strong positive Ekman upwelling feedback. It results from the enhanced atmospheric wind stress response to SST anomaly, and also enhanced oceanic upwelling response to equatorial wind stress anomaly. So here is our conclusion. And basically, we find the slowdown of AMOC can enhance ENSO variability. And we also quantify the number is about 11%. So we also look at mechanism, we look at the SST annual cycle, and also we conducted Bianchi stability analysis. We find that Ekman upwelling feedback is very important. Due to the time, I did not include other results, but I include here, and we also look at the ENSO complexity. We find that AMOC can also impact the Central Pacific and Eastern Pacific patterns for the ENSO. So thank you very much. And here is the paper. And if you want to learn more information, please go to our papers published this year. Thank you.
We have time for a question. Yeah.
Hey, great talk. So my question is, how do you determine how much negative freshwater forcing are you putting? And is that determined through trial and error to maintain the AMOC?
Thank you very much. Very good question. Yes, so this experiment was done, and also the some details were published in 2020 paper. So basically, we first conducted freshwater hosting experiments to slowly, gradually input fresh water, see how the AMOC will slow down. By doing that, and we can get a relationship between the AMOC strength and the fresh water we input. Then we look at RCP 8.5 scenario, how much slow down due to this global warming, and then using the previous linear relation we get, and then we can tune the model to fix AMOC strength under the RCP 8.5 scenario.
We will move on to our next talk. So we'll be back in the room now. So Jacob, over here. Let's make sure. So next up, we have Jacob Swinvolt Allen. You can correct me now. but this isn't your presentation. Correct.
Sweet, thank you. All right, hello everyone. My name is Jacob Stuyvenvold Allen. It is terribly impossible to pronounce, so I do not blame you at all. Yeah, I'm working with Alexei Fedorov and Minmin Fu at Yale, where I am currently a postdoc. And today I'm going to talk about some changes in ENSO statistics we see in climate change, in enhanced global warming experiments, and the role of wind stress in contributing to these changes. So there's been kind of an emerging consensus on ENSO variability in CMIP6 models, where they're projecting kind of an increase in ENSO, SST, and precipitation variability. This can be shown a little bit on the right plot. We're looking at some bootstrap statistics around the multi-model ensemble mean for the top panel, which is SSP 585. In the purple, you can see the SSP, and in the green, you can see the historical. For also the SSP 126, what you end up seeing is that the standard deviation of ENSO, or the Nino 3.4 index, is higher in these enhanced emission scenarios. And you can see this across not just Nino 3.4, but also looking at the EP and CP index. So it's well represented in ENSO diversity as well. The thing I want to point out is that the change is still markedly different across models, and some are even projecting a weakening of ENSO by varying metrics. So there's a big impetus to understand why these models are differing on their projections of simple ENSO statistics. And this is really easy for me to try and to answer the question, where do models diverge and why? It's quite easy to get lost in the sauce of the known model biases and uncertainties. And these all kind of boil down to a delicate balance between positive and negative feedbacks related to ENSO. And we're not going to talk too much about those, but I think the point is that my goal here is to try and find some unifying features across models that help explain the spread in projected ENSO statistics. Just to cut right to the chase, we think that the westerly wind forcing is really quite important for this, and specifically the distribution of wind stress about the equator. This is supported by some other research, and I'll talk a little bit about what I mean by the distribution of wind stress. So if we think about westerly wind forcing for ENSO, it often comes in kind of high-frequency westerly wind bursts, but integrated over a month or a season, we might get more Gaussian shape of westerly wind anomalies about the equator. And what people have shown is that the shape and structure of this wind stress anomaly can be pretty important for ENSO statistics. Namely, something like a longer wind stress anomaly can correspond to a weaker and higher frequency ENSO, where something like a wider anomaly about the equator can correspond to a stronger and lower frequency ENSO. Important note here, right, chicken or the egg, this is a coupled process, so I'm definitely, with the way I talk about this, might not acknowledge that, but I recognize that this is a coupled process and the winds also respond to SST forcing. So again, can the shape and characteristics of wind stress explain the projected changes in ENSO? First, we'll look at some CMIP6 results. And predominantly, we'll talk about just increased SST variability, but we think there's also implications for frequency and skewness, so check back in on those later. The first plot is looking at a multi-model ensemble mean of the Nino 3.4 monthly regression onto zonal wind stress anomalies. In the top panel here, I've got the historical simulation of CMIP6, again, the multi-model ensemble mean from 1900 to 1999. And we see that nice red blob about the equator, which is that wind stress anomaly associated with the Nino 3.4 index. One panel down is the SSP 585 multi-model ensemble mean, and by eye, it's really hard to see a difference. But if we look at the third panel, there's quite a difference in the wind stress anomalies that occur just on the equator and just north of the equator in the western and central tropical Pacific. And we think these are quite important. So it's a little bit of an asymmetric change. We don't see this to the south, and I want to make sure that that is clear. How do we quantify this change in wind stress structure? To figure out how important it is, we need to kind of quantify that shift in the wind stress anomalies. And so I'm going to reduce a dimension of that data to get a better look at kind of how this wind stress anomaly is shifting. This is a 5 degrees south to 5 degrees north average across the Pacific basin of that wind stress anomaly. The red line here is SSP 585, and the blue line is your historical. The bottom panel is showing us the difference. So we can characterize this as primarily a westward shift of the westerly wind stress anomaly associated with Nino 3.4, but also a magnitude increase. We see that the SSP scenario has stronger wind stress values in the Western Pacific. When we look in latitude, so we're averaging over longitude in the Nino 4 region, what we can generally see is that there's an increased width across the equator. That might be one way that we can describe this. So I'm not showing the exact way that I calculate those three changes or those three metrics of the wind stress shape, but I want to just highlight that if these seem to be really important for predicted changes in ENSO SST variability. So if you use those metrics, the westward shift, the magnitude increase, and the increased width of that wind stress anomaly about the equator as predictors in a multiple linear regression model, you can do a really good job of predicting the projected change in ENSO standard deviation. So each color here, each little circle is a different model. The x-axis is showing us the predicted values from this multiple linear regression model, and the y-axis is the observed. So if the multiple linear regression model was perfect, all of these dots would fall right on the line. But what this is showing us is that generally we get a pretty good fit with an R value of about 0.7 by using these metrics of wind stress as predictors of the model's change in ENSO standard deviation. Now, this is purely statistical so far, so we do have some dynamical hypotheses, but to kind of just wrap this up, and the reason I'm here at a CSM workshop is that we're interested in trying to simulate this. And our simple question here is, well, if we add this change in the structure of wind stress to CESM, can we see an observed increase in Nino 3.4 standard deviation like we're seeing at least in the CMIP6 multi-model ensemble mean? So that's what we're going to do. What that looks like is the first step in this is a branch run using a B case from the pi control. And this is giving us these daily wind stress values. It's quite difficult to see, I'm sorry. But the point is that from a 100-year branch of the pi control, we can mask out the tropical Pacific values and replace those with El Nino anomalies that are scaled by the value of the daily Nino 3.4 index. And that might be a little bit, I may not have explained that super well, but I will show a result that kind of highlights what this is doing. The whole point is that we want to remove internal variability between a couple of simulations, remove that complicating factor of internal variability. So we're kind of replacing the El Nino of one simulation with the El Nino of the same simulation. I'll show that in a second. Another thing we're adding into the tropical Pacific is the climatology. And then we can do this for the historical and the SSP scenarios with the altered wind stress shape and see the response to ENSO. So I'll just get right to showing kind of what this might look like. The result is that in our first override simulation, we have effectively replicated the ENSO of the first control simulation. Our internal variability is quite the same. You can see the R value is about 0.83. The orange line here is the override scenario. And while we are reducing things like ENSO magnitude, because this is a linear framework, we're using linear regression to impose ENSO into the override scenario. What we're doing is removing the confounding internal variability between these simulations and giving us a better apples-to-apples comparison. The next step, and I'm really sorry, this is not a result. I have the files ready, and I'm about to start the simulation for the final bit of this piece. But what we're expecting is that when we add that off-equatorial wind stress anomaly into the model and then do this simulation again, we will see probably, hopefully, an increase in ENSO standard deviation, and that will help us to diagnose some of the dynamics at play here in terms of this westerly wind stress anomaly. So I'll leave my conclusions up. I think I'm out of time, but again, if there's anything that you take away from today, I hope it's that the structure and shape of wind stress about the equator is really important and can explain some of the intermodal differences in ENSO projections of El Nino standard deviation. And CSM2 experiments used this way will allow us to analyze this hypothesis without the internal and model variability that we're seeing in the CMIP6 suite. So yeah, this is working next step, and I'll take any questions. Thank you very much for having me.
But the broadening in the wind pattern is a consequence of the changing the strength of ENSO anomaly.
Right, chicken or the egg,
So
right?
this is called chicken egg.
Yeah,
right?
so that's kind of the idea, because in these simulations, what we'll be allowed to do is alter the wind without having the ocean responding to the radiative forcing like it is in the CMIP6 suite. So we'll get a better idea of, is the atmosphere responsible for these changes aside from the radiative forcings that we see in CMIP6?
Oh, yeah, yeah. Some experiment like that will help to,
Correct.
to sort out what's cause, what's the effect.
Thank you.
Thank you.
It's really interesting. I was just curious, as we all know, the incident amplitude in CSM2 is really huge. It's about twice the observed. By using your diagnostics, can it be traced back to the width of the wind stress forcing, just this kind of systematic error in the CSM2?
I'll have to check. I don't know off the top of my head. Yeah, I'd be curious if potentially it is a much wider distribution compared to observations. Yeah, I'll check that. Thank you. Great point.
All right, our next presentation is from Honghai Zhang.
Good morning, everyone. Today I'm going to talk about the work that I collaborated with Richard Seeger from Columbia and Shangping Xie from Scripps. The work is about IDCZ in the Indian Ocean. So the IDCZ is the tropical rain band, right? This figure shows the observed annual mean precipitation, and as you can see, most IDCZs are mostly in the northern hemisphere, including the Pacific and Atlantic Ocean. But in the Indian Ocean, we actually have IDCZ sitting south of the equator. We have a lot of theories about the northern hemisphere IDCZs, including global energy constraint, local asymmetries in coastline geometry, or orographic forcing, but we don't have anything for southern IDCZs in general. So our goal is to explain this IDCZ. But of course, as you can see from the title, this is one step towards that goal. Here we take observed ST as given, and then we try to focus on the atmospheric dynamics. This figure here shows the annual cycle of the Indian Ocean IDCZ. It's zonally averaged across the Indian Basin. Here, the y-axis is latitude, x-axis is the annual cycle. Vectors shows the surface winds in observations. Shading shows the wind divergence, and green contours are observed precipitation. So as you can see, IDCZ in the Southern Indian Ocean exists year-round, right? It peaks in, It peaks in DGF here, and decays rapidly in spring, and then grows slowly throughout the summer until its peak again in winter. Notable, having trouble with this flicker. But one feature I want to point out here is in summer, you already see the IDCZ is actually secondary to the South Asian summer monsoon in terms of the amplitude of precipitation and surface divergence. So a closer look at the Indian Ocean IDCZ. Here's the peak phase during DGF. The IDCZ is the traditional IDCZ where it's a convergence of the trade winds from both hemispheres, and it stretches across the entire Indian Ocean from the maritime continents to Madagascar. But in summer, due to the South Asian summer monsoon, northeast trade winds reverse direction. Now the IDCZ is a result of the slowdown of the southeast trade winds. And the orientation is also different from southwest to northeast. So all of this makes this IDCZ in the Indian Ocean quite unique, and we want to understand what causes it. The first thing we did is to turn to observations and try to examine observed theory. Here we specifically look at convective quasi-equilibrium theory. So this theory states that IDCZ should generally occur over regions of maximum surface MSE. So here's the case for the winter peak season. Green contours shows the IDCZ precipitation. The black contours show surface MSE, where the maximum values are highlighted in magenta contours. And clearly, the winter peak phase is consistent with our theory. But in summer, the maximum surface MSE shifts to the northern hemisphere, the South Asian summer monsoon region. MSE decreases monotonically southward across the Indian Ocean. So this summer case is not consistent with our theory. But even in the winter case, right, the theory tells us where we expect the IDCZ. It doesn't tell us much about the atmospheric processes that are responsible for the IDCZ. So next, we turn to models. Here, we try to quantify the contribution from two specific groups of atmospheric processes given observed ST. The first one is the planetary boundary layer dynamics. This is the classic lens enigma argument, right? ST gradient drives surface wind, sea level pressure gradient, which drives surface wind, and IDCZ. The second one is the classic theotype argument. Free atmospheric diabatic heating, especially latent heating, drives large-scale circulation, including surface winds and IDCZ. We used two models. The first one is a linear dynamic model, which I'm not going to talk about today. It's in the paper. But I want to focus on the second one, where we use the latest CAM version, CAM 6.3. And this is a 1 degree resolution. Again, it's driven by observed ST. So starting with the control run, sort of also a check of the model performance. On the left, that's the model simulation, comparing with the observations on the right, which I showed earlier. As you can see, the model overall does a really good job capturing the seasonal cycle of the Indian Ocean IDCZ. But of course, there are biases, and this is well known for this EMIP type simulation. But overall, I think the model is good enough for us to move forward. So the next experiment we did is to try to separate the contributions from PBL versus free atmospheric contributions. The idea is from this figure, which shows the model vertically integrated diabatic heating. As you can see, it has a horizontal structure that's very similar to the precipitation structure that we saw in observations, right? And this horizontal structure in the free atmospheric diabatic heating has been argued to feed back to the IDCZ. So in this experiment, we try to keep the PBL dynamics the same as control run. We don't touch it, and we try to get rid of the horizontal structure in the free atmospheric diabatic heating. So what we did specifically is over the Indian Ocean, which is this black box, we, in the model thermodynamic equation, we homogenize the model calculated diabatic heating, which has this structure, but we use this uniform domain average value to override the model value in the thermodynamic equation. So this way, we effectively remove the horizontal structure of the diabatic heating. And then this experiment will allow us to quantify the contributions from the PBL dynamics, and then the difference from the control run will tell us the contribution from free atmospheric diabatic heating. So here's the result. On the left is the control run simulation that I showed earlier, comparing with the result in the sensitivity experiments. So without the contribution from free atmospheric structured diabatic heating, you can still see the model is able to simulate surface convergence and rainfall local maximum in both seasons. This suggests that the location of the IDCZ should be up to the PBL processes, of course, given observed ST distribution, right? But I'm sure you already noticed the amplitude is actually much weaker than the control run, suggesting a contribution from the free atmospheric diabatic heating. So here we quantified this contribution from the free atmospheric diabatic heating using this formula. This is the fractional contribution using precipitation. So control run minus sensitivity experiments, and then divided by the control run precipitation. That's the shading in this figure. The green contours shows you the mean precipitation in the control run as a reference. So we start from the top of the peak phase. Clearly, the free atmospheric diabatic heating still contributes or explains more than 50% of the IDCZ precipitation. And in general, you can see the stronger the mean precipitation in the control run, the larger contribution the free atmosphere contribution diabatic heating is. This is also true for the JJA Northern Hemisphere summer season, and it's true not only for the IDCZ, but also for the South Asian summer monsoon region. The stronger the mean precipitation in the control run, the larger contribution is from the free atmospheric structured diabatic heating. So these are the two main points from this work. I'm not going to read it. I just want to take this opportunity to shout out a special thanks to the Anchor CESM team, and especially these two scientists, Steve and Patrick, who I never met, but they helped set up this experiment. Thank you.
Interesting, and it's kind of one of these conundrums, this Southern Indian Ocean ITCZ, and why it's really hard to get it in coupled models. And I think it'd be really interesting as a next step, because CSM2 really struggles getting that, and your results indicate it has to do with the SSTs. So how the coupled models simulating the SSTs in the southern Indian Ocean is probably a good clue as to why that systematic error is there in the coupled models. I think that'd be a really interesting kind of thing to look at with your diagnostics.
Yeah. The next step is to use the fully coupled model. But as you mentioned, there's a strong bias in the ST. So we plan to do a flux corrected version as a start so that we will get around, we don't have to get stuck in the ST bias issue. But yeah, that's the next step, to bring in the ocean component and then try to really explain this in a fully coupled framework. Sorry.
Technical question. If you homogenize the heating entirely, right, then over that entire region, then you don't really get any heating because you have, radiative cooling and latent heating. But then if you don't have the radiative cooling, then how does the air subside back down to the surface?
Sorry, can you repeat your question? The other room is really loud here.
So when you homogenize, I'm surprised that you can homogenize the heating and still get sort of a realistic simulation, because it seems to me as though the diabatic heating is, the diabatic radiative cooling is what allows the air to subside after it's been lifted into the free atmosphere from the boundary layer. So I just wonder sort of dynamically how you think about that. Or maybe I'm just misunderstanding how you set up the experiment.
Yeah, that's exactly the point. I think the reason we were able to, the model is able to still capture the part of the IDCs is because we didn't touch anything in the boundary layer. So that's the contribution from the PBR processes. And also the ST forcing is the same. We use the observed ST distribution in this sensitivity experiments. The model is feeling the forcing from the ST and then has all the PBL dynamics that's the same as control run. So that part of the model is able to simulate. We interpret that, or we attribute that to the PBL processes plus observed ST. Yeah, I think that's the whole point. I didn't make it clear. All right, thank you.
All right, up next we have Shivri Shi. You're here right behind me.
Good morning, everyone. I'm Jerry from Hui. The title of my talk is Fingerprints of the False Responses to Anthropogenic Aerosols in the Ocean. The anthropogenic aerosols is a very important external forcing, but its effects in the ocean is relatively unknown compared to the greenhouse gas effect. So in this talk, I will first briefly talk about the sea surface temperature responses to anthropogenic aerosols, and then I will move on to talk more about the ocean heat content responses to a different kind of external forcings. So here in this slide, I'm showing the forced sea surface temperature responses, and the model we use is the CESM1 large ensemble simulations with all forcing and all but one forcing simulations to get this anthropogenic aerosol effect. And the method we use is signal-to-noise maximizing pattern analysis. So in this method, we extract a pattern that has a maximum of the ratio of the signal to noise, which is associated with the total variance from all the ensemble members. So here I'm listing the first two leading modes about the aerosol effect. The first mode is associated with the global mean effect of the aerosol, and we can find this is actually associated with the northern hemisphere distribution of aerosol forcing, which can lead to a significant cooling in the northern hemisphere. And the second mode is associated with the aerosol transition effect. We can find the transition of aerosol forcings from the west, from the Europe, North America to the East and South Asia. And next, let's go deep to look at what's going on in the ocean. So here, I will talk about ocean heat content responses. So the idea is a little bit different from the analysis in the previous slide about the sea surface temperature analysis. So we're not going to talk about how to decompose the effect about the aerosols. So here we try to put everything into this system, including the greenhouse gas and other external forcings. So now the question becomes whether we can detect the aspergillic aerosol signals within the ocean for the ocean heat content change in these all-forcing runs and also in reality. So here what I'm showing is ocean heat content trend from 11 CMIP6 models, including the all-forcing experiment and several single forcing runs. So I think you would be interested what the performance of CESM models. So I highlighted as a SIG gray curve right here. Oh, sorry. Oh, how to go back? Backward. So if we compare the top two panels, we can see they are not similar. I feel it's really hard to directly read this aerosol fingerprint from these all-forcing scenarios, all-forcing experiment. But the effect of the aerosol on the ocean heat content change is it's not small, but it seems its negative effect is overwhelmed by this greenhouse gas warming. So we need to find a way to make the aerosol signal stand out. Before moving on, there is one interesting thing I would like to talk about. There is a very striking larger negative decrease of ocean heat content in the southern hemisphere induced by the aspergillic aerosols. It seems in contrast with what I have shown earlier, that the aerosol forcing is mainly distributed in the northern hemisphere. And actually this one is associated with the anomalous northward heat transport in the ocean. And another important thing we found is this asymmetry is linked with ocean volume. So we can find that the ocean volume is much larger in the southern hemisphere than the northern hemisphere. And then we are thinking about this minus computation to extract the aerosol forced signal. And this interhemispheric asymmetry is widely used, such as the northern hemisphere minus the southern hemisphere. So here we retain one more dimension into this inputs about the latitudes. So what we do is calculate the ocean heat content for a certain northern hemisphere minus the ocean heat content in the southern hemisphere for the same latitude. So again, it is associated with the interhemispheric asymmetry, but with more spatial information included. So to the right-hand side, I'm showing the forced response about this asymmetry and the corresponding time series. So in the top panel, we can find a very clear dipole pattern right here in two different latitude bands. And the good thing is we can see these two signals with different directions are dominated by two different aspergillic forcings, one associated with the aerosol effect and the other associated with the greenhouse gas effect. And the negative result induced by the greenhouse gas effect is associated with tremendous warming in the Southern Ocean. And so we can find where to find this, the aerosol effect, which is within this 20 degree to 35 degree latitude band. And then based on previous studies, such as the Clara Desert's paper, they have mentioned that aerosol-induced response is very sensitive to the analyzed period. So we think we have to take the temporal information into consideration. So here what I'm showing is the ocean heat content trend within this latitude band where the aerosol effect is dominant. Here the y-axis is the start year for the period, and the x-axis is the length of the trend, which starts for 10 years. So we can directly see there's for the aerosol and for the historical runs, they share a similar structure. It's quite straightforward. And here I use unhatched regions to represent where we have the significant trend. So here the definition is more than 90% of the individual runs have the same sign for the trend of the multimodal mean. So as we can see, we can only find the significant trend right here. It's not working. So based on this map, we can see if we calculate the trend less than 20 years, this internal variability and also the modal uncertainties obscured the detection of significant aerosol signals. And for the greenhouse gas, the signal is gone, and all of these points are insignificant. And it's also the same for the natural external forcing effect. And so the last step, I would like to have a quick comparison between the models and observations. So we have to admit there are still some discrepancies between them, but we can find some clear similarities. The first thing is associated with the direction of these changes. They're all positive. And another thing is occurrence time. There's a very good consistency between the occurrence of this positive trend. So here are the summary. We think we have the reason to believe that aerosols do leave their fingerprints within the ocean, and it is detectable based on several temporal, the temporal and spatial information here. So I would like to stop here, and I would like to take questions. Thank you.
All right, our last presentation is from Yichun Tian.
Hi, I'm Yichun, a second-year PhD student at Duke. Today, I'd like to introduce our work on critical role of biomass burning aerosols in enhanced historical Indian Ocean warming. And I'd like to thank to my collaborators, Shineng, who is also my advisor, and Clara from NCAR. So the tropical oceans have warmed substantially in the past century. This figure shows the observed SST trend, and the black contour line represents the tropical mean SST trend. This value is also shown on the top right corner. Well, okay. We can see that relative to the tropical mean, the tropical Indian Ocean teal has experienced enhanced surface warming. And this teal warming has a lot of climate impacts, and they're listed, some of them are listed here. Now we add the CESM1 all-forcing SST trend, and compare between A and B, we can see CESM1 underestimates the observed tropical mean SST trend. However, the black contour line surrounds the teal region in both panels, so the enhanced teal warming relative to the tropical mean is a robust feature across observation and CESM1. We then want to further prove that CESM1 can capture the teal relative warming. In the plot A, the x-axis is teal SST trend and y is tropical SST trend. The colored and black scatters are observations, and gray represents CESM1. In the x direction, we can see CESM1 underestimates teal absolute warming, but it has teal enhanced warming as observations, since almost all the scatters are under the diagonal line. And in plot B, the x-axis is same as A, but y-axis becomes teal relative SST trend. The relative SST is absolute SST minus tropical mean SST. And in plot B, we can see the CESM1 has a similar range of the teal relative SST as observation in the y direction. So we conclude that CESM1 performs well in the teal relative warming. Next, we want to investigate the impacts of the single forcing agents, including the greenhouse gases, the anthropogenic aerosols, and biomass burning aerosols. The plot A shows the tropical mean temperature trend, and it's not surprising that greenhouse gases and anthropogenic aerosols are the two dominant and offsetting drivers, and the biomass burning only plays a minor role. In plot B, we calculate the tropical spatial standard deviation of temperature trend and use it as a measure of spatial variability. In this figure, we can see biomass burning contributes significantly to the spatial variability and is comparable to the greenhouse gases and anthropogenic aerosols. As far as we know, the impact of biomass burning aerosols in the spatial variability of the tropical ocean warming has been overlooked in the previous study. And we find the biomass burning is the main driver of the teal relative warming in the historical period. And I'll elaborate on this in the coming slides. So the plot A to C here shows the tropical relative SST trend, and the value on the top right corner is the teal mean relative SST trend. In plot B, we can see the biomass burning contributes significantly to the teal relative warming rather than in plot C. And we also performed forcing decomposition for teal. The y-axis on the left is absolute teal SST trend, and on the right is relative SST trend. We can see biomass burning contributes little to the absolute teal SST trend in black bar, but it acts as the most important radiative forcing for the teal relative warming in the red bar, while the greenhouse gases and anthropogenic aerosols are in opposite. So we then wonder how biomass burning changes in the historical period. Plot A here shows biomass burning induced AOD trends, and the B shows the time series of AOD variations in specific regions. In plot B, we can see there is a decrease of biomass burning induced AOD over the Indian subcontinent in the green line. And in the plot A, we can see the biomass burning emission changes which originate from land can in turn affect the surrounding tropical oceans and decrease in most of the teal region. This spatial heterogeneity can give rises to the teal relative warming. Then to uncover the mechanisms of biomass burning induced teal relative warming, we conduct an ocean mixed layer heat budget analysis. The SST changes can decompose into 7 subterms. The first 4 are from short wave, long wave, sensible heat, and ocean dynamics. And the last 3 are changes from surface wind speed, relative humidity, and air sea temperature gradient by the latent heat flux. The figure shows the biomass burning induced teal SST trend decomposed their contributions with each terms. And for the relative teal SST trend in the red bar, we can see the largest contributors are from shortwave and the wind speed by latent heat flux. We now take a close look at these 2 terms' spatial maps. For the shortwave contribution, biomass burning reduction over the teal increases the clear sky shortwave radiation reaching to the surface and leading to the local warming, especially near the Indian subcontinent, while the cloud changes contribute to the warming primarily near the equator. For the surface wind speed by latent heat flux, the anomalous easterly and northwesterly winds in the teal oppose the background wind and cause decreases in surface wind speed. Therefore, the latent heat flux contributes to a warming effect. So the biomass burning induced relative warming can potentially have regional and climate impacts. Plot A shows rainfall trends. The teal relative warming leads to a significant increase of rainfall over most of the teal, and the cooling of the Western Pacific lead to decrease of rainfall. This zonal pattern suggests that the Indo-Western Pacific warm pool convective center moved westward, and the salinity trends in plot B is consistent with the rainfall pattern. The local rainfall changes can have far-reaching impacts by teleconnections. So here we show the global impacts. In plot A, we can see the North Atlantic jet stream strengthened and shifted northward. And in plot B, we can see this strengthened North Atlantic jet stream transports more water vapor to the northwestern Europe. And these two changes both suggest that there is a shift to the positive NAO phase. However, the more definitive demonstration of the biomass burning decreased and then to the teal relative warming and then to the positive NAO phase still needs further investigation. Here is my summary and I'll stop here. At last, this work is just published this morning and you can find more information if you are interested. Thanks.
Hi, thanks for that great presentation. Can you explain, it's obvious to me how the biomass burning component, how that's impacted was not so obvious to me. Could you explain how that works?
Yes. So anomalous easterly wind, and on southern teal there is northwesterly wind, and this is opposes to the background wind. So the wind speed is decreased, and the wind speed decrease can explain by the latent heat flux, and so the latent heat flux will contribute to a warming effect. If that's
the causality that the latent heat flux is impacted and therefore the wind stress?
Actually, so at here, the last three terms are, they are all impacted by the latent heat flux. And then the latent heat flux is decomposed into three sub components. And the wind speed here is one of them. It's just based on the derivation of the equation.
Okay, thanks.
Thanks.
One thing I noticed is not only in some of your figures, not only was there some warming over the tropical Indian Ocean, but I also saw some cooling over the eastern equatorial Pacific. So do you think the biomass burning could have anything to do with observed strengthening of the Walker cell, for instance?
Oh, thank you for your question. I didn't look at the biomass burning in the other tropical area yet, but I will take a deeper look in the future. Thanks.
Maybe related to all these questions. So in shortwave, you mentioned it's direct aerosol radiative forcing and cloud effect. I was wondering for that cloud effect is mostly local cloud response or cloud response to local radiative forcing or cloud response to remote SST forcing? Like in tropical Pacific SSTs.
I can pull up the backup slides.
I think you showed the shortwave and latent heat resulting energy, but
sorry, which one? Is this helpful for
yeah,
shortwave from clear sky and cloud?
Yeah, there's a local cloud response, but it's driven by local radiative forcing on local heat budget, or it's actually driven by remote SST forcing.
Or could you please repeat your question? I can't hear you.
I was just wondering for this cloud response, is it a response to local forcing, like radiated forcing or SST forcing, or a response to remote forcing, such as in tropical Pacific SSTs changes?
Okay.
Yeah, thanks.
All right, hello everyone. Welcome back to the second session of the Climate Variability and Change Working Group. So we have 15 minutes at the beginning here to just go over some future plans that we have, and we're hoping to have a bit of this time for discussion of anything that you would like to see the working group do. So I'll kick us off here with the first few slides. So we have some additional experiments that we want to be doing in the near future, building off of the single forcing large ensemble. There are a couple of things that came up there that we'd like to investigate. So one is, you're seeing here, this is the response of global in CSM1 and CSM2 in the single forcing large ensembles, but also with the experiments done in different ways. So the solid line is where you only evolve the aerosols in time, and then the dashed lines are where you evolve everything but the aerosols in time. And what we find is that in CSM2, there's a strong sensitivity to what method you use, whereas in CSM1 and the teal lines, there isn't. And so there are a number of reasons potentially for this. One is the very different forcings that were used for the aerosol emissions between CSM1 and CSM2. So we want to run some experiments with CSM2, some single forcing experiments using the CMIP5 aerosol emissions to pull apart what the role of the different emissions is in this differing sensitivities between the models. Another thing we wanted to do is that in this green line here, this is the global mean temperature response to the everything else run, which has things like solar, ozone, land use, land cover change. And what you see here is that there's kind of this persistent warming that happens kind of, and it starts kind of as you go into the SSP portion of the run. And so one question is, what is causing that? And it's hard to pull apart when we have all of those different forcings evolving in time, but we thought a pretty likely candidate for that is maybe this transition in the volcanic forcing. So you go from this historical forcing period that's kind of punctuated by these large volcanic eruptions, and we go into the SSP where we just are specifying this background volcanic aerosol. So we wanted to run a volcanoes only just to see if that was actually what's kind of governing this response we see in the everything else runs. Some more work that is going to be done probably in the next year of the allocation cycle is to look more at regional refinement in the North Pacific. So Yang-O Kwan's group, in collaboration with Clara and others, are already thinking about regional refinement in the Pacific, and this is the grid that they're using. And so we're going to use some of the working group resources. It's going to be led by Jeremy Clavens and Pedro Dinicio to explore regional refinement in the North Pacific, running some, probably to begin with, some idealized time slice experiments with perturbations in the KOE region to look at the impacts on atmospheric circulation. And then depending on how those results look, we may follow this up with a long historical simulation kind of analogous to what we've done or are doing for the North Atlantic. I'm going to hand this over to Aishu to go through this one.
Okay, for this tropical basin interaction experiment, which is led by Clever Tropical Basin Interaction Research Focus Group. For Tier 1 simulation, we basically include two sets. One is we call it historical pacemaker simulation. The other set is historical is handcast. It's run like 12 months. And for the historical portion, we will have 10 and some members each, and except the control simulation, we have the pacemaker for the Atlantic, Indian Ocean, and the Pacific. The experiment design has been revised quite a few times, and right now, it's basically say when we do the restoring the SST, for the Pacific and Indian Ocean will be 15 degrees south and north, and for the Atlantic is 10 degrees south and north. The transition is 15 to 30 for the Pacific and Atlantic and Indian Ocean simulation, but we may change to 10 to 20 for the Atlantic simulation. That's the most recent discussion in this group. For this figure, this is provided by Steve Eager. He has done quite a few testing runs for the second set of simulation. Here, it basically shows that the left figure is the Atlantic Nino, the right figure is the Nino 3 and 4 in the Pacific. You can see that from these two lines, the black line and the red line, okay, this one, this pointer?
Oh, it's the top one.
This one?
Yeah, you'll need to go back, the bottom.
Okay. So this black and the red line, one is smell run, the other one is the TBI simulation. You can see that in the Pacific, both TBI simulation and the smell simulation can have simulate observed Nino 3 and 4 variation, but for the Atlantic Nino, we can only do it using the TBI simulation, but not the smell, which suggests that for the Atlantic, the SIT bias maybe in our model is too large, which cannot produce the Atlantic Nino. This simulation right now is currently ongoing and possibly will be available by the end of this year.
Thanks. And then I think the final thing to mention is that there's more work being done led by Sarah with the mechanically decoupled configuration. So Sarah mentioned some simulations this morning that she did on an NSF allocation, and now this is being built upon with Climate Variability and Change Working Group resources. So these will be made available through the Climate Data Gateway. So there's going to be historical simulations run with greenhouse gas only forcing using the mechanically decoupled configuration. I think these are done, just about to be post-processed. And then some additional climate sensitivity simulations looking at the response to increased CO2 in a more idealized setting. So these data will become available whenever they've been described in a manuscript and post-processed and everything. So I think that's all we have in terms of near-term simulations and things. So we want to have a few minutes. I guess we have 7 minutes for discussion of other ideas of things that you would like to see the working group do. I guess we have some to kickstart the discussion, some kind of broad ideas for future directions. One of the things that we had proposed in the CSL allocation was to try and make use of the new interactive biomass burning capabilities when they're ready to see. Did I do that? Okay. Yeah, to see what is the impacts of having interactive biomass burning emissions in the model. We prescribe them right now, so they're not really linked to the climate. I think Steve showed some very exciting results yesterday in the Earth System Prediction Working Group about the higher resolution configuration, maybe getting the Eastern Tropical Pacific cooling and the connections to the Southern Ocean more correctly. I think it would be really nice to build on that and figure out, do we just need the high resolution ocean, or do we need the high resolution ocean and the atmosphere? And then, of course, we've got quite a lot going on in the realms of regional refinement. So hopefully there'll be a lot of things to build on when these new long regionally refined simulations become available. But yeah, we'd be glad to hear your thoughts if anyone wants to raise any issues you'd like to see addressed by the working group. Clara?
Wondered the proposed simulations. So putting the CMIP 5, are you going to consider also doing a separate biomass burning? I don't know how different they are from CMIP 5 to 6, but that might be valuable if they are different.
Yeah, I think they are quite different, and I think that would be good, especially in light of the last talk.
Exactly.
I mean, I guess at the moment it would be nice to see what in our single forcing large ensembles with CSM1 and CSM2, how different the response to inferred from biomass burning is.
Apparently they are different.
Okay.
Yuxin has analyzed them, she told me.
Right, great, yeah. And I think I think that's good. We can definitely consider doing that.
And then a question for Aishu on the pacemaker. I saw you're going to do full field nudging, but isn't that problematic? Because if the model has a mean state bias in the tropics and you give it the observed mean state, that's very different.
When a decision for the historical pacemaker simulation, we still will do the anomaly. We use the model climatology plus the observed anomaly.
Okay, I misread your slide. Thank you.
That's,
I think that makes more sense, yeah.
This is just discussed recent couple of months. Previously, we were suggested to use the full field.
I don't think that's a good way to go. Yeah, yeah.
Any other thoughts or suggestions? Yeah, Dylan?
Are there plans to formalize a set of extratropical pacemakers, either for North Pacific, North Atlantic, Southern Ocean, that sort of thing?
So yeah, the Southern Ocean, I think work is underway or about to be published on that with CSM2. We haven't run those, but I don't know if Clara wants to talk to the availability of those or...
Southern Ocean pacemaker runs. Sarah King has done the now with CSM2, and that paper is now in published or accepted for publication in PNAS. I can ask, I'm sure she'd be very happy to share the simulations.
Yeah, I think she has shared them with other people that I know of already, so I'm pretty sure you could get them from her. And for other extratropical pacemakers, we didn't have any in the plans, but if there's something you want to propose and a reason to do that, can certainly consider it. Anyone else? We have 2 minutes. Yeah, who?
I think the third lat is very important because if you're going to use high resolution model, ocean model, then it'll take a lot of resources. So are you planning to do any sensitivity experiment like Will did? So using high-res SST and Corson SST to see the difference between two simulations?
Yeah, I think, well, I don't know, Steve and I have discussed this a little. I guess it is very tricky to kind of start a whole new set of experiments and have a pre-industrial control that's balanced and things, but it seems like there could be things that we could do that might be less expensive building off of the decadal prediction results, like taking extreme ends of the kind of trend period and running just with the high-res ocean and with the low-res atmosphere, maybe in collaboration with the Earth System Prediction Working Group. Maybe we can think of something to try and really pull that apart. I'm not sure that we just want to prescribe the SSTs, since I think we'd really want to know what does the high-res ocean dynamics, what is that giving us? But yeah, it's definitely expensive, but of course if we could figure out that it's just the high-res ocean that we need, that's less expensive than needing the high-res ocean and the atmosphere. But okay, I think we're at time, so unless anyone else has anything to say, we'll move on to the next set of talks, and I'll hand it over to Aishu.
We have 3 online talks. The first one will be given by Natalie. Looks good.
All right. Well, thank you so much for.
Looks good.
All right. Well, thank you so much for having me give a talk here. I'm usually over in biogeochemistry or chemistry or something. But I think what I'm going to argue here actually goes to what we were just talking about in the group session there. And I'm just going to give you a little bit about this opinion article that we just submitted to the ACP 20th anniversary special issue. And it has to do with historical and paleoclimate aerosol radiative effects, which of course are key, right, to understanding what's happened over the 20th century for sure. I'm going to give you my main points so that I make sure I get done in my allocated time here, just up front. And then I'll try to show you why I'm arguing this in this article, that we're arguing this in this article. And it's just been posted up, and I welcome your either comments directly to me or anonymously through the ACP website. Everybody knows aerosol impacts on radiation are extremely important for climate, and they are very sensitive to poorly known quantities like size, mixing state, spatial distribution relative to clouds in the current climate. For the pre-industrial or any paleoclimate, we simply have no in situ data by definition. So we really don't know what's going on in pre-industrial. The only thing we can really look at is emissions and deposition, and even there we have very, very limited data. So I'm going to present you a little bit of data just showing that the CMIP6 emission inventories are probably wrong. I could show it for dust. I skipped that for this presentation, but it's in the paper. I'll focus a little more on wildfires here and talk about, there's a little bit of evidence that the wildfires are completely different than what the CMIP6 assumes. So I would argue runs that should be done by this working group that would be really insightful is actually use historical emissions for wildfires and biomass burning that are consistent with the available observations, and instead of continuing to use scenarios that aren't. So I think the CMIP5 is actually lower in the pre-industrial than the CMIP6, so you'll exaggerate the problem I'm going to talk about here if you went to the CMIP5. I would also say that the uncertainties in the pre-industrial emissions and their distribution in the atmosphere are not accounted for. Basically, how we do our uncertainties right now are everybody takes the same emissions from CMIP6 and we look at the model spread to get our unconstrained uncertainties. So errors in the emission data sets are not accounted for, and from the studies that are available, they are the same size as the model spread. So aerosol radiative forcing from pre-industrial to current, unconstrained before the constraints would be about 1.7 times higher, and paleoclimate aerosol radiative forcings are obviously even more uncertain. What we don't know about the current climate, we know even less about paleoclimates. So those are the points I'm going to try to show you in the next just couple of minutes here. So if we think about CMIP6 emissions and the combinations with the models, they don't do a good job for dust, but I'm not going to show you that here, but they also don't do a good job of wildfires, we think. Of course, what we're looking at is black carbon, so it could actually be industrial emissions as well, but there's more data behind those data sets than for the wildfires. But for example, here's a compilation from 2 different studies that do comparisons in the ratios of the present day PD to PI ratio in the ice cores for proxies for wildfires or any kind of combustion. The blue here are the CMIP6, and you can see that in the model results, they are way, way higher than in the observations. Okay, so there's an exaggerated change in aerosols between PI and PD in the CMIP6. I think the CMIP5 might be the AirCom, so it's even worse than that. But if you use alternative biomass burning and databases like the LM Fire, you actually can match the observations, okay? So we know CMIP6 is wrong. We're not sure what, but it could very well be the wildfires. And we need much more wildfires in pre-industrial. So we have a little bit of information about wildfire proxies. So Van der Werf, I'm sorry, this is, I think 2013 here. This is a typo that I've reproduced here. We have charcoal data that are kind of semi-quantitative, and that's what's shown here. Or, methane and CO, which, all these things are a little bit hand wavy. I'm waving my hands here, but you can see that over the last 2,000 years, there's kind of a flat period here. It goes, and there's a little bit of a minimum down to 1750, maximum in 1850, and a decrease since the 1850s. So there's a maximum in wildfires in 1850 suggested from quite a bit of data. And so, if we take 1850 as the beginning of our runs, we should be going down. We don't know exactly why this is. There's different explanations. It could be a climate effect, and it could be a human land use, the cutting up of the terrain. And once you remove natural systems and replace them with agriculture, your fires just completely change the time. And the more land you have in agriculture, for example, you don't have forest fires in that case. And we see something similar in the trends over 20 years before 2017 from satellites. So what does this mean? If you just take a look at the model spread, PI to PD, using the CMIP6 simulations from Bellwin et al. Or from Smith et al., you get a 90% confidence interval of 2.8 watts per meter squared. If you take a look at models that, just one model run between using two different emission scenarios, for example, the ones that match the data versus the CMIP6, you get a spread of 2.8 watts per meter squared also. So this emission uncertainty that we're completely ignoring is the same size as the process uncertainty. This is unconstrained. There are other constraints that we could use here. The dominant source of the uncertainty is wildfires. There's other natural aerosols, but the dominant uncertainty comes from wildfires. What does this mean? Here's the PI, or the radiative forcing at 1850 and the range out to 2100. So I'm reproducing kind of a plot from Smith et al. Here in the blue, and then adding in this extra uncertainty if we include the fact that we don't know what the emissions were in the historical time period. So adding in the uncertainty from those studies, we don't know what the pre-industrial, if we call pre-industrial 1850, what was happening there. So, what could be happening right now is we could have actually a really high anthropogenic aerosol radiative forcing, really large negative, and that could be consistent because we started out with a much larger aerosol forcing than we put in the CMIP6 emissions. I'm just going to say that things are only going to be worse, less glacial maximum the current day. We don't have very good data, and then also we have all this variability in the pre-industrial. So when you say, LGM to pre-industrial, you don't know which pre-industrial to use. So you're only going to have larger uncertainties if you go back farther in time. So we just guessed, a 4.8 watt per meter squared range. So coming back to my conclusions, the CMIP6 emission inventories combined with our models do not match available observations for things like wildfire and dust. But they're poorly known. We really actually need more paleo proxies in order to constrain that. So I would argue that one of the things that this working group could do is take a look at what that means. The other thing to realize is pretty much any time before 1980, we really don't know what the aerosols were doing from the natural aerosol perspective. So contrasting 1940 to 1970 is probably not a good idea because we really don't know the aerosols in 1940 and 1970 very well, okay, because that's before the satellite era. We have to have a really good reconstruction of wildfire to do that. All right, I think that's probably my time there. So pass it back to you.
Right, thanks. Okay, one quick question.
Hi, Natalie, it's Clara. Thank you for your talk. Is there any hope in getting spatial information of observed wildfire evidence? Because I think it matters where the fires are.
Yeah, so I mean, we could do something that's consistent with the charcoal record and consistent with the data, which the CMIP6 is not, right? And so if we use that, we could get some information. But right now, the proxies are not quantitative. That's our biggest problem. And so we really need to put an emphasis on having the wildfire proxies be a little more quantitative. But from the charcoal record, we could probably do something. So I think there is enough. There are cases that we could run to see if it's important. Let me say that. We have emission data sets we could put together that could be run as some controls to see how important these issues are.
Move on to next talk. In terms of timing, yeah. We move on to next, yeah. No. We move on to next talk. Sorry. And Our next talk is also an online presentation, will be given by Daniel.
Yeah, good morning, everyone. Thank you for the opportunity to present this research. I'm Daniel Hugel. I'm a PhD student at Colorado State University, and I'll be talking about ecological risks from rapid cooling with stratospheric aerosol injection. So just to start off, I'd like to give a little background on stratospheric aerosol injection, or SAI for short. So this is a proposed method of climate intervention to cool the planet by adding reflective particles to the stratosphere, analogous to what happens naturally after volcanic eruptions or extreme wildfires. And it's really important to be clear that SAI is not a substitute for decarbonization, but it could complement its goals. And what I mean by that, kind of conceptually, can be thought of in these schematics on the right from a recent United Nations Environmental Program report on climate intervention. The top frame can be thought of as a peak shaving scenario. So with climate change and without some intervention, we might overshoot briefly a temperature threshold that's considered important, and one could use climate intervention to prevent that overshoot from happening. Or you could even use a larger amount of climate intervention to rapidly reduce global mean temperatures, as in the bottom frame on this slide. So to explore these scenarios, I'm making use of data from the recent ARISE SAI project, which many of you have probably heard of at earlier talks in this session or at this workshop. But just to describe this briefly, these are experiments primarily in CESM2, WACM 6, where aerosol is injected at 4 locations to obtain simultaneous global temperature targets, pole-to-pole temperature targets, and a pole-to-equator temperature target against SSP2 4.5 forcing. So I'm using 3 experiments from this. One is shown in the orange on this temperature time series. That's just a standard SSP2 4.5, no SAI climate change scenario, and temperature increases throughout the simulation as expected. In the teal curve, this is called the ARISE 1.5 scenario, where starting in 2035, you maintain global mean temperature at approximately 1.5 degrees Celsius. And this is kind of a peak shaving scenario. So you're maintaining global mean temperature at some value. And then in the lavender curve, ARISE delayed start, this is a similar SAI strategy with a slightly lower temperature target, but the big difference is that you start 10 years later. So with that warming in the meantime, now you actually have to reduce global mean temperatures to go back to that target of, in this case, 1.37 degrees Celsius above pre-industrial. So the climate risk I'm talking about focused on today is the movement of environmental conditions driven by changes in temperature. So ecosystems have an environmental niche that they're adapted to. In a changing climate, that niche moves, and if it moves more quickly than species can follow it, then that can be a problem for species. It can even cause extinction in some cases. So one variable that speaks to this effectively is the climate speed of 2-meter temperature. And this can be thought of as the speed you have to move at to stay in the isotherm where you started. And it's just the rate of change in temperature divided by the spatial gradient of temperature by unit analysis that gives you a speed, usually kilometers per year. And climate speeds of greater than 1 to 2 kilometers per year on land are a problem. Climate speeds greater than about 10 kilometers per year are a big problem anywhere. And there's limitations to this analysis. I'd be happy to talk about that in the Q&A. But overall in the literature, it looks like this variable provides actionable information about the degree of forcing experienced by ecosystems in bulk. So just to provide some intuition, since climate speed scales with the rate of change in temperature, just going back to this time series, if the no SAI climate change trend is a problem, which it is, that's one reason why we're worried about ecosystems and climate change, then maybe ARISE 1.5 isn't going to be as bad because you're holding global mean temperatures nearly constant. But in delayed start, if you wait 10 years and deploy a similar SAI strategy, now you have this really rapid change in temperature to go back to that target that you've passed. And maybe that's a problem too. So when we actually calculate the climate speeds, looking at ARISE 1.5 first, you can see that climate speeds are very small. This is quite similar to pre-industrial climate shown on the left from the pre-industrial control simulation. You see patchy climate speeds consistent with internal variability. And just to be clear here, the sign says nothing about the direction. The sign is just showing whether that speed is associated with a warming or cooling trend. And I've maxed out ocean data for simplicity on these figures. But under delayed start, we see that SSP2 4.5 is shown on the left here, and there's a large force response. from the warming in this simulation. And then on the right, in a rise delayed start, there's a large response with large climate speeds, especially in tropical regions, forced by that cooling. And the way this color bar is set up, anywhere there's color, that's a substantial forcing to terrestrial ecosystems. Taking a more statistical view and bringing in the ocean here, we can see that in a rise 1.5, climate speeds are actually indistinguishable from the pre-industrial control variability. Those distributions overlap completely. But a rise delayed start is actually robustly greater than what would be happening without SAI at all in SSP2 4.5. So essentially, by waiting 10 years, you might actually be making things worse than climate change by deploying a very similar SAI strategy, or at least when you're considering this one aspect of ecological risk. And finally, these climate speeds can provide one way for us to think about relative risk between scenarios. So the way this figure is set up, the x-axis is your change in temperature, and then the y-axis is the area exposed to a climate speed over 9.8 kilometers per year, which is considered a threshold for very high risk in the literature. And I've plotted a whole ton of simulations on here, including some ones I didn't talk about, but the big take-home point is that SAI scenarios where you rapidly reduce global mean temperature can expose more area to large climate speeds than climate change without SAI at all. But in scenarios where you're maintaining global mean temperature, like that Arise 1.5 scenario or the earlier CESM Glen scenario, these experience climate speeds within natural variability. So to wrap up, climate speeds when global mean temperature is maintained with SAI are similar to those experienced in a pre-industrial climate, but a very similar SAI strategy delayed by 10 years yields large planetary scale climate speeds as you reduce global mean temperature. And these climate speeds are far beyond natural variability and greater than what would be experienced under climate change without SAI. I'd like to thank Brian Dobbins, Alicia Karsbeck, Matthew Henry, and Jim Haywood for early access to data that made this analysis possible. That was very helpful. And with that, thank you for listening, and I'd be happy to take any questions.
Please go ahead.
Thanks. Hi, thanks for that great talk. I was interested in maybe somewhat methodologically, you compared land and ocean. So is it the same, you're doing surface temperature changes, or can you explain a little more? And I'm also wondering whether there's a fundamental difference for the ocean versus the land in terms of movement speeds that species could deal with.
Yeah, thank you for that question. So at this stage in the analysis, I'm using 2-meter temperature everywhere, which there's quite a lot of precedent for that in the literature. It is true that ocean ecosystems can adapt more quickly than ecosystems on land. So that's definitely something that has to be factored in. And that's why when we're talking about like relative risk between scenarios, that threshold of 9.8 kilometers per year is quite a bit beyond what either ocean or land ecosystems can adjust to on average.
Any other question?
I was just wondering if people use these kind of metrics for other fields, like incoming solar radiation, I assume would matter, and precipitation and things.
Yeah, so there you can apply this climate speed framework to, well, mathematically you can apply it to any variable, but it's kind of only meaningful for certain ones. There's some kind of specific conditions that go into it, but one reason why it's applied to temperature is that the forced response in these simulations tends to have a very clear sign, and we understand the spatial gradients quite well with temperature. But you can apply this to precipitation. Sometimes you see it applied to temperature at different levels in the ocean, which could be really interesting here because there will be a delayed response to the SAI intervention in the ocean. Yeah, you can apply this to a lot of variables, certainly.
Thank you. Let's move on to the next talk. Will be given by Yanning Guo.
Okay, can you see the slide here?
Yes, everything looks good.
Okay, cool. Thank you for having me online. I'm Yanning, a PhD student at Cornell University, working with Dr. Flavio Liner. Today I'm going to present this work that is done with my advisor and a postdoc in our group about the influences of the forced and unforced Pacific decadal variability on the southwestern United States precipitation. This study is motivated by the discrepancy between the two trend maps. On your left, it is the observed precipitation trend since 1980 from GPCC, and on your right, it is the CESM2 large ensemble mean trend during the same time period. As you can see, there was a significant precipitation decrease in observation, but there's no trend indicated by CESM2 large ensemble. So one of the probable reason for this discrepancy is that in the observation, because this is only one single realization of the historical period, the internal variability may contribute to this precipitation decline. And the precipitation variability in the southwestern United States is reported to be influenced by the Pacific sea surface temperature variability with different timescales. For example, interannually, it is influenced by El Nino Southern Oscillation, and in a longer timescale, it is influenced by the Pacific decadal variability. So the main questions we want to answer in this project is that, first, what is the relationship of the low-frequency Pacific variability and the southwestern United States precipitation? And second, to what extent the observed trend is forced, and forced by what? So in this study, we apply a low-frequency component analysis, LFCA. It is actually just an analogy of ELF analysis, but we try to obtain the modes that the low frequency to total variance ratio is maximized. And there is a similarity between the low frequency pattern, LFP, to ELF pattern, and the low frequency component, which is similar to the principal component in an ELF analysis. We apply LFCA on the 1900 to 2020 Pacific sea surface temperature from ERSST version 5 in order to get as much as possible the full cycles of those low frequency variability in the Pacifics. And we get 4 physical and meaningful mode that is also reported in Wells et al. In 2018. With the first low frequency pattern indicating the forced response potentially from greenhouse gas and also anthropogenic aerosols. The second mode is very interesting here, and I will elaborate more in the following slide. It is a mixed mode that is forced by anthropogenic aerosols and also has some evidence that it is partially the internal Pacific decadal variability. With the third and the fourth modes here are more internally generated Pacific decadal variability. That because of the time limit, I won't discuss more about those 2 modes. So with the 4 temporal and spatial patterns of the decadal variability in the Pacifics, we can construct a multivariate linear regression of precipitation based on the 4 low frequency components. And then we can get the teleconnection that is associated with each SST patterns. And as you can see from the 4 regression maps here, each of the modes are having totally different force response, totally different influence on the southwestern United States precipitation. And for here, I would like to highlight the second low frequency pattern, which it has a very significant impact on the southwestern United States precipitation. So in order to understand this mode more, we have to disentangle the forced and internal component of this mode. So here we apply LFCA on each single ensemble members from CESM to large ensemble. So it can give us an idea about how much of the mode is forced and how much is not. And interestingly, we get similar results from CESM to large ensemble that it is very similar to the observation. And we also include the other 2 CESM2 single forcing simulations, that one is forced only by anthropogenic aerosols, and the other simulation is forced by the other forcings that did not include anthropogenic aerosols. So with the 2 counterfactual experiments, we can isolate the role of the anthropogenic aerosols. So from here, we can see that the first low frequency pattern is actually a combination of the force response from the other forcings as well as the anthropogenic aerosol, with the other forcing contributing to the long-term increasing intensification of this pattern. But the anthropogenic aerosol is influencing the mid-20th century warming hiatus. And the second low frequency pattern is obviously forced by anthropogenic aerosol. And in order to understand what is the physical meaning of the two anthropogenic aerosol forced SST response, we regress the two low frequency components to the aerosol optical depth. And then the result is that the first low frequency pattern from aerosol is forced by the aerosol increasing, especially in the northern hemisphere. And the second low frequency pattern in the anthropogenic aerosol is forced by the aerosol emission shift, especially from the northern hemispheres, North America and Europe to Asia. And our results here is similar as the results from Conrado in 2021 and also Jarre's paper in 2022 and 2023 with different methods. So we again did the regression of the low frequency components in the observation and in the CESM2 full forcing ensemble and the anthropogenic aerosol only ensemble to the precipitation. And we found evidence that the observed low frequency pattern 2, which is very significantly influencing the southwestern United States precipitation, is forced, and it is forced by aerosol shift mode. So there are some key takeaways from our study. First, the Pacific decadal variability is influenced by both internal variability and anthropogenic forces. Second, this mode of PDV influence southwestern United States precipitation through different teleconnection patterns. And finally, we've found evidence in CESM2 that the anthropogenic aerosol, specifically the aerosol shift mode, is contributing to the observed post-1980 southwestern United States drying. And thank you for your attention. And this is actually a project that we are wrapping out and ready for submission. If you have any question, I'm very happy to answer those questions. But if I cannot answer the questions within this 10 minutes, feel free to email me and then reach out. Thank you.
Hi, Ning. Do you have any results on the seasonal dependence of this study?
Yeah, we did. The figures I show here is actually annual mean precipitation, but we also did the same analysis for different seasons. And basically, all the seasons are very consistent, but we found the anthropogenic aerosols has probably the strongest influence in winter and spring. But that was done in observation. We haven't done it yet for the CESM2.
Have any other question? Good.
Wondering, I think what you referred to as the shift there is pretty different between the CMIP5 and CMIP6 emissions. I'm just wondering if you've compared with CSM1.
We actually haven't compared to CSM1, but I remember in Jarre's paper on Journal of Climate 2022, they shows a stronger signal of the aerosol shift mode, but the aerosol shift mode in CSM2 is actually not that strong.
Yeah, I think that's consistent with the emissions difference. Thanks.
Yeah.
Thank you. Let's move on to the next talk. It will be given by Carlos.
There we go. Alrighty. Hi, everyone. So I'm Carlos Martinez, an ASP postdoc here at NCAR, and I'm going to be talking about some continued work that I've been doing on the Caribbean hydroclimate, specifically evaluating the simulations of CESM and other CMIP6 models in the rainfall cycle. Is this working? There you go. Okay. So why the Caribbean? Well, it's a highly vulnerable region to climate variability and change. Many stakeholders in the region rely heavily on their climate and weather services for rainfall information. And this is because it is a rain-fed region. So hydrometeorological disasters like hurricanes, droughts, floods can really largely impact many of the stakeholders in the region. And when I started this work, I found that another reason for my motivation is that it's a relatively understudied region. There isn't a lot of scientific understanding into how and what the rainfall cycle looks like, what that could look like in the future under climate change. That's in large part because it's a relatively data-sparse region. So I was able to collaborate with CIMH, the Caribbean Institute of Meteorology and Hydrology, to look into this region, and I've found a more refined understanding of the rainfall cycle, which you can find in my Martinez et al. 2019 paper. Okay, next slide. Going. Okay, it's taking a minute. So the mission of my work then from this observational understanding is to look at modeling, specifically at the latest state-of-the-art modeling capabilities we have to evaluate the simulation of the rainfall cycle and the governing mechanisms, because there's a myriad of small to large-scale features that impact the hydroclimate in a sub-regional and seasonal lens. And so that's why I'll be utilizing CESM and CMIP6. And these are all the data sets that I have collected to investigate this. To break this down, I'm looking at the CESM 1 and 2, large ensembles, and their AMIP simulations, which is the SST prescribed simulations as well. And then I'm also looking at the high resolution CESM, which is under a 25-kilometer grid and in the atmosphere and a 0.1 degree grid under the ocean, to look at differences in resolution, especially since we're dealing with Caribbean islands, right? Very small land topographies, to see if the models can resolve the features associated with the rainfall cycle. And I also looked at the CMIP6 high-res MIP project, which under the same fine-tuning of a given model can nicely look at comparisons between low and high resolution versions of the same model. And then for my observational benchmark to compare with the models, I looked at several satellite precipitation data sets, as well as ERA5 for the dynamical component of this project, as well as looking at the rain gauges that I've collected within CIMH and the NOAA Global Historical Climatological Network. Alrighty, so the first part of this presentation is showing an overview utilizing one specific subregion for the sake of time, which is over Puerto Rico in the Central Caribbean, and looking at the early rainy season. This is the first of three main seasonal components of the rainfall cycle during the springtime. And I looked at their original resolutions for these models, although the regridding showed similar results. So what you see here, you have the spread of the observational total early rainy seasons in millimeters. And what I find is that the fully coupled model runs underestimate the early rainy season totals, land totals in the Central Caribbean. The high resolution IHEPS run has values, however, both in their fully coupled and AMIP simulations that are within or comparable with what the observations are showing. And similarly with these SST prescribed runs, we see very similar results in both CESM model runs. When I break down the CMIP6 models into their respective model groups, we also find very similar findings, where in the blues denoting the low resolutions and the reds denoting the high resolution, we see values more close to what the observational spread is showing for most model groups. And even in a more contrast, for example, with the ECMWF, we do see a large contrast between the fully coupled runs and the AMIP runs, where the AMIP runs tend to show values that are closer to the observations. And this is the main reason why I wanted to look at the early rainy season, where I found some really interesting findings here, looking at the time series of the mean state of rainfall, the black dotted line denoting the bimodal structure of the rainfall cycle in the Central Caribbean, and most parts of the Caribbean have this modality, where you have the early rainy season in the spring, the midsummer drought, and then the late rainy season. And during the early rainy season, I found a lot of interesting findings in the fully coupled simulations, where we saw a large spread in the ensemble means, where the IHES model, several of the high-resolution CMIP6 models do show an early rainy season peak, whereas the low-resolution models, such as CESM 1 and 2, and those CMIP6 low-resolved models do not show an early rainy season. Interestingly, however, when the models have the SSTs, observed SSTs prescribed, we do see an early rainy season peak, regardless of the resolution of the model. So this to me suggests that there is some linkages here perhaps with the dynamics, large-scale features that inform the rainfall cycle, especially if we're seeing similar findings regardless of the resolution. And so I'm going to now look and examine the individual models because I wanted to see if there were any differences between the model groups high and low resolutions. And so what you see here is the ocean-only early rainy season precipitation versus land-only. The black is showing the observed values as well as the land-only totals on the top left table here. And what we see is a large contrast between the fully coupled and the AMIP versions of these models, where we do see a shift with the values closer to what the observations are showing in the AMIP runs for a majority of these different models, and to some extent a difference between each model group's low and high resolution versions, where the high resolution is having values closer to the observations. And so now I'm going to look at the dynamics here, where I regraded the values, regraded the resolution to a 1 degree. And what you see in this example is looking at, for example, SLP, or sea level pressure with the zonal mean removed, for each model correlating with their May precipitation land values in the Central Caribbean. And what we see is a large low, or lower sea level pressure corresponding to more precipitation. And alongside this, we see this circulation pattern denoting this low that would weaken, technically, the North Atlantic subtropical high, or the NASH, which is one of the main facilitators of moisture convergence in the region. We also looked at the AMIP simulations, and even though we do see the improvement in the AMIP runs in the scatter plots of precipitation, the values are very similar in terms of the spatial structure in comparison to the fully coupled runs. So this to me shows that there are intermodal differences in the large-scale circulation regardless of the configuration of the model. And then when I examine a spatial average over the Caribbean basin here to look at each model's sea level pressure value corresponding with their precipitation values over this region, what I do see is this very clear linear relationship where the models that have higher sea level pressure denote lower precipitation values over the region. And similarly in the AMIP runs, although the range is much smaller, we do see this similar linear relationship. And so thinking that NASH has a big role in this, I calculated the longitudinal center of the subtropical high across the models in ERA 5, and what I do see is that most model, if not all model groups, have the center of the high further west than what ERA 5 shows, which denotes a closer high to the Caribbean basin, perhaps more subsidence, and perhaps a reason why you do see this dry early rainy season bias. And this is also true for the other subregions as well, and then this is looking at sea surface temperatures where we also see this relationship as well. And so finally, the last thing is the total moisture budget, which looks at all of this in a nice picture. What I see here is the AMIP minus the fully coupled runs for all of these different model groups. And what we see in the AMIP runs is moisture more into the Caribbean basin with more southerly flow from this moisture flux analysis. We do see warmer SSTs in the AMIP runs with the exception of CESM2. And we do see in the high resolution CESM runs, the difference is quite muted actually, which denotes what we saw in that first figure I shared where the values, regardless of the configuration in the CESM runs for the high resolution are similar to one another. And so these are my general conclusions. I found that most coupled models underestimate the early rainy season land and ocean totals across the Caribbean and to some extent in the other seasons. There is improvement when SSTs are prescribed and to some extent under high resolution models. And there perhaps are some dynamical linkages here that should be explored further. Thank you. Okay, no worries. Thank you.
Carlos is here, and if you have a question, you can just ask him. Next talk will be given by Ke Zhou.
Okay, so good morning, everyone. I'm a PhD student from Georgia Tech, and today I'm going to talk about the model uncertainties in the projections of summer North Pacific high. This work is in collaboration with my advisor, Jay, and Ayla from NCAR. So to start with, the North Pacific Subtropical High, or the NPSH, is a semi-high pressure system located in the North Pacific, and it's also part of the planetary wave system. The NPSH in the summer is usually maintained by the length-thermal contrast, the summer monsoonal heating, and also the extratropical trends in eddy fluxes. And the summer monsoonal heating is shown to be the main driver. We care about the summer NPSH because it's huge economic and hydrological impact. So for instance, the variability in the summer NPSH has a significant impact on the monsoon and typhoon over the East Asia. So in the future, if the western branch of the NPSH extend further westwards, that might potentially cause more typhoons and floods. On the other hand, the future changes of the NPSH could also intensify the drought over California. So now let's see how our state-of-the-art models project the NPSH changes. So here on the top panel, I show the response of the summer NPSH in a couple models under the abrupt FOOTMC2 scenarios. And I look at the 46, CMIP 5, and CMIP 6 models. So I use the eddy stream function at the 850 hectopascal to represent the NPSH. As you can see, the changes of the multimodal domain has a very, very weak weakening in the North Pacific. However, if you look at the individual models and see how they deviate from the multimodal domain, and you can see the models are all over the place. So if we look at the intermodal standard deviation of the NPSH response, then we can identify 4 hotspots with high intermodal variance, and they locate at the West Pacific and North Pacific, North Central Pacific, and the East Pacific and Gulf of Mexico. So if you look at these 4 regions, you can see in a lot of places, the intermodal standard deviation is actually much higher than the multimodal mean. So we want to know what's the source of these intermodal spread. And to look at this, we utilize intermodal UF analysis, where we can decompose this intermodal variance into a PC series in the model space and also the spatial information that contains different UF modes. So let's first look at the first leading IUF modes of the NPSH changes from a couple models. So in the first mode, you first see there is a strengthening and overall westward extent of the NPSH, and you see 2 maximum centers that is captured in the NP and NCP regions. And for the second mode, you can see the strengthening of the NPSH located in the West Pacific regions, and both modes accounting for more than 75% of the intermodal variance. However, we wanted to identify what causes this intermodal uncertainties. However, it's too complicated. So we are wondering if we can simplify the questions by using the AGCM. So in the AMIP scenarios, there are models that is forced with the identical 4 times CO2 concentrations, and they're also forced with the identical SST changes in the future. So we call this set of AMIP models as the AMIP 4 times CO2 plus futures. As you can see, the intermodal variance over the WP regions are well captured by the leading mode of the AMIP 4 times CO2 plus futures. And then if we compare these patterns with our IUF2 in the couple models, and we see our big similarities. So this encourages us to hypothesize maybe the IUF2 of the NPSH changes is due to the non-SST related factors. So what is these factors? As we stated before, the tropical precipitations play a major role in maintaining the NPSH. So here, we look at how the tropical precipitations associated with these intermodal spread of the NPSH changes. So on the plot here, we show the tropical precipitation changes project onto the PC2 of the NPSH intermodal EOF. And then we do the same thing for the AMIP 4 times CO2 plus futures. And you can see in both scenarios, you see a wet south and dry north dipole patterns. And now we take these patterns, and then we fit the related diabatic heating to the CESM CAM5, and then we see how the model responds to this non-SST related intermodal spread in tropical precipitation. And here is our results. So the plot here shows the low-level circulation response, and then you can see we successfully reproduce the the intensify of the NPSH in the WP regions, and you also see a cyclonic changes in APG regions, and also a little bit westward extension of the NPSH. And this is very consistent with our statistical analysis. So to delve into the mechanisms, the circulation changes is actually just a material gilt type response in response to the asymmetric heatings respect to the equator. And then to put this into a better perspective, we can also look at the upper level response of the circulation changes. And then you can see there is a baroclinic structure around 15 to north, 20 north. And then we can also see a barotropic structures here around the 45 to 55 north. In addition, we can see a very clear propagation of the Rossby wave train from the tropic to North America. So now we know the IUF2 of the MPSH intermodal spread in the couple model is due to the non-SSE related intermodal spread in precipitation. So what about the first mode of the intermodal spread? As we know, the different UF modes, they are orthogonal to each other. So we might be hypothesized the first mode is probably due to some SSE related factors. Okay, so now first of all, we need to get the intermodal spread of the SST. So to do this, we plot the intermodal PC1 of the MPSH intermodal spread. And then we choose 18 models with significant PC values. And then we compose the SST changes with the positive and negative models. And then here is the SST intermodal spread plots. As you can see, we have like a La Nina-like cooling patterns as the intermodal bias of the SST pattern. And now we fit this pattern to CAM5. And then we will produce some diabatic heat anomalies. And interestingly, if you compare this SST intermodal spread-driven diabatic heat anomalies, and then compare it with the precipitation that is associated with that mode of the MPSH, you see a very similar wet and dry alternating patterns spanning from the maritime continent all the way to the Central Pacific. Okay, so now let's just take the tropical part of the diabatic heat anomaly, and then we use a similar method and fit into the CAM5. And here is our results. So the lower panel is the 150 hydropascal changes, and the upper level is the 300 hydropascal changes. As you can see, we still see a very similar gilt type response, but just slightly shift eastward. And in the upper troposphere, you still see a similar Rossby wave propagation from the tropics to the North America. And then if we compare our experiment results with our statistical results, and you can see we also successfully reproduce the high intermodal variance over the MP and NCP region, and also the EPG regions. And so now we know the leading mode of the MPSH intermodal spread in the couple model is actually due to SST-driven intermodal spread in the tropical precipitation. So to quickly summarize this work, we know the state-of-the-art models show very large diversities in the future projection of the summer MPSH. And the source of these uncertainty originates from the tropics. The intermodal spread in the tropical SST will affect MPSH through the production of the anomalous precipitations. And on the other hand, that the intermodal spread of precipitation that has nothing to do with SST will also contribute to the modal uncertainties in the MPSH projections. Yeah, and that's it. Thank you.
Kind of encouraging that, you only have a couple of things to worry about, that in some sense life is simple. But I wonder, do you think that there would be differences, systematic differences in future projections? If you looked at, models that were kind of positive for the EUF pattern or negative for the EUF pattern, just looking across the biases in the models?
Sorry, can you?
Well, you're looking at differences between the models in the present-day climate, right?
No, I'm looking at the intermodal spread, so basically just looking at the model world.
Yeah, but I'm saying for each of those models, there's a future projection.
Yeah.
Right. So do the differences that you can characterize this in this very nice low-order way have consequences for the projections that the models make of what happens in the future in this region where people would care about the rainfall? Yeah.
I think you can. And actually, now what I'm doing is I'm trying to see if I can see the similar relationships in the current day precipitation and the relationship with the subtropical circulations, and I do see the correlation. So what I'm doing now is I'm trying to constrain this part by tuning the diabatic heatings and see if I can make the signal-to-noise ratio of the MPSH changes in the model in the future scenarios smaller. So that will be probably more important. Yeah, thank you.
Thank you. And move on to the next talk. It will be given by Daniel.
Hi, everyone. Thanks for having me here today. Today I'll be talking about recent research that just got published, looking at the impact of stratospheric aerosol injection on extreme fire weather risk. And this is work done in collaboration with Jim Hurl, Marie Tai, and Katie Dagan. And thanks to NCAR for making the ARISE simulations publicly available. So the motivation for this work was the recent and future trends that we've been seeing in extreme fire weather. So extreme fire weather are conditions that can lead to large wildfires to occur and spread. And we've been seeing that over the last 4 decades, there's been significant trends, increasing trends in these type of conditions over much of the globe. So you can see places we're familiar with, such as Western North America, parts of the Amazon, parts of Southern Africa, and parts of Europe, where we know there have been really large wildfires occurring. And looking into the future, there have been many studies looking at how extreme fire weather will look like in the future. And in our study, we found that extreme fire weather will become the new normal in over 70% of the globe by 2080. That means that the frequency of extreme fire weather will emerge above the historic natural variability. So you can see that in many parts, the signal has already emerged in the CESM1 large ensemble, and in many places it will emerge in the next several decades. So we wanted to understand how stratospheric aerosol injection, which is a form of climate intervention, which Daniel explained really nicely earlier today, would impact extreme fire weather. And we know that SAI can decrease global temperatures quite well, but it sometimes has unintended consequences. For example, Tai et al. Showed that there are regional differences in how SAI could impact consecutive dry days and total wet day precipitation. And you can see that in some regions, there's a lot of drying projected to occur under SAI. And another study showed that global burn area would also decrease under SAI. However, these impacts are regionally varied. So for example, if we look at the impact of SAI by latitude, we see that while SAI has a net decrease in global burn area by the end of the century, it's not equivalent over the whole globe. So you can see that in the northern hemisphere, SAI has a really small impact on burned area, while in the tropics, SAI has a large decrease in burn area. And so we wanted to understand what SAI looks like for extreme fire weather. So to do that, we use the ARISE SAI 1.5 simulation suite. And this consists of an SSP245 baseline scenario. So we have 10 ensemble members run with CESM2 WACM6 from 2015 to 2100. And the ARISE SAI simulations inject stratospheric aerosols starting in 2035 all the way to 2069. And the goals of this injection is to maintain global mean surface temperatures below 1.5 degrees Celsius above pre-industrial levels, and to maintain north to south and equator to pole temperature gradients. And using these simulations, we quantify the Canadian Forest Fire Weather Index. This is an index that assimilates different daily climate inputs that are important for fire weather, and calculates 3 different moisture codes on different timescales, and then gives us a daily index that gives us what our fire weather conditions will look like. And we use the 99th percentile to define extreme fire weather days. So under SSP 245, you can see that extreme fire weather frequency will increase in many parts of the globe. And I want to note that these increases are on top of what we've already witnessed in many parts of the globe. So you can see that parts of the Mediterranean, the Amazon, Central America, and Africa all see increases in extreme fire weather risk by mid-century under this scenario. If you look at the difference between the SAI simulations and the SSP2 simulations, SSP 245 simulations over this period, you can see that SAI leads to a dampening of many of these increases in many parts of the globe. So you can see that over the Mediterranean, we see this really, this dampened signal of increases in extreme fire weather events. On the other, but there are also regions such as West Central Africa and parts of the Amazon that show increases in extreme fire weather events under SAI. So on top of what we're seeing in the global warming scenario. So let's dive into these 2 regions a little bit to see what's going on. So if we look at the time series of extreme fire weather frequency change from 2015 to 2035, we see that right after stratospheric aerosol injection, we see dampening of extreme fire weather event increases under SAI. However, there are still some increases in the Mediterranean region by the end of the simulation period. On the other hand, under SSP 245, we see continuous increases throughout the simulation period. And we looked at the 3 different moisture codes, or 3 different drought codes, to understand why this is occurring, what is causing the differences between SSP and ARISE. And we find that that under SAI, all 3 drought codes are wetter than in SSP 245. So you can see that daily, weekly, and monthly drought conditions are all decreasing under SAI. However, in West Central Africa, you can see that the ensembles, you can see that SSP and ARISE don't really differ that much at the beginning of the simulation period, but going further into the future, you can see that they start to separate. So by this point, SAI is showing much larger increases in extreme fire weather events than SSP 245. And we can look at the different moisture codes for this region too, and we find that there isn't much difference. There isn't a significant difference between in the daily conditions between SSP 245 and ARISE, but we do see really large increases or large drying in SAI on weekly to monthly conditions compared to SSP 245 under SAI. So overall, we found that stratospheric aerosol injection does dampen increases in extreme fire weather under warming in many regions, but there are regions that do experience increases in extreme fire weather due to drying on weekly to monthly timescales. And we also saw that the impacts vary seasonally and multi-annually, though I didn't show it here. And I do want to note that we don't examine changes in fire fuels or ignition in this study as well. Thank you.
Thank you. Very interesting talk. I have a question. So the SAI scenario is based on SSP 585. while that's the background, and then we apply. Oh no, it isn't. It's on 4.5.
Yeah, it's SSP 245.
Okay, so you compare the same land data in your analysis here.
Yeah, the
That's
land
different.
data stays the same.
Right.
Yeah.
Okay. Thanks for
So
clarifying.
yeah, so the fire fuels might change because of vegetation growth and drying of the vegetation, but in terms of land use, they are the same. Yeah.
Okay. Thank you.
Yeah.
Next talk will be given by Osamu. Okay.
Okay, hello. I'm Osamu, I'm a postdoc here, and I'll be talking today about the efforts we've done, and it's an ongoing project on trying to understand the warming of hot days, and this is in collaboration with Isla Simpson and Brian Medeiros. So we all know that one of the most robust responses to anthropogenic emissions of greenhouse gases is surface warming, and that this surface warming has a spatial pattern. In particular, for mean surface warming, there's more warming that we project to happen in the high latitudes that we call Arctic amplification. And even just focusing on the mean, there's very important applications to the spatial pattern of warming, such as the response of atmospheric large-scale circulation, sea ice melting, ocean heat uptake, and so on. But there's growing interest in trying to understand the warming, the spatial pattern of warming beyond the mean. And for example, we want to know the full distribution, but in particular, the right tail of the distribution is important, right? Because of its applications to things like heat waves. So this shows the warming of hot days as defined as the days exceeding the 95th percentile for the moderately high emission scenario, and this is the multi-model mean. And you might be able to immediately see there's differences between this warming pattern of hot days compared to the mean. There's not as much of an Arctic amplification going on here, and to make it a little easier to compare, here's a plot now showing the difference between the two. So wherever the plot is red here, you get more warming of hot days relative to the mean days, and the opposite for the blue. Another way to think about it is the red regions are where the right tail is getting expanded to the right, further to the right, and the blue regions are contracting the distribution. And we see this systematic latitudinal structure where the high latitudes see as contraction in the distribution, the right tail, and the low latitudes see an expansion. And this isn't the first time something like this has been shown. For example, Mike Byrne looked at this, the amplified warming of hot days relative to the mean in the tropics, as shown by this red line that's increasing to the right. So the mean warming is all the way to the left here, and as you go towards the right of this plot, you're increasingly looking at the rightmost tail of the distribution, and the fact that it's sloping upwards means that you get more warming as you get to these hotter and hotter days. And this is Mike explains using a very simple theory in the tropics where we assume moist convective adjustment and weak temperature gradients. This dashed line is able to explain this multimodal mean response very well. And just to keep it short, this prediction is made because hot days tend to be dry, and with the moist static energy constraint, this relative small change in moisture on hot days has to be compensated by a large increase in internal energy or temperature. So there's a lot of questions here, though, that I thought through, like when I read this paper. For example, a lot of these studies focus on one season or the annual mean, so we don't have a complete understanding of both the spatial and the temporal structure of how these amplifications of amplified warming of hot days look like. And another thing is this large spread we see around the multimodal mean. So is there something we can do about that and try to understand why models disagree and how we can constrain this spread? So starting with the first question, going back to this is the same plot, we see not only latitudinal variation, but longitudinal variation as well for the annual mean warming of hot days relative to the mean. In particular, South America stands out And this has been reported before with CMIP5 models, so this is not new. But what is new is the seasonal cycle of this amplified warming of hot days. This now shows the seasonal amplitude is just the range across this seasonal cycle. So where you get these yellow colors is where you have a large seasonal amplitude. And if you've been looking at the color bars, the magnitude of this cycle is about as large as the signal in the annual mean itself. So this suggests that in some parts of the tropics, the amplified warming of hot days occurs in a very specific part of the season and not rest of the year. And these three regions stand out here in particular now: Southeast Asia, South America again, and this southern part of Africa. And so if we look at the seasonal cycle in these three regions, starting with the Southeast Asia region, we see this systematic peak that occurs in the summertime. And since this is a northern hemisphere region, that corresponds to June. And if we look at the South America region, which is now in the southern hemisphere, again, we see that this largest amplification of the warming of hot days occurs during the southern hemisphere summer, so in December. And another southern hemisphere example was the southern Africa region. And here again, we see this systematic seasonal cycle where you get the most warming of hot days relative to the mean during the summertime. So this suggests perhaps there's a simple explanation to the mechanism behind what governs the seasonal cycle. And moving on now to that second question, one way to try to get closer to a mechanistic understanding for something like surface temperature is the surface energy budget. And here the relevant state variables are temperature and moisture of both the surface and the atmosphere. And the energy budget is maintained by a net radiative heating of the surface balanced by sensible and latent cooling, which both, in simple terms, just depend on the gradient between these temperature and moisture terms. On hot days, as I said earlier, the idea is that the surface is moisture limited, so your ability to cool evaporatively is low on those days. And so sensible heating has to take up that slack, which should mean that atmospheric temperature is high on these days. And so we expect sensible heating to be positively correlated with the amplified warming of hot days, whereas latent or evaporative cooling to be negatively correlated. And this has been shown for the spatial pattern of the warming and sensible heat shown here by Suchin's work. So the left panel shows a very similar kind of plot as I showed before, the amplified warming of hot days, but for the CMIP5 model mean. And the middle panel shows sensible heat. And we can see that just by eye, there's a very strong positive pattern correlation here. And now if we add sensible heating, evaporative cooling on the right, we see that there's an almost exact opposite response as we expected from that schematic I drew. So this was for the the spatial patterns. What hasn't been done before is, does the same explanation actually explain intermodal spread, intermodal variations? And this plot shows just this magnitude of intermodal spread. So bright yellow regions are where models disagree most on this amplified warming, and the same regions that we saw where the signal is strong pops up again here. And as an example, I'll just show you first this Southeast Asia region, and we see that models that project the largest amplified warming of hot days indeed also project largest enhanced sensible heating on hot days. So the left panel shows this very strong positive correlations across models in this signal, and the right panel shows this negative correlation. We can see evaporative cooling. And the one obligatory CSM plug here is that CSM runs in the middle of the pack here, and we don't know for sure if this is a good thing or a bad thing because we still haven't constrained it with observations, but that's the next step. And the last thing I'll show is that if we now, that was one grid point, right? If we look at this pattern, the correlation across all grid points, we see that it works really well almost globally. So there's a strong positive correlation across models between the warming response and sensible heating, and the negative correlation for latent heat. And because I'm out of time, I'll just leave my takeaways here and help you to answer any questions.
I think the mean Arctic amplification is mainly a wintertime phenomenon, and I've shown with James' screen that as Arctic sea ice melts, you'll have a reduction in wintertime cold air outbreaks. So I feel like the Arctic amplification mean state and the, synoptic variability in the winter, that's very different, I think, from what you're emphasizing, which is a warm season, hot day view. Is that right?
Yes, there's also a very strong seasonality to this metric of relative warming of hot days to mean days in the Arctic, where in the wintertime, you get this contraction, which dominates the annual mean. But in the summer, you actually get an expansion. And I think it has something to do with moist air intrusions, which obviously are connected to cold air outbreaks, because those are the days that are the hottest days of the year in the Arctic. And my sort of intuition there is it might have something to do with the reduced meridional gradient in temperature or energy in the future. So my just guess here is that these warm days don't get as much as warmer because moist air outbreaks or moist air intrusions may be becoming weaker or less frequent as the sea ice melts.
Thank you. By Umi Kim.
Hello, thank you for having me here. My research focuses on understanding the interaction between the atmosphere and land. And in today's talks, I'm going to talk about the association between precipitation intermittency and soil moisture variability in CSM model and observations. And this work is collaborated with Ayla Simpson at NCAR. We know that the atmosphere and land are tightly related to each other, constantly exchanging energy, fluxes, and water masses. And precipitation is the main source of the soil moisture. Therefore, plenty of studies have focused on how the amount of precipitation and its variability affect the variability of soil moisture. However, little attention has been paid how intermittency of precipitation, which means the temporal distribution or discontinuity of precipitation, is associated with soil moisture variability. This question needs more attention because intermittency is a core characteristic of precipitation, and precipitation intermittency is expected to change under future warming scenarios by showing more increases in extreme precipitation event and extended dry days. Therefore, these changes would have some influence on the mean soil moisture condition. So in our study, when we talk about precipitation intermittency, we mean the temporal distribution of daily precipitation of a given season. The hypothesis is that different precipitation intermittency, different situation with different precipitation intermittency can influence in a different way the surface fluxes and runoff, therefore leading to a different mean soil moisture condition. For example, we can assume two periods with a different kind of precipitation intermittency. For example, the first period with low precipitation intermittency, where we have rainfall distribute evenly in more days, and extending the full period like that. And the second case would be the period with having the same amount of rainfall, but just the rainfall pouring in fewer days, therefore having a large amount of rainfall falling in fewer days, and the rest of the days just stay dry. In this case, we would expect that we will see different like values of surface fluxes, for example, sensible heat flux and evapotranspiration and runoff. Therefore, this would influence in a different way to mean precipitation in a long term. And so in this presentation, I'm just going to present, so the whole idea of my research is to understand this connection between the fluxes and the variables. But in this presentation, I'm going to present the first part of the research, which is about the quantification of statistical association between precipitation intermittency and soil moisture on a seasonal scale and during the present day. Then, if it's possible, to try to identify whether there are some regions where these associations are stronger or weaker, and using the CSM model output and observational-based data set. So, and data and method that we use is the CSM large ensemble, the SSP 3.7 S370, which has the 100 ensemble members. Then for the observational-based data, we use ERA5 and ERA5 LAN. Actually, ERA5 LAN is the offline ERA5 LAN model, which is forced with the ERA5 observation. We take two variables from this data set, which are surface soil moisture and daily precipitation. This daily precipitation is used to calculate index for precipitation intermittency. The precipitation intermittency that we use is based on the number of wet days, and the index basically quantifies how many wet days a given region needs to have the 50% of the total rainfall of that season. From now on, I will just call this index as the wet day index. And using this index, the high value of wet day index means a low precipitation intermittency because there are more days with rainfall, and low wet day index indicates high precipitation intermittency. And the method to quantify the association between precipitation and the association between the precipitation intermittency and soil moisture, we use partial regression analysis. In this method, we try to remove the influence of precipitation that still exists in soil moisture and wet day index, as these two variables are highly correlated with the amount of precipitation. Therefore, regression analysis is applied first to the soil moisture and wet days separately to remove the influence of precipitation. Then again, the regression analysis is performed between these two residuals, the residual of soil moisture and residual of precipitation. And the positive regression coefficients means a more wet day index is related to the more soil moisture, and vice versa. A negative regression coefficient means that more wet day index is related to the less soil moisture condition. So this is some of the results that I got from this regression analysis. This one, so the upper panel shows the regression coefficients from the ERA5, and the lower panel is for the CSM, for the DJF in the left side and JJA for the right side. The first observation is that the association between precipitation intermittency or wet day index and soil moisture is overall positive in general, both in ERA5 and CSM. But there is still some sort of spatial consistency between these two data sets, mostly when we observe DJF, when there are over the region where ERA5 shows the negative regression, there are also negative regression in the CSM. Another observation is that the magnitude or the signs of the regression look like they change with the season. For example, from the DJF to JJA in ERA5. we can observe this better when we make a longitudinal means of the regression coefficient and separating the season in drier and wetter season. And here we have the CSM, and another in the right side we have the era 5. We can see that the magnitude of the regression becomes larger during the wetter season. And this plot is basically showing the same. It's the global mean of the regression coefficients, and it's showing that the higher, larger magnitude is shown is more like there are more larger magnitudes during the wetter season. And one observation is that in general it looked like the era 5 have shows the regression values which are more larger than the CSM ensemble, CSM even considering the maximum and minimum ensemble range. So here is kind of summarizing all the short results that I showed today. So overall, the positive association is more dominant, which indicates that high precipitation intermittency is linked with a low soil moisture condition and vice versa. In general, CSM and era 5 show some kind of consistent spatial pattern, though there are differences in some region. And the magnitude of the regression seems to be bigger in era 5. And the last observation is that magnitude of the regression coefficient look like they depends on the mean precipitation, so wetter season. Larger and positive regression coefficient occurred more frequently during wetter season, and smaller and negative coefficient is more observed during the drier season. Yes. And the next step would be trying to understand what's happening with the fluxes during these different association, different signal, different sign of association, and to try to understand how this relationship changed in the future climate scenario. Okay, thank you.
Thank you. And having the interest of time, we'll move on to the next talk. And if you have questions, just ask me in person. Our next talk will be online talk. It will be given by Wahid.
You should be able to share over Meet.
Sorry, I'm unable to share the screen. Can you please see if it's an issue from your side? Okay.
Try now.
Yep. Okay, so thank you. I hope you can hear me okay and everything is clear. Okay. So thank you for this nice event and invitation. It's my first time presenting at this platform, and I've seen very nice presentation being delivered. And finally, I saw something at the end that are related to my work and some capacity. So the work I'm about to present include my PhD work that I did while I was a PhD student in China. I graduated very recently in 2020. So most of the work is out except the final chapter that is under review in Journal of Climate, and I got some minor comments from the final reviewer that I'm working on. So I will start with some brief background and then move towards the work that I've done in the recent past, and then what we are doing now and how we are considering CSM in this work, and also in some other work, especially the nature of the climate extremes and the natural and the forced variability of the climate in the South Asian region, the monsoon, the Asian monsoon. So from the literature, we have found that there are two forcing associated with the Himalayan and the Tibetan plateau. There are these two terms interchangeably used in the literature that include the Himalaya or the Tibetan Plateau, and the studies conducted so far, they're mostly focusing on their nature of the heat sink or the heat source. So I started this work considering the influence of the soil moisture in controlling these thermal forcing of the plateau, because the thermal forcing are playing a much substantial and greater role in controlling the regional circulation pattern in the water cycle of the region that has been discovered in many outstanding research articles. So due to the nature of the complex topography and the regional, the nature of the region, there isn't enough soil moisture data available. So I started with using remotely sensed soil moisture data from one of the source, and employed some reanalysis data. So from the comparison, we found that the reanalysis and the GL-DAS soil moisture has substantial limitation, especially during the transition phase, when the nature of the plateau switch from the heat sinks to the heat source, and that is the timing of the South Asian monsoon onset, and a lot is happening during that time. So in our initial study, we conducted with this remote sensing soil moisture data, we discovered that a lot of precipitation. We used the couple manifold technique by Navarre and Trivia, where we separated the precipitation and the that is connected to the soil moisture forcing, the spring soil moisture forcing over the Tibetan Plateau. And then we discovered that over the Tibetan Plateau, the soil moisture controlled thermal forcing has a major role in controlling the divergent circulation pattern over the plateau, as shown here in this picture in the down right here. And we can see that over the eastern plateau in the Indian Ocean and in the Bay of Bengal, there is much going on here. So we found this pattern during the transition phase, and we were able to link this with the soil moisture variability in the region. And there was this dipole pattern of the South Asian monsoon related to the soil moisture variability. This study was published in Journal of Climate. In the next phase, we focused on the Yangtze River basin. We used the same data set and used partial regression, because we got a lot of questions asking the influence of the INSO and the Pacific and the Indian Ocean. So we removed that signal using the partial multiple regression analysis, and then we used the data, and we discovered that the Yangtze River basin monsoon precipitation is also influenced by the Tibetan Plateau or the Himalayan soil moisture variability, and especially when there was like these extreme flooding years in the Yangtze River basin before the dam, the Three Gorges dam was built. So those peaks were coinciding. So we discovered that the plateau thermal forcing interact with the atmospheric circulations in this region, and these atmospheric patterns like the South Asian high or the Pacific high, and how these high pressure systems are modulated by these diabatic heating of the plateau, and as a result, how it influences the regional variability of the precipitation, not only in the South Asian region, but also in the East Asian region of the Asian monsoon. But the major difference between the South Asian and the East Asian, and that was the reason we split the study into two parts, was that the dynamics are a bit different. The whole plateau, the nature of the plateau soil moisture, when we consider the South Asian monsoon, is a bit different when we look into the East Asian monsoon. There is this dipole pattern. When the eastern plateau is wet, we see more precipitation in the Yangtze. But in comparison, when the plateau is wet, we see less precipitation in the South Asia. So this is the one of our outstanding study. Now we are working on this. One of our graduate students from the lab where I graduated from, he is working on this aspect to explore this in more details. So after this work, my next work is focusing on the South Asian monsoon onset. This work is under review in Journal of Climate, and I got some, out of the 3 reviewers, now I'm dealing with the final review or some text modification. Because of the extensive review, I lost track of the original text. So now I'm re-ordering the paper, some terminologies, some abbreviations that I've used in the while I started this work as my PhD chapter. So in this work, this is the last chapter, we found that the Arabian Sea and the Western South Asian monsoon onset is significantly sensitive to the Tibetan Plateau and the Himalayan regions, soil moisture, thermal controls over the plateau, thermal profile. And in this part, we found, based on the previous study where the South Asian high, you can see here in this down right, the first panel on the left side panel, we see the South Asian high modulation. So building on this hypothesis and some comments from the reviewer, we conducted this study and we explored that this movement not only influenced the East Asian monsoon, but in this move, it also influenced the South Asian monsoon onset timing and also the related precipitation patterns here. So we see the South Asian high down here in the right corner here, and the monsoon onset variability in time. So this work is also finalized and hopefully it will be out soon. So learning from these diagnostic and some physics and process-based approaches to explore the soil moisture thermal controls, we started working on utilizing the CESM capabilities based on our interaction with the CSM and our efforts to build this on our server and then the problems we encounter. So during this time, we also employed RHCM and conducted a study where we adopted another approach rather than using like 75th percentile or some other like 110th percentile or above normal or below normal scenario. We focused on a much realistic simulation where we employed the ECV soil moisture and we forced the coupled model using the Bates scheme. So we forced the RHCM model with the ECV data rather than the model producing its own soil moisture data and using that to calculate the flux and momentum exchange between the land surface and the atmosphere. And with that, we found that over the East Asian monsoon, there is a dipole pattern and soil moisture has a substantial role in it. We also discovered that the ocean, like the ENSO, is a 3 to 5 year cycle or other oceanic forcing are not continuously there, but the soil moisture influence is always there. And from there, we discovered a dipole pattern and we proved that with the RHCM. That study is also out in the NPJ Climate and Atmospheric Sciences recently published. For now, we are working on the CSM, but quite recently I moved here to the Middle East and now I'm calculating my steps and working with my group and also looking for new collaboration to see with current resources that I have and the proposal that I'm about to submit to utilize the CSM capabilities and the data that is currently available from the CSM, not only to look into these control and sensitivity experiments, like what is happening in that regions, not only affecting the monsoon, but also the river hydrology and the cropping pattern and everything like the major river basin, the Indus, the Ganges, the Brahmaputra, the Amo, all these river basin are also would be substantially affected by any changes that is taking place over the plateau. So thank you, and that's what I wanted to share with you, and hopefully I'm looking forward for any suggestion and questions. Here's my email address. If someone want to connect with me, I would be happy to collaborate and see how we can move ahead. Thank you.
Thank you. Maybe we can ask for one quick question you will have. Okay. If not, let's thank all the speakers one more time. Okay, now we conclude our session, and if you have any questions, just send an email or any suggestions during the break. Otherwise, let's see you in winter or the next year of our meeting. Thank you.
Thank you. Thank you, everyone.
there for now, it doesn't matter. Okay, slowly starting back after lunch. I don't know how many people will still come in, but we just slowly start. My name is Simone Tilmes from ACOM. I'm the co-chair of the Chemistry Climate Working Group. This is Rafa Fernandez, and he is the outside co-chair. You can introduce yourself.
Rafael Fernandez from the National Research Council in Argentina.
Thank you. And then we have Rebecca Buchholz as our chemistry climate liaison. And Francis Witt is our software engineer. And we'll start with some overview highlights. And after that, we have our talks. We have several talks that will be true, and then later on a discussion. So I will start with our development highlights. And the first thing that I don't have a specific slide on, but that's on the Chem7 workhorse model. As you can see here on the right, this is just, as we all know, the workhorse model is, we have the 80-kilometer mid-top model is the workhorse model for CMIP7 that will go and hopefully be the one that we're using for CMIP6 simulations. But we also developing at least majorly at the moment a also low top model, and there's a lot of work going on, and even on the same height 40-kilometer but a 32-level model that we discussed in the last working group are still desired, and we can come back to that. So in terms of the 58 and the 93 level model, we are working closely with CGD, with the atmosphere group. That's the main, obviously, developments going on in terms of tuning the model, getting it ready, getting the winds and the tuning right. And so at this point, we don't have a current version of a fully chemistry model running yet. It is in progress, and so that's why I don't have slides on this time. But the new version does currently include our new MEM5 modal aerosol scheme that we had discussed in the winter meeting. We have updated chemistry. We do have new DMS emissions, and then all the other changes that go on in the atmospheric group in physics and so on. So yeah, we're hoping to get a reasonable chemistry at one point. The other thing that we are still working on is using the current development code to also look at its 32-level model, just basically out of the box, that still runs with Chem6 physics to make sure that it is reasonable and running. And our interest is to compare the finite volume and the spectral element to really understand what the differences are. Again, this one is work in progress, so I don't have slides on that yet. The other thing I want to point out also in this talk is a more simplified chemistry. As we know, the 93 level model is quite expensive to run, and maybe having a little lighter chemistry version was desired. So we started some development here, and I have a couple slides on that from Louisa Emmons. And the other thing that is going on with mostly Mary and Francis working on the MPAS dynamical core with ChemChem. There are also some preliminary results that you have already seen during the last days, but I will just show a couple more plots on that. And yeah, and then we have the karma development as well as development on very short-lived hydrogen chemistry that I want to quickly go over. So the other thing is that we still have a lot of things we want to get into, potentially CSM3, which is currently not there. So there are various issues that are in development and in progress. HEMCO emission component, this is an improved way to describe emissions in the model that requires less processing of emissions from original scheme files. And we don't have presentations on this right now, which should be working at one point. In the future, you will get more information. We also have a new photolysis scheme that is in progress, and Doc, Francis, and others are working on that. The same as a new dust emission scheme. Marine organic aerosols are not started yet, and we'll have to see where we are going with that, how fast we can implement it. There's a new Megan code for biogenic emissions that is also not started yet really, but it's an issue, and so on. So we have some planned work also, as I said before, to with the atmospheric group, get a 32-level model grid, and I want to keep that for the discussion later, how much people are desired to have that version continued. And then the very short-lived halogen implementation. So quickly to the TS4, more simplified chemistry. And I don't know if that's, I think it's in the, no, it's here. So the model, it is about 30% cheaper. It's not a huge amount, but maybe it will help for some configurations, like if we run really long climate simulations. It's basically removing most of the complicated organic chemistry in the troposphere, but it will still have, most of the, actually almost all of the stratosphere chemistry. So the processes for the ozone hole and those things are still included, including also all the aerosols chemistry, the sulfur chemistry. Other than this version has a more simplified secondary organic aerosol chemistry, which we may actually want to still put back in if the performance would change. But what you can see here is really it reduces the amount of tracers, makes it simpler. And in the next slide here, I just show quickly some burdens of chemistry and aerosols to see that there is actually not that much difference when you run these two schemes. I could have shown a bunch of plots, but I thought that just shows that you really don't change too much the chemistry with the more simplified scheme. The only thing is that the aerosols, maybe sulfate changes a little bit more. That could be changing the cloud in some way, but if you look at the total top of the aerosol, top of the atmosphere imbalance, it really didn't make a big difference. So that's promising. We will look into this more. The other thing was, as I just said, we have now first 5 days run during the Asian summer monsoon period that uses MPAS, and Mary had already yesterday shown this plot, so I don't probably have to say much to it other than a very initial cost estimate is quite high on that. I think if I had it right, it's about 2 million core hours per year, but obviously this may not be an application to run for several years, but more for periods to look at. But definitely quite promising to see that we get new results and interesting results. So that's really great progress. And then you have probably already seen this slide too. We do have now Karma in a development version of CESM. Karma is the sectional aerosol model that can be run in it instead of the modal aerosol model. So it basically can give you a more detailed description of aerosol size distribution, and Gökhan has mentioned that. We do see somewhat a better representation for both volcanic eruptions as well as the background aerosols, but this version at this point has been tested for a specified dynamic simulation, so now we are working on more prescribed sea surface temperatures to make it also potentially soon have a fully coupled model version that could run with it. It doesn't run at the moment without chemistry, it's just implemented in the chemistry versions. And finally, this is for Rafa to explain a slide on the very short-lived halogens, and we will have more presentations on that. Oh, can you keep it up still?
So yes, after the break, we'll have a couple of talks on the implementation of short-lived halogens in CESM 2. So basically all the studies done with this tropospheric halogen chemistry, with detailed tropospheric halogen chemistry, has been done in CESM 1 and never been ported. So basically I don't want to talk about this. I'll provide a technical talk and then some interesting results, including all this chemistry induce a cooling effect on climate, and I invite you to stay after the break also. So due to time, we will leave the discussion for the end of the session, and I think we can start with our first speaker today, Ben Gobert. he will talk about some carbon monoxide studies. So.
Thanks, Rafa. Thanks for giving me the opportunity to talk here. Let me know if people online cannot hear me. I try to speak in the mic. So I'm going to talk about carbon monoxide simulations and data simulation in particular to trying to understand the role of emissions, transport, and chemistry on the CO biases that we've been seeing for very long. So the tools I'm using is CESM and CamChem, so the 32-layer CESM2 at 1 by 1 degree. And I'm doing ensemble simulations where I'm doing perturbations in the emissions in the initial conditions, but also global parameters such as nudging to spin up the ensemble, and aerosol like dust or sea salt emissions. So those would be global perturbations. So then you get a spread in meteorology, in transport, in physics, and hopefully in the concentrations of the species of interest. Here I'm assimilating MOPIT CO, daytime multispectral retrievals from the V9 versions of it, MODIS AOD, and meteorological observations. And to perform the assimilation, I'm using the data assimilation research testbed from NCAR that is community open source software for efficient data assimilation. It provides various analysis algorithms, and especially localization and inflation algorithm that helps improving the ensemble data assimilation. So I'm doing the perturbation, and especially I'm using the CAMS version 5.1, and I'm perturbing with the same noise all of the CAMS emissions, and with the same noise all the FIN 2.2 emissions. And we're doing 6-hourly simulation of 30 members, and then we're performing the assimilation of MOPIT in one case, of MODIS AOD in another case, and meteorology as a baseline. And so after the assimilation, we have updates on the emissions, so we can apply those updates back to the emission inventories. So this is for CO, so then I'm estimating separately the emissions for anthropogenic and fires. And this is for the aerosols, where I'm using only the 4 mass mixing ratios as a control. So I'm updating those 4 species using AOD, and then updating the rest of the species and their numbers in the MAM4 algorithm. And I'm updating also the emissions, and I'm using the CO to separate fires from anthropogenic in this case. So the case study is August 2015. So the spin-up is done. So I'm looking just at, so there is a spin-up of CamChem, then a spin-up of the ensemble, then a spin-up of the meteorological DA. And then on August 1st, I'm starting the MOPIT CO on top of that. So I consider the first 2 weeks of August to be the spin-up for the CODA, and that's the results for the last 2 weeks of the month of August 2015. So it's summertime, you get lots of fires in the northern hemisphere, and the fires in central equatorial Africa and the Amazon and Indonesia. This is also El Nino year. The next month will be the largest fires emissions in Indonesia over the course of the last 25 years. And you can see the hotspot of emissions over China too, that is the largest emission source from non-fire source. And so in the control runs, we usually have that underestimation of the CO in the northern hemisphere, usually in the late winter, early spring, but this is also happening in August, close to the sources, so you can see over the large underestimation of Chinese emissions. But for the fires, we are actually overestimating by quite a lot, and that's exported over large regions. So that's in the control one. So after the assimilation, then we don't have any more biases in the columns. There are only residual errors that are in the instrument noise as expected. So the comparison with independent observations, we're using NDAC tropospheric weighted VMR CO. And those are daily averages over 15 sites. And overall, we're reducing the bias and the variability, and we improve the correlation. So those improvements are seen independently. For the AOD, we have a very similar story with improvement of errors over time and of the bias and RMSE. And what's interesting is the structure of the errors are very similar, with underestimation of emissions in the northern hemisphere and an overestimations of the fires in the tropics. So those are the emissions increments I get in the end of the simulation. And you can see that the feature you see in the concentration and the AOD space are similar to what you get in the emissions. But sometimes it's different between, so for instance, over India, the aerosols emissions are increased after the assimilation, so they're underestimated, but in the CO, it's a bit more complicated. But aside from that, it's mostly very, very similar feature between CO and AOD-DA, even though they're completely independent instruments. They don't even measure the same thing. So since China is a hotspot for CO emissions, I looked at other inventories, and you can see that the CAMS is the red one at the bottom, and two other CEDS and HTAP emission inventories are other independent bottom-up estimates. And the blue line is the posterior. So overall, after assimilation, we're getting closer to other emission estimates. So it's actually in line with the other, but we have actually pretty convergence of emissions for this month. So what I did after that was to run the model with the updated emissions for both FIN and CAMS. And so here I'm contrasting the control reference run with the one with the posterior emissions. I'm calculating the errors for the MOPID climatology to the left and the MODIS AOD climatology to the right. And you can see that, so if it's in the blues, it's an improvement. And if it's in the reds, it's a degradation compared to the original emissions. And we have an assimilation in August. So you can see that for the fires in August in the region, you get an improvement around that time, and that propagates over all the southern hemisphere. But then you don't get an improvement in the beginning of the year because we don't have a signal for improving the fire emissions during that time of the year. And overall, the change in China with just largest signal is propagated towards all the Pacific, and there is an improvement over the entire northern hemisphere. And it's a very similar story for AOD, but the biomass burning aerosol emissions have a shorter lifetime, so according to the directions of the winds, you could have an improvement or a degradation. In places where you have an underestimation or an overestimations of the plume, then you would reduce the concentrations and you would have an improvement. But in the places where you actually have no plumes, if you reduce the emissions, you increase the bias, and so then there is a degradation. So those are mostly due to transport errors. So I did a 3 years run, and so I can look at aircraft observations here for mostly for CO, OH, and HO2 that were measured during this campaign. I did another simulation where I'm reducing the J01 signal D because it's the source of OH. That is the main sink of CO. So I can look at the difference impact of changing the sources of CO or changing the sink of CO. And so if you look at OH distribution, in the northern hemisphere for OH and HO2, so this is in the summer, February, October, and May, which is like the 4 different deployment of the atom. And it's flights over the Pacific and the Atlantic averaged. And so you can see that OH is pretty well reproduced in August and October, but it's overestimated in the winter and the spring as we are used to. And the changes in emissions is pretty small, and decreasing the sources of OH is reducing OH. So we have an average methane global tropospheric lifetime of almost 8 years, and it should be 9.5. So we are overestimating OH, and mostly in the winter season. But mostly what's important is that if you look at this profile, you would think that OH is pretty well modeled, but if you look at this metric, it's not the case. And if you look at HO2, you can see that there are also differences. It's not because you're modeling when you're using interactive chemistry, it's not because your OH is right that you get the total OX correct. And on the other hand, changing the photolysis is actually improving the methane lifetime and has an impact that is larger than the emissions. So if you look at CO, you can see that there is overall pretty small changes, and that it goes in the right direction in the winter and the spring, and that reducing OH in the northern hemisphere improved the CO. But in both of those cases, it remains fairly small. The decrease in the tropics is improving at the right time of the year, or it doesn't change. And for the southern hemisphere, the bias is the other way around. So reducing the tropical emissions is improving the CO as well. So to summarize, I'm using the Dart CamCam for ensemble data simulation, and I'm assimilating MOPIT and MOPIT CO and MODI CODs to estimate emissions and concentrations of CO and aerosols. And so I did an inversion to update the CAMS emissions and the FIN emissions that have biases that goes in different directions. And we were able to detect them and to correct them and to improve the simulation. And there is some consistency between the species, the CO and black carbon and primary organic matter emissions between the 2 different MOPIT and MODIS-based inversions. But overall, the sensitivity of CO in the middle of Atlantic or Pacific Ocean to biases in emissions is very small. So it means that the historical biases we were talking about on CO for since MOPIT has been launched in 1999, it's mostly due to chemistry and not to emissions. In the future, I'd like to assimilate also CRIS and Tropomi CO, and to assimilate methane observations and trying to develop a framework to improve OH to characterize the methane sink. And there are some improvements of the assimilation algorithm for bounded quantities that is available in Dart now. And performing data assimilation for more challenging aspects, which is variable of very high resolution compared to what I'm doing now, and coping with the assimilation of vegetation parameters in CLM to improve biogenic emissions. So that's what I have.
Hello. Back to you changed the photolysis of J ozone, so you decrease the O singlet D, right? Is that what, can you repeat again? That made it better overall, all your comparisons, or was it conflicting?
You don't have the same biases in the northern hemisphere and the southern hemisphere. So OH is too high in the northern hemisphere, it's better there. But on the other hand, in the southern hemisphere, then the CO increases, even though it's already overestimated. So it's worse in the southern hemisphere.
Thank you.
So next speaker is Halima Salah, that will speak about emissions, air quality, and human health impact.
Hello, everyone. Thank you for giving me the opportunity to speak at the CSM Workshop 2023. To start my presentation, titled Comparing Global Emissions of CEDS, CAMS, Eclipse, and Eclipse version 6B, and their effects on air quality and human health using CSM CAM6 Chem. To start off with the motivation and hypothesis, I'm systemically comparing the differences of emissions amongst three commonly used anthropogenic emission inventories, which is the CEDS, CAMS, and Eclipse version 6B. We will be assuming that there exist uncertainties in global anthropogenic emission inventories for trace gases and aerosols in these inventories. As you can see to the left, when looking at black carbon, for example, we find that when comparing to CEDS in blue as a baseline and CAMS in gray and Eclipse version 6B in orange, we see that it is 21% lower when compared to CEDS. We find that this large difference between CAMS and CEDS, and we will also compare the spatial and annual total variability of other species such as NO2, nitrogen dioxide, sulfur dioxide, carbon monoxide, NH3 ammonia, organic carbon, and also the non-methane VOCs. In addition, we assume that there are uncertainties among the emission inventories, ultimately could be leading to different impacts on human health. The scientific questions that we have are, what are the drivers of regional and global differences in global anthropogenic emission inventories for trace gases and aerosols among CEDS, CAMS, and Eclipse version 6B? Also, what are the regional and global air quality and human health impacts resulting from the application of different anthropogenic emission inventories? And lastly, what are the implications for air quality management and air pollution mitigation strategies attributable to the uncertainties of global anthropogenic emissions? So using CSM 2.2 and with CAM6 Chem model configurations, we ran CAM6 Chem simulations from January 1st, 2014 to January 1st, 2016. The first three cases, 1, 2, and 3, anthropogenic emission inventory are using CEDS CAMS and Eclipse version 6b. And we are using the year 2015 modeling outputs for result analysis. Case number 4, we have the anthropogenic emission inventory turned off. The CAM6 Chem resolutions for all are at the 0.9 degree lat and 1.25 longitude. The differences between case 1, 2, 3, and case 4 will be the net air quality and human health impacts for each of the anthropogenic emissions inventory. To start off, we were able to intercompare the trace global emissions. As you can see, the left with CEDS as blue, CAMS in gray, and Eclipse version 6b in orange. I would also like to note that for CAMS, the NO, it is archived, NOx is archived as NO, and we had converted to NO2 to compare for uniformity sake. And as you can see, for NO2A, for nitrogen dioxides, when comparing between CAMS, Eclipse version 6b, and CEDS, we find that they're consistent amongst the three inventories. And when we look into the black carbon, for example, in B, CAMS is significantly lower when compared to CEDS at 21%. It's 21% percentage difference lower. And when we look into Eclipse version 6b, the global annual total emissions of black carbon and NMVOCs in D are 6% higher higher than CEDS and 25% lower when compared to CEDS. Continuing, looking into ammonia in E, sulfur dioxide in F, and G, OC, or organic carbons. The global annual total emissions of sulfur dioxide and OC from CAMS for the year 2015 were 8% and also 19% higher for CAMS. And when comparing with to CEDS at being lower than CEDS for CAMS being 17% lower, and we found large discrepancies between Eclipse version 6b, with for CEDS for SO2 being lower than percentage difference being lower by 20% when compared to CEDS. And when we look at the global annual mean surface concentrations for PM2.5 and ozone in 2015 for CAMS, CEDS, CAMS, and Eclipse version 6b, these are the global annual total, not just the anthropogenic. So they're not regional specific. It's just the global overview. And similarly for ozone, we hope to plot a difference between CAMS, Eclipse version 6b to CEDS as the baseline. And for the impacts on human health, when we look into the induced premature deaths, we're looking into the non-accidental deaths from lower respiratory infections, the LRIs, and non-communicable diseases, NCDs, linked to long-term exposure to PM2.5. We see that, for example, in CEDS, the PM2.5 induced premature deaths, we find that it is 3.7 million deaths per year. For CAMS, we find that it is 4.14 million deaths per year. And for Eclipse version 6B at 3.17 million deaths per year. A lot of the concentration being in the Asian continent. And when looking at ozone, where the ozone-induced premature deaths are the chronic obstructive pulmonary disease, COPD, linked to long-term exposure to ozone. And these are just the anthropogenic emissions for both my plots. And we find that for CEDS at 695,000 deaths per year and 670,000 deaths per year for CAMS, and for Eclipse version 6B, we find that it is 422,000 deaths per year. In total, for the combined annual PM2.5 and ozone premature deaths for 2015 for CEDS, CAMS, and Eclipse version 6B, the total is 4.41, 4.82, and 3.59 million deaths per year, respectively. Now, we are using the regional categorization of 11 regions, being China, India, ROA, which is rest of Asia, and then we have USA, United States, Western Europe, and we have Latin America, and name North Africa and Middle East, and then we have Eastern and Central Europe, SSA, Sub-Saharan Africa, and up top here, zoomed into Canada and rest of the world. We find that when compared as similarly, green being CEDS, CAMS being blue, and Eclipse version 6B being yellow. We use CEDS as a baseline to calculate the percentage differences. And we find that for CAMS, when compared to CEDS, the global annual PM2.5 ozone-induced premature deaths to be 25% higher when compared to CEDS in the China region. And then when looking at Eclipse version 6B, when compared to CEDS, we find that is 25% lower. And however, yeah, we see that Eclipse version 6B is 25% lower. And then when we look at the India region being Eclipse version 6B being 16% lower, and CAMS just being 3% higher. So to summarize and to conclude, we find that the global annual total emissions for NO2, nitrogen dioxide, and CO, carbon monoxide, are consistent amongst the three inventories. However, the global annual total emissions for OC and SO2 from CAMS in 2015 are 19% and 8% higher, with black carbon and NH3, or the ammonia, being 21% and 17% lower than that from CEDS, respectively. For Eclipse version 6B, when compared to CEDS, the global annual total emissions of the NMVOCs and SO2 in 2015 were 25% and 20% combined global annual PM2.5 and ozone-induced premature deaths for the year 2015 for CEDS, CAMS, and Eclipse version 6B are 4.4, 4.82, and 3.59 million deaths per year, respectively, for the 3 inventories. And the drivers of the discrepancies were mainly caused by the regional differences over Asia, particularly from China and India. And when compared with CEDS, the global annual PM2.5 and ozone-induced premature deaths from CAMS over China in 2015 were 25% higher. However, Eclipse version 6B showed 25% lower relative to that of CEDS. To acknowledge, I'd like to thank my advisor, Dr. Yoshun Huang at Wayne State, Dr. Simone Tilms here at NCAR, and also Dr. Wenfu Tang for their help and guidance. I'd like to thank NCAR and the NSF. Thank you. Yeah, if you have any questions.
Of the premature deaths in this does the World Health Organization have deaths, premature deaths are due to
So the health impact calculation is using, for example, the hazard ratio, which is attributed to the global exposure mortality model, which is GEM. And this was done based on 16 a cohort studies around 16 countries. So based on that equation, we were able to calculate the deaths, the premature deaths.
So our next talk from Hui Wang is about high latitude isoprene emissions and different sensitivities with temperature.
Oh, can you guys hear me?
Yes, we can hear you and see your presentation.
Okay, sounds good. Thank you. So, hi everyone. My name is Hui. I'm a first-year PhD student from University of California, Irvine, and I work with Professor Alex Gonser. And it's my honor to have a chance to present my work here. And at first, I would like to acknowledge my co-authors from UCI and from Europe. I really appreciate their contribution to this work. So the title of my talk today is Differences in High Temperature Sensitivity Between Herbaceous and Woody Plants Affect High Latitude isoprene Emissions as Temperatures Rise. Okay. First, let me give you guys some background. So bioorganic VOC is very important and could be affected by the global warming and climate change. So here we can see when the climate becomes warmer, it will increase bioorganic VOC and it will affect the formation of ozone, lifetime of methane, and also aerosol and cloud formation. And all these chemical and physical changes could have feedbacks back to the climate system. So the most widely used for estimating bioorganic VOC is a Megan model developed by my advisor. So the figures here shows the spatial distribution of isoprene in July estimated by Megan. And according to the Megan estimation, the global bioorganic VOC is about 1,000 TG, and the isoprene accounts for half of it. And also the amount of isoprene is also 3 times of the anthropogenic non-methane VOCs. In that case, it's very important for us to quantify the isoprene emission. But at the same time, there's a rapid changes of climate in the Arctic. We can see from here, the air temperature, also permafrost temperature in the Arctic is dramatically increasing in recent decades. And also there's more precipitation and water supply. So in that case, the tundra and high latitude ecosystems is becoming greener. And more vegetation means there's more biogenic VOC emissions. At the same time, some recent whole ecosystem measurements shows that the isoprene emitters in the Arctic are more sensitive to the temperature than we think in the model. So here, all these figures shows like the relationship between the isoprene emission isoprene emission response to the temperature change. So here we take this figure as an example. The black line here is the current mega model, and the red line here is the temperature response curve derived from the ID covariance flux measurements. We can see the red line could be more sensitive to the temperature and can increase dramatically when the temperature get increased. So to figure out like the impact of global warming and climate change on the Arctic biogenic VOC and aerosol, we have this campaign called Baryons, Biogenic Emissions and Aerosol Response on the North Slope. And then we had our first campaign last summer at Alaska, in Alaska and on the North Slope. And for this campaign, we check like the temperature response of the local vegetations, and we use the gas exchange chamber system from our lab. So here's a picture shows the system. So what we do is like we fix the light and we put the leaves of all the branches of the local vegetation species into the chamber system and change the temperature slowly. At the same time, we collect the VOC samples while ramping up the temperature. And then we can see the VOC response to the temperature from our experiments. And here are some pictures shows the local vegetations we sampled at the North Slope. And according to our measurements, we found like the willows and sedges are the main isoprene emitters on the tundra. So here's a picture of the willow, and here's a picture of the sedge, and here's a comparison of the isoprene flux coming from different vegetations. We can see these two species are dominant isoprene emitters. And also we checked the temperature response of willows. We found the temperature response of willows are similar with the current mega model. We can see the green line here is the current mega model, and the pink line here is the temperature response curve we fitted from our observations. We can find two lines has a similar shape but different optimal temperature. But however, we also found the temperature history of the growing temperature could change the emission capacity of willows exponentially. So the figure here shows how the exponential relationship between the past-10-day temperature and the emission factor of Salix. So Salix is also willow. So the emission factor is defined as the isoprene emissions at the temperature of 30 Celsius and a ppfd of 1,000 microgram per meter square per second, which could be used to represent the emission capacity of plants. And we found that the willows in the Arctic could change their emission capacity dramatically with the growing temperature, which is more pronounced than the current mega model. From this figure, we can see when the temperature gets higher, its emission capacity will just increase. And here's the pink line here is the current mega model. We can see the change is more dramatic than we expected in the model. And so this is for the willow, but for the sedge, the story is different. So we use the Q10 to represent the temperature sensitivity. So the equation of Q10 is given here. So which means like 10-degree change could introduce how much change of isoprene. And we can see the Q10 values of the willows is very close to the current mega model. So the red line here represents the current mega model. But the Q10 of sedge is much higher than the willows as well as the current model. If we go back to a temperature response curve, we can see the green line here is the current mega model, and the blue line here is the Arctic willows, and the orange line here is the sedge. So the sedge can increase their isoprene emission more dramatically than the current model and and also the local willows. So we also compared our temperature response curves of sedges and willows with previous study. And we confirmed that the pronounced temperature response curve isoprene about in the Arctic ecosystems is coming from the sedges. And we can see here these lines these temperature curves derived from previous whole ecosystem measurements is consistent with our sedge measurements. But for the willow dominant ecosystems, the temperature response curve like this one, the blue dashed line is more close to the mega model and also our willow measurements. And so we also integrate our findings from this study into the mega model, and we run the model for 3 high latitude flux measurement sites. And we can see from here, the black line is the observations, and the blue line is the current mega model. And the pink line here is the updated model from this study. And we can see the updated model has a better performance than the previous model, and it can capture the isoprene variability better for the high latitude regions. In addition, we also update the temperature response curves from this study in the Megan with the CESM model for the Arctic ecosystems. We found that the isoprene emission from the high latitude increased by 31% according to the simulation of CESM model. And also we found the updated model can simulate the nearly double increased trend of isoprene emission in the Arctic. We can see from here, from 1960 to 2009, and so the trend could be increased by 91% from this pink updated model compared to the default Megan model. So in that case, if with the warming trend of Arctic, these mechanisms could play a key role in local chemistry. So the heat, so we can see the warming in the Arctic could increase isoprene emission by different pathways. So for the short-term intense heat waves, it will increase the isoprene from sedges dramatically. But for the long-term, like the warming environment, will increase the salix or willows emission capacity, then increase isoprene emission in the Arctic. Now, the increased isoprene will also affect the methane lifetime and ozone formation and aerosol formation. And all these change will also have a feedback back to the warming events. So the conclusion for this study is like, we use our gas change chamber experiments confirm the strong isoprene temperature response curve report for the Arctic ecosystem reported from the Arctic whole ecosystem level flux measurements. And the isoprene emission model could simulate flux observations better in 3 high latitude sites by integrating findings from this study. We also found these strong temperature response curves cause 31% increased isoprene emission for the high latitude in CESM model. And we also found the current model underestimates the long-term trend of isoprene emission during 1960 to 2009 in the high latitude by 91%. So far we're talking about the high latitude, about like the Arctic regions, but actually this it's kind of like a global phenomenon because we also tested some like local, like the temperate sedges. For example, we tested the California field sedge and the European green sedge. So we can focus on these figures. The x-axis is the leaf temperature, the y-axis is isoprene, normalized isoprene emission. We can see the pink line here is the normal isoprene, normal Megan model. And the circle here represents the lawful statement. It's kind of like a tree species. And each temperature response is very close to the current Megan model, which makes sense because current Megan model is based on the tree, many tree measurements like oak trees. But if we take a look at the sedge temperature response, we can see it's much more stronger than the current Megan model, which means we may underestimate the isoprene emission from the herbaceous like species like sedge. And also we may have more like isoprene emission in the future globally with this high temperature response of sedges. That's all my talk, and thank you so much. I can take any questions from here. Thank you.
We have some time for questions.
Yeah, thank you very much. Very interesting. So you said 30% underestimation in the Arctic. That could mean we do form, isoprene will form aerosols that can impact the climate, as you nicely described. You have not, obviously this was for present day. So what do you expect in the future when we get more warming and thawing of the, the Arctic? Will this have even be a much larger impact than what you can estimate based on present day?
Yes, I agree. Like, because like the Arctic, we all know like the Arctic is kind of like have a higher warming trend than the other regions. So definitely in the future there will be more isoprene emission. But here I just run the model for like the historical record. I didn't run for the future. But if we run for the future with different scenario and different like emission, like the different like SSP scenarios, we will see the different like the changing trend. And also we should so here we just consider the change of temperature, but also with the higher temperature, more precipitation, there will be more vegetation in the Arctic. So in that case, the volcanic VOC emission will be much more higher than we expected from the temperature increase.
Yeah, exactly. That was my question. So it could have a much larger effect than 30% for sure. Yeah.
Yeah.
Thanks. Other questions?
I think I saw one question from the chat box. Is asking like, in one plot, the sedge isoprene emission seems to grow exponentially with temperature with no maximum optimal temperature, where other plants shows peaks and decline with increased temperature. Can you explain that? Yes, I think it's this figure. I think it is because when we do these measurements, we only stop at 35 Celsius, but for the willows, we stop at around 45. The thing is like, at that time, we didn't know like the sedge could be the key for the story. So to compensate this part, when we came back, we also measured the other like sedge species here. And we can see from these figures, for some sedge species, for example, the California field sedge, when the temperature gets really high, like 45 Celsius, it still can, so it's kind of like we kind of like reach its optimal temperature, maybe for one is around like 45. So, but for some species it will be around 42. And so it will have like optimal temperature, but yeah, but for the measurements we did for the Arctic, we didn't reach that point. But also like Arctic, we never expect it could be like 40 Celsius. So that's why we didn't go that way, that far.
Okay, thank you very much, Hui. So
yeah,
we'll keep
welcome.
on with the next talk. Noribeth Mariscal will talk about the evaluation of ozone precursors during the Michigan-Ontario campaign using Musica.
Good afternoon, everyone. My name is Noribeth Mariscal. Thank you for the opportunity to present my talk, where I'm evaluating model-simulated ozone and its precursors using the multi-scale infrastructure for chemistry and aerosols during the Moose experiment in Michigan. So ozone in Southeast Michigan. So ozone is a secondary air pollutant that continues to exceed national ambient air quality standards of 70 parts per billion or less, established by the National Ambient Air Quality Standards in Southeast Michigan. Many factors are responsible for these increases in the region, in particular with Southeast Michigan, which is located in this bottom part here, from power plant emissions, for example, in Monroe, Michigan. We have industrial and transportation emissions in Detroit, which is the largest urban center in the region. And then we have power plant emissions in East China, Michigan, as well as potential impacts from Sarnia's Chemical Valley in Ontario, Canada. Although there have been previous studies that have focused on studying, ozone chemistry in the state, more detailed and innovative measurements and modeling studies are needed in this particular region for understanding the production and loss of ozone in Southeast Michigan. So I'd just like to highlight some, kind of
concerning news articles that have been presented in the area. So Detroit has been dubbed the Michigan's most toxic zip code, as well as been named the most challenging place to live in the U.S. with asthma. Recently, the Canadian wildfires have also impacted, the air quality in Detroit, making it for an even, rougher situation for local residents. So some of the objectives for this project are essentially to investigate the sensitivity of model simulated ozone and precursors using model horizontal grid resolution through the creation of a 7-kilometer grid over the state of Michigan. Secondly, I'd like to quantify the drivers of ozone non-attainment using the optimal model grid through various emission sensitivity experiments that, so in this presentation, I'll be focusing more on the first objective and kind of introducing what I'm doing for the second objective. So I just also would like to, give a shout out to the Michigan-Ontario Ozone Source Experiment, otherwise known as MOOSE, which was led by Michigan EAGLE, which is the Department of Environment, Great Lakes, and Energy. This campaign was a collaboration amongst various university partners, as well as federal agencies and collaborators in Canada. It sought to define potential attainment strategies in Southeast Michigan and better understand what's contributing to excess ozone. The campaign was held in 2 phases in the summers of 2021 and 2022 for about 6 weeks in May and June, and it included, various high-resolution measurements via, aircraft, mobile labs, and stationary sites. So the 2 sites that are kind of presented here are 2 of the sites where our research group spent a lot of the time taking measurements of ozone and NOx, and to the right here is myself, my advisor, and other collaborators from our university and Brown. So to begin, I'm sure many of you know Musica is the multi-scale infrastructure for chemistry and aerosols. It's the first implementation of the Musica framework as a configuration of the community atmosphere model within CSM. It uses a spectral element dynamical core, which is an unstructured grid mesh based on this cubed sphere here. The default resolution for Musica is currently this 14-kilometer grid over the continental United States with 1 degree over the rest of the globe, with 32 vertical layers with a model top of approximately 40 kilometers. So the model configuration that I've listed down below is going to be consistent for the model simulations that I'm presenting here, as well as future simulations. The models that I've run are from April to August of 2021, using April as a spin-up, meteorological reanalysis fields from MERA2, the Mozart TS2 chemical mechanism, and then emissions data sets from CAMS, QFED, and biogenic emissions from Megan version 2.1. So for the grid that I created over Michigan, in order to better understand local impacts within the region, I defined the 7-kilometer grid over the state of Michigan, which then transitions into a 14-kilometer grid over the rest of EPA Region 5, and then 1 degree over the rest of the globe using the Community Mesh Generation Toolkit. Each of the resolutions, so going from the 7 to the 14 to the 1 degree resolutions, has a smooth transition, sort of like a halo between the resolutions to mitigate for potential errors. Both the default CONUS grid are presented, and the NE30 by 16 Michigan grid are presented at the bottom here. And we're both run with identical chemistry, physics, and dynamic settings. So after doing some initial runs, I found that the CONUS grid takes about 28,000 core hours per simulated month versus 18,000 core hours per simulated month in the region of Michigan, which can be potentially relevant to more local scale, more focused projects, especially when you're incorporating the TS2 chemical mechanism, which can be significantly more expensive to run than the TS1 mechanism, which and an initial comparison with stationary, with ground observations from stationary sites in Southeast Michigan. So I have the Allen Park site, which is a more suburban area, kind of northwest or southwest of Detroit, and then the Detroit East 7 Mile site, which is a combination of urban and suburban infrastructure. Initial looks at ozone, some variation of NO because as we probably all know, stationary measurements are sometimes hard to come by that are co-located with each other, as well as temperature here. So with this initial look, I have the black X's which represent observations, and then the red line represents the default resolution, and then the blue line represents the 7-kilometer resolution over Michigan. So initial looks with ozone, the any 30 by 16 grid that I created over Michigan is simulating better in terms of the afternoon peak ozone times at both sites, where underestimation with both of the models are with both of the resolutions are underestimated compared to observations in the nighttime to early morning times. We're looking at the variations of NO, so NOY for Allen Park, and then NO2 for the Detroit East 7 Mile site. In Allen Park, both of the simulations are highly overestimated compared to observations, and this overestimation kind of carries through when NO2 is at its highest at the East 7 Mile site here. Temperature, so when it came to the meteorological species, or the meteorological parameters that I've listed here, I did not nudge within the latitude, longitude grid box for the 7-kilometer and the CONUS run, because for the 7-kilometer run, the MERA2 is finer resolution. So kind of with this initial look, the temperature did perform significantly better compared to the not nudged CONUS run here for these two sites here. And then I also did a brief comparison with the Aerodyne mobile lab measurements. So this is a pretty hefty time series here for ozone, NOx, and temperature. But what I kind of wanted to make note is when comparing the overall mean biases of each of the data sets for late May to end of June of 2021, the overall mean bias for the NE 30 by 16 run was significantly better than the default CONUS grid here. And this is just the AML track to the right here. So I wanted to emphasize that although this performance for the NE 30 by 16 grid is looking better here, the AML did move a lot during this time from more suburban to kind of chasing these like hotter like ozone hotspots, as well as point sources in the region. So after doing I zoomed in slightly for ozone and NOx here, and I wanted to note that for both ozone and NOx, this improvement does for the NE 30 by 16 grid does show pretty good performance in this case. But when kind of looking, for example, at NOx in these yellow areas here, we can tell that the NE 30 by 16 grid is not capturing some of these higher NOx spikes that we would want it to capture essentially. So because of that, one of the approaches that we've kind of been exploring is doing a couple emission sensitivity studies. So right here I present anthropogenic emissions for nitric oxide from CAMS version 5.1. I've calculated the percent of total NO emissions per sector in Southeast Michigan compared to the rest of the state of Michigan. So it was found that 30% of total NO emissions are within the Southeast Michigan region compared to the whole state. Residential made up almost 50%, and then the transportation, both on and off-road, made about 45% of total emissions in the state of Michigan. So one of the ways that we've been exploring how we can optimize this NE 30 by 16 grid is through the implementation of a diurnal cycle. So these diurnal cycles can be important for evaluating model uncertainties and can also cause large differences, especially in areas with large anthropogenic emissions, which is one of the reasons why we're testing it out here. Diurnal variations are currently, for anthropogenic emissions, are currently not considered in CSM2. And like I said, they can have heavy influences in anthropogenic areas. So we're currently working on regridding and setting up the CAMS version 5.1 emission data sets, as well as adding diurnal information files. To complete Musica version 0 runs at the default and 7-kilometer grid over Michigan. And then we'll eventually, evaluate these runs with Moose Phase 1 to see if there are any significant improvements. Additionally to this, we're also working on running a suite of sensitivity experiments to quantify, contributions from the various sectors as well as long-range transport in for ozone in Michigan through, some of these, I guess, cases that we're hoping to run. So turning off, transportation emissions, power generation, all other sectors, as well as turning off all emissions to kind of study the meteorology in the region. And then, hopefully, kind of similarly to how Halima presented, we hope to combine, Musica version 0 with an exposure model to potentially study the impacts of ozone on human health at a more local scale. So, so I'd like to acknowledge, NSF, the National Center for Atmospheric Research, and then the Michigan Space Grant Consortium for funding support, as well as, Cheyenne and Wayne State's Grid High Performance Computing. And then I'd like to thank all of my collaborators, my advisor, Dr. Huang, Luisa, Dusang, who's been a lot of help for, throughout the diurnal cycle and Musica applications, Andy and Dr. Chai, as well as like the Moose Science teams. So, yeah. Thank you. Don't know. Yeah, and I'll take any questions if anyone has any.
Ari, nice talk. You showed, I was curious if you've done more evaluation with meteorology parameters. You showed a couple of moose-related sites with temperature, but have you looked at precipitation or other factors in the region?
I have not yet, so it's mainly been looking at temperature. I did have some wind data, but I haven't looked at it too in depth, so I didn't want to include it here for the sake of not knowing how to explain it quite yet. So.
Well, and I would encourage you to look at some meteorology data sets, like the stage 4 NCEP data for precipitation. I just, there's one point where temperature dropped off in the observations, and I was curious in that because it's not happening in the model.
Yeah, definitely. I'll take a closer look at those days, especially because since the AML was moving, sometimes they were, on the coast of the lakes, as well as other times they were more kind of towards the center of the mitten, per se.
Yeah, so that's another interesting factor to take into account.
Yeah, so it's something that we're currently exploring. So I know that there's a bunch of like NOAA data along the coast, so I'm hoping that I can pull some of that and to take a closer look at it. Thank you.
Talk. Have you? I haven't used Musica, never, but I've used WorkCam, and we also found for other air quality studies this overestimation of NOx during the night, and we changed the temperature profile, and it didn't work. So, are you thinking about the position, planetary boundary layer, evolution during the night? I don't know, other options to evaluate on that?
So I mean, so far it's been kind of taking it. So it's very like preliminary results so far. So we haven't explored too much into like planetary boundary layers, but it was more, seeing if the diurnal application of that diurnal cycle might help it out a little bit. But definitely, I would like to consider that in the future for future runs for sure. Yeah, I don't know if that answers your question.
Thank you.
Thank you.
Okay, so we go to the final talk before the break. The song is going to present results on regionally refined versus global uniform comparisons during the Chorus campaign.
Yeah, hi everyone, my name is Do-Sung Jo. I'm a project scientist at NCAR ACOM. Today I'd like to talk about comparison of urban air quality simulations during urban airfield campaign by regionally refined versus global uniform grids with Musica version 0. Since Musica was already explained in Norris, we'll give a brief recap here and move on. So Musica is multi-scale infrastructure for chemistry and aerosols, which was released in latest CSM version 2.2. And each chemical mechanism is based on ChemChem, as you saw already, with spectral dichlor and regional refinement techniques. And Musica provides two predefined grids, such as Kronos and Arctic grids, but as in the previous talk, actually we can create any custom grid for any region of interest, up to 7 kilometer resolution at this moment. So thanks to this flexibility of creating new grids, I was actually able to create 4 different grids. So 2 global grids and 2 regional refinement grids with 14 kilometer and 7 kilometer resolutions, especially over South Korea. So now we have 4 different grids in a single modeling framework, Musica version 0. So it means that we have same dichlor, physics scheme, and chemical mechanism. So with just different grid resolutions, our question was how and how much will the results change if the resolution of the global chemistry models gets better. So in this case, for CSM side, from ChemChem to Musica version 0. So let's look at this schematic diagram here. So this is for NO concentration simulated by 2 different grids. So on the left, it shows urban air quality simulation by regional refinement grid. And we can resolve this urban center and urban downwind regions like this. But with global uniform grid, all of these values are artificially mixed and we have just single value. So this change in NO concentration can affect gas phase chemistry and aerosol formation and other chemical processes. And let's assume we have surface observation site. Then we can also expect that model evaluation statistics can also be substantially changed. So our goal of this study was to quantify the effect of grid resolution on air quality simulation, especially over urban areas. So we set up model cases with 4 different grids, as I said earlier, from 7 to 100 kilometers resolutions, with 2 different anthropogenic emission cases. As Nori already said, our default model has monthly anthropogenic emissions, but we also applied this diurnal cycle to these monthly anthropogenic emissions so that we can compare these 2 simulations and see the effect of diurnal cycle along with these 4 different grids. Our target period was Course-EQ campaign, which was conducted in 2016. So you can see here the flight tracks in yellow color over South Korea. So it provides a number of aircraft observations, so we are able to evaluate the model against these aircraft field measurements. I'll show you some evaluation results later in this presentation. But for now, let me just explain some model results. So first, here these 4 figures are showing Musica version 0 result for black carbon concentrations at the surface. This is May-June average result in 2016. And 2 from global grids and the other 2 from regional refinement grids. And as expected, regional refinement grids can capture these fine-scale structures of cities in South Korea. And here's another plot, actually. So this plot is based on any 30 by 16 result, but we regraded the model result to this any 30 grid. So if you compare this any 30 grid, original 30 grid result and this one, then for this black carbon case, there's no significant differences between these 2 plots. This is because black carbon is chemically inert, so there's not much nonlinear chemistry. But this is not the case for ozone. So this is the same plot, but for ozone. So again, I'm showing 4 different grid results here on the left side. And again, as expected, the fine-scale structure was well simulated in these regional refinement simulations with much lower ozone mixing ratios, especially over Seoul metropolitan area due to high NOx in regional refinement runs. And again, here's another plot showing any 30 by 16 result, but regraded to any 30. And now we can see some differences. So for example, here the yellow color in this plot disappeared in this any 30 simulation. So there's certainly some nonlinear effect just caused by grid resolution, which cannot be simply reproduced by regrading. And previously I showed just monthly mean averages, but let's look at the diurnal cycle of different air pollutants. So here first let me explain these four figures. So these are for diurnal cycle of different air pollutants with different lines showing different model grid resolutions, with orange line again showing any 30 by 16 result but regraded to any 30. And here we have two different line styles. So one with monthly plus diurnal cycle of emission, the other with just constant monthly emissions. So we can see here for NO emission flux in Seoul, we can see the constant emission flux from this dotted line. So first, what you can see here is regional refinement simulations. So any 30 by 8 and any 30 by 16. Resolution models show higher NO emission flux because they can resolve urban area. And resulting NO and NO2 mixing ratios are higher in regional refinement runs. It leads to lower ozone in regional refinement runs due to NOx titration. If you compare these values, then for daytime ozone, there's about 40 ppb differences between grids. And for nighttime ozone, there's about factor of 4 differences just by changing the grid. And there's also additional 10 ppb changes if you compare solid and dotted lines. This is due to diurnal cycle of emissions. We also compared other chemical species such as OH, HNO3, NO3, and N2O5 here. Again, we can see a lot of differences caused by grid resolution in Seoul. And for example, for OH, we can see here the lower OH in high resolution grids due to higher OH reactivity associated with higher VOC concentrations. And also for NO3, we have lower NO3 in high resolution grids due to lower ozone and higher NO. We further calculated other things. So here is oxidation pathways of VOCs on the right panel. So here again, this is about diurnal plot. So x-axis is an hour, but y-axis shows the fraction of monoterpenes reacting with OH in red, ozone in yellow, and NO3 in blue. And these three are from, the first one is NE30 coarse grid model resolution. Second one is the highest resolution, 7 kilometer. And the third one is again high resolution, but without diurnal cycle of emissions. And if you look at the values around midnight, then we can see that 90% of monoterpenes are reacting with NO3 in this NE30 grid resolution. But this 90% is decreased to 60% if you use high resolution model. And there's additional 20% change due to diurnal cycle of emissions. So it means that by changing grid resolution, we have different oxidation pathways of VOCs, so it can affect secondary organic aerosol formation, organic nitrates, and further nitrogen cycle can be simulated differently. So now let me show you some evaluation results against aircraft measurement. First, different lines again showing different model grid resolutions, with box whisker plot showing observation here. And you can also see some different line styles here, but I would like to just focus on different colors today. So just focusing on grid resolution effect. First, on the left side is an evaluation for ozone and NO and NO2 here. And each species, we have two plots. So one for all flight track case, the other one for Seoul metropolitan area, which is a heavily polluted region. First, if you look at the NO and NO2, then you can see here the red and purple lines, so regional refinement runs, will reproduce the observed NO and NO2 concentrations during this aircraft field campaign. But if you look at ozone, then actually ozone is better reproduced by coarse grid. So it means that high resolution is not always better at this moment. So there should be some possible compensating errors in coarse grid simulation. So we need more investigation, such as physics scheme or chemical mechanism. Here's another evaluation for OH, benzene, and isoprene. So one thing I'd like to mention here is if you look at the values below 2 kilometers altitude, then we can see there are some significant differences caused by grid resolution. But above 2 kilometers altitude, then they are quite similar. So for air quality studies within boundary layer, high resolution model is really important, but for pre-troposphere or above, maybe coarse grid resolution is still valid. And another thing we can notice here, and also in previous slides, is that two regional refinement simulations, so red and purple colors, were actually always showing similar values for this application. So for computational cost, we think any 30 by 8 resolution may be enough for air quality simulation in South Korea. So let me summarize. Musica is the new model with great flexibility of making new grids. So I was able to create 4 different grids within a single modeling framework. So I could quantify effect of grid resolution on urban air quality simulation, and grid resolution really matters for urban air quality simulation. And if you're interested, you can also visit this website for tutorials and pre and post-processing tools at this Musica Wiki website. And actually, this paper was accepted a couple of days ago, so I think it will be available in the next few weeks, so please stay tuned if you want to more details. So thank you for listening. I'm happy to take any questions.
So you showed comparisons with evaluations with looking just at the Seoul metropolitan area and then all of the region. Are you able to do any evaluation for the coastal cities as an alternative to a highly polluted spot?
Oh, that's a good question, but I haven't done any comparison for coastal cities. But one thing I noticed from two-dimensional map was again related to planetary boundary layer thing. So I found a planetary boundary layer were very different for this coastal region. So it may be important for coastal region, but I actually didn't evaluate the model against coastal region.
And then I was kind of going to go there with my next question, is going back to the meteorology. Early on, you showed satellite pictures of the flight tracks, and you could see that the coastal cities have clouds off the coast. And so again, how well are the model simulations doing on the meteorology part of the equation?
So I only compared temperature and wind speed and relative humidity to this aircraft measurement, and models well simulate all 4 grids actually simulated these meteorological conditions very well. But I also did some comparison against some surface observations, but it depends on the region. And one thing I found was there's a mountain area, you can hardly see here, but there's a mountain area in South Korea around this eastern part, and there's some meteorological field observation sites, and high resolution is actually better than coarse grid because it can resolve some mountain terrains.
Yeah, it'd just be interesting to see the things like PBL height and again, like clouds, because that's going to affect the photolysis rates, right? So it might have an impact on your ozone results. Anyway,
Yeah,
just some
yeah.
thoughts.
Yeah.
Yeah, thanks.
Thanks.
Thanks. Good talk. Maybe you mentioned, but what is the reason for the nighttime oxidation shift for different grid resolutions?
Oh, yeah. That's a good question. The main reason is this one? 3 panels on right. Ah, this one? Ah, yeah, for this one. I'm sorry. So this is for the initial oxidation of monoterpenes, and monoterpenes are mainly react with ozone, NO3, and OH. So that's why I created this one, and yeah, this was caused by different OH and NO3, as you can see here. And if you're asking about chemistry, then there is some, yeah, for NO3, yeah, I think I mentioned here that other chemical concentrations are very different. So in resin refinement simulations, we have lower ozone, and ozone is actually very important for NO3 loss. And maybe the other way, lower ozone. Yeah, I'm somewhat confused, but anyway, lower ozone and higher NO, both are for lower NO3 in the model. So, but coarse grid resolution shows higher ozone and lower NO, so that is not good for making NO3 in the model.
I guess a quick before the break. So you can show nicely, see nicely for the OH as soon as you go to half degree, 56 kilometer. Basically, you do get a bit of a change that may be the biggest change compared when you go further even to other resolutions. So when you look at that globally, have you by chance looked at it, how much it actually matters? Because you said that in the upper troposphere, you don't see that much changes with the resolution, but does it matter for OH globally or not so much?
Yeah, I had a chance to look at it, and it actually didn't matter much. I didn't look at OH actually, but I looked at CO, background CO, and I think that is related to OH. So background CO concentrations were very similar across all 4 grids globally. So I think in that case, OH is also similar.
Okay, thank you. Okay.
Yeah. So we can thanks all presenters one more time. And we have a right on time, so we have a 30 minutes break and start here at
Okay, everybody, let's start up again after the break. I know it's hard. Wednesday afternoon, I guess, already. So last session of this meeting. And while people come in, our next speaker, the first speaker after the break, is Rafa Fernandez, and he will talk about the short-lived halogen chemistry in CESM2.
Let me put the clock. So thank you very much. I'm really happy to be here in the CESM workshop in present for the first time. So I would like to thank to all my colleagues in Madrid, here in the US, and also some students in Argentina that have helped me with the development of all of this. And I will focus mostly on a talk for people not really familiarized with this tropospheric coloring halogen chemistry in CamChem, and what we've done to get all this chemistry ready in CESM2 for make it available for many users. So I will first talk about some similarities and differences between chlorine, bromine, and iodine, burdens, distributions, sources, sinks, and all of I can get like in a simple way. I will not present impacts on oxidants or impacts in the troposphere, but mostly the distributions of these species. I will later present some sensitivity results, changing some configurations in CESM2 that I found. And I will let Alfonso, who is presenting the talk after me, to provide some details on the impact of this chemistry in the atmosphere. So I will basically consider 4 different processes or 4 different types of species of halogen species or considering. So first, the long-lived species, which are basically inert in the troposphere, and they are of interest in the stratosphere, but we need to be sure that's also remain working well. So then all the short-lived halogens or very short-lived halocarbons that they have a shorter lifetime, so they release the chlorine, bromine, and iodine atoms in the troposphere, and they start to interact with other oxidants. The release of these species is really important because these inorganic halogens that are being released in the free troposphere can be washed out depending on the partitioning. And also because in the marine boundary layer and in the lower troposphere, they can also participate in these very efficient recycling processes, which are additional sources. So in many of these plots, you will see vertical profiles for the tropics on the left, for the mid-latitudes on the right, and the solid line is CESM1, and the dashed line is CESM2 results with the same chemistry, the same configuration. So basically, what we needed to do to make these 2 versions of the models to work well was first to increase the emissions of very short-lived halocarbons by 15% from the ocean. This is because the transport in CESM2, the escape of many of these species that are short-lived from the marine boundary layer to the free troposphere is slower, and then we don't get exactly the same vertical profiles, and then to improve this discrepancy over here to what we have in the model, we increase that emissions at the surface. This is the complete picture. Here on the left is CESM1, and on the right CESM2, the whole chlorine distribution from the surface up to the middle stratosphere. And we can see that the whole inorganic chlorine distribution compares really well between the 2 models. There is a slightly larger values of total chlorine in CESM2 because our stratospheric injection, product gas stratospheric injection of inorganic chlorine is a little bit higher in the new version of the model. I'm not really scared about that because with this, we are a little bit closer to the best recommendation in the last WMO report because our source gas injection is a bit, in CESM, is smaller than the recommended values, and then our product gas injection is a bit higher, so the total injection is quite well represented. And just as a final general concept, So this is the partitioning of all inorganic chlorine species. So blue and red are the reactive halogen, the reactive chlorine, Cl atoms and ClO, which are the ones that participates in all this tropospheric chemistry. And these are really minor species for chlorine. We'll see that for bromine and for iodine, these are larger, and that's why bromine and iodine has larger impacts in the troposphere. So these are results for bromine. Once again, this is CESM1 and CESM2. The distributions is more or less the same, all through from the surface to the stratosphere. We can see in the free troposphere some higher values of BRY, total inorganic bromine, in the free troposphere, mostly in the tropical and mid-latitude regions. This is related to the sea salt recycling, which is really different between the models, not because of the halogen chemistry, but because of the sea salt aerosol distributions and also the escape of these species to the free troposphere. So we can see that at the surface, the distribution of inorganic bromine depends on the distribution of the sea salt, but then in CESM1, all these hotspots were transported to the free troposphere, something that is not any longer occurring in CESM2. So we have a little bit less inorganic bromine in the free troposphere. One important point that I will get to this later in the talk is that we get 1 ppt less inorganic bromine in the top of the model. And I will get to that in the last few slides, because that's one of the things that keep us quite busy when doing all this porting. So for bromine, then you can see, once again, blue and red. These are the reactive species affecting ozone, OH, and everything else in the troposphere, which are larger, mostly when you move to the upper troposphere. So that's why bromine impacts are much larger than chlorine. And another important point here on the right, you can see these are the sources. I mean, which species is releasing chlorine atoms? This is the bromine. The bromine atom release at different heights. So in the marine boundary layer, it is really clear that 84% or almost 85% of the total bromine source arises from sea salt recycling. But once you get into the free troposphere, it's basically bromoform, the dominant species releasing bromine atoms that can reach as product gas to the stratosphere. So an additional point to consider for the particular case of bromine is that the NEU scheme used for washout of many inorganic species in the model that we use for halogens does not really work well in CESM2 for bromine. I don't know, I never really got to understand why. So we implemented a different approximation that we call the free regime approximation that we use for iodine nitrate in CESM1, and it also worked well for bromine nitrate, and that's how we get to have this total of 5 ppts of product source gas plus product gas injection in the bottle. Finally, for iodine, we get 0.7 ppt of injection. These are the two lines for CESM1 and CESM2. This is our results that we always have in the model in CESM1, and the first estimation of the contribution of iodine in the stratosphere was based on this study, so we are really happy with those distributions. And also to highlight that for the case of iodine, the blue and the red lines here, these are the reactive iodine species, are the dominant ones in the upper troposphere, and that's why they are the dominant species controlling all the tropospheric impacts of halogens. And another important point is that these 2.1 teragrams of emissions of inorganic iodine, as a difference from bromine and chlorine, most of the emissions of iodine are inorganic, and they occur from ozone depositions into the surface of the ocean. And we really have a quite constant value. In CESM1, it was 1.9, 2.0 teragrams per year, and we also are replicating those results in CESM2. And this is something computed online. This is not an offline file that we introduced to the model. So finally, to get into some of these final things that I think are more related to the dynamics or to the resolution, which have not, we never really test that much in the model. So this is a comparison between the new nudging scheme and the free-running scheme, 32 levels, 2 degrees times 2 degrees resolution. So we see that the source gas injections of chlorinated halocarbons is more or less the same. There is a small difference of up to 20 ppts at most on the inorganic chlorine injection. But once we reach the stratosphere, if we look at the difference between the total inorganic chlorine of these two simulations, it's about 200 ppts difference. And this is like a mirror with the vertical distribution of long-lived halogens. And so this is something related with some stratospheric transport or some differences in the efficiency of these distributions. And it does not affect really much the total amount of chlorine reaching the top of the model for chlorine. But when we move and do the same analysis for bromine, what we see is that the total bromine injections end up to be reduced by more than 1 ppt, and it's basically, it has a signal. This red line is halons, are the halons difference between the models. So the halons has a different distribution in the lower stratosphere, which is not compensated by the inorganic bromine that is being released for that. And that gets up to have different bromine, total bromine in the top of the model. And we need to make sure that that is solved in this version in this type of experiment. So this is comparing nudging versus free-running configurations. So we also evaluated different vertical level resolutions, maintaining everything at 2 degrees times 2.5 degrees. And luckily, those experiments worked really well. In CESM 1, they were not working really well. We need to do much tuning, but here it worked quite well. For bromine, where we see, I mean, there are minor differences, but this is about 0.2 or 0.3 ppt difference, and we are not really worried about that. And then for iodine, this difference here that you can see is because the simulation was not long enough to stabilize iodine in the stratosphere, but we get to see here at the tropopause that the values are very similar. And finally, where we do have some problems is when we change the spatial resolution. So when we go from a 2 degrees times 2 degrees into a 1 degrees times 1 degree resolution, clouds and sea salt distributions change significantly. Iodine is mostly inorganic in the free troposphere, and then washouts efficiencies change a lot depending on those fields, and we reduce the stratospheric injection by half just by changing the resolution of the model, the horizontal resolution. So for sure we can tune these type of things, but this is important for us as, I mean, we've been working with this halogen chemistry for many years, and it has taken a lot to understand and to learn how to make the model to be reproducible. But then if this will be used by people with not that much experience in this specific chemistry, we would like to have most of the configurations to have reproducible results. And that's basically my main conclusion. So we have most of the development already implemented. There are some technical issues that I would love to finish during my stay here at NCAR. And also I call for keeping using this low resolution configuration and to maintain model support on these low resolution configurations. It's much better for me to perform 10 low-resolution simulations than to perform 1 high-resolution simulation to evaluate new chemical species, new reactions, and many things. So that's something that we can discuss later at the end of the session. Thank you.
Any questions? Eva?
Hi, thank you for a very nice talk. I was wondering, have you evaluated the transport, the differences in transport, like Brewer-Dobson circulation or age of air between the different versions of the model? And is one of them more?
Actually, not. We're always looking at the chemistry and trusting many colleagues cooperating with us in all this transport. We know that everything is, I mean, there have been many things being improved in CESM 2. I don't know exactly all the details like a stratospheric dynamic can say. So, but I need to update all this chemistry into whatever the specialists in this area says or thinks that are the better representations.
But like even between the changes in the spatial distribution resolution and using the nudging as compared to free running, do you have an idea how does the transport differ between the different versions?
No,
Sorry.
not really. I don't really have, and I would love someone to show me exactly if this is an improvement or not.
Talk offline. Thanks.
We can talk about that, yeah.
Assume by nudging you mean nudging to mirror to.
Yes.
Okay. And then so I've done the nudging versus free running using Joe's model. Look at using age of error as a sort of the diagnostic to look at the transport. Even within Jill's, nudging makes a huge difference. You can have age of error of like about half a year difference at 50 hectopascal. And also resolution makes a big difference as well. So if you're running, like we run standard one, we run quarter degree resolution versus a 1 degree resolution, you see differences. So I would say it's the simplest way to just sort of I think you guys starting to have the age of error, that will be the easiest diagnostic to look at it. But the nudging versus free running really makes it's different. Not to mention, this is within Jill's, not to mention if you're nudging to CESM. I think it's going to be very tricky for halogen simulation.
I agree with you, and my main concern was that I don't see those differences in the concentration on the short-lived halogens. I saw those differences on the long-lived halogens. And that's why I was wondering if someone ever looked at that. Because the difference in the model response in inorganic chlorine or inorganic bromine in PPTs is larger than the uncertainties that I have in the different injections of short-lived halogens.
Yeah, just a comment. Yeah, there will be differences between the free running and the SD, just like Geos gets, and it is important to look at. But also, it's when you go to different resolutions and things like that, or SD versus free running, the recycling surface area densities change, right? In the upper troposphere?
Yeah, in the lower troposphere it does, and that's why we see really different results for iodine where these washout efficiencies are very important. Yeah. But then for bromine and iodine, the differences appear only in the stratosphere. Okay. So this result recycling does have nothing to do with it.
Okay, all right. Well, I think this also lets us know that when we make our comp sets for these things, people have to follow. If they go off the rails and do something different, then they're going to have to retune the model. That's just a warning.
Yeah, that's kind of message. Thank you, Doug.
All right, let's go to the next talk. Thank you, Rafa. And we have, I do remember about the more climate forcers of the short-lived halogens and the importance of them.
Yeah, good afternoon, everyone. My name is Alfonso Say Lopez. I work at the National Research Council in Spain. And I'd like to thank the organizers for the opportunity to present the results today. And I'd like to acknowledge my co-authors in what I'm going to show, in particular, Rafa, Doug, Simon, and Jean-Francois. So I'll be talking a little bit about short-lived halogen chemistry and their interactions with short-lived climate forces, ozone, methane, and aerosols. So what are short-lived halogens? Rafa gave a nice overview about implementation in the model. So short-lived halogens are species that contain chlorine, bromine, and iodine that have lifetimes in the atmosphere less than 6 months. They are emitted mainly from the ocean. In the ocean, they're produced by biological and photochemical processes, and they have different lifetimes in the atmosphere, ranging from minutes to months. So once in the atmosphere, either by photolysis or OH oxidation, they release the very reactive halogen atom, chlorine, bromine, iodine, that reacts with ozone very fast. The rate constants are close to the collision number. They form halogen oxides, and these oxides initiate a myriad of reactions with HOX, NOx, and themselves, forming a set of reservoir species that are weakly bounded halogen oxyacids and halogen nitrates that either by photolysis or by heterogeneous recycling on sea salt or ice particles or surfaces, they release back the halogen atom, thereby establishing a very efficient photochemical cycle. And this cycle can go on about 1,000 times in the troposphere before the halogen atom is removed from the system. And every time this cycle goes on, let me complete the picture, we are destroying one ozone molecule and we are changing the budget of HOX and NOx. Therefore, my introductory conclusion is that halogen chemistry, even at parts per trillion in the atmosphere, has a profound effect on oxidizing capacity. So that obviously has an impact on short-lived climate forces. That's the focus of today's talk. And I'll say that for the last 20 years, we've been making measurements of these species all over the world, from the tropics to the polar regions. And also during that time, in parallel, we've been developing the sources and chemistry of these species into ChemChem and WACOM, trying to understand what their impact on atmospheric composition is. So today I'll show some examples of their impacts on ozone, methane, and aerosols. Starting with ozone, our current estimate is that this chemistry reduces global tropospheric ozone by a percentage between 13 and 20. And this is particularly the case over the marine environment and the polar regions. So in the polar regions, just some examples of the impact on ozone. Over the polar regions, the combination of bromine and iodine drives ozone pretty low, initiating what the so-called ozone depletion events, where ozone levels can be depleted down to detectable levels. And that's been observed both in the Arctic and the Antarctic. But halogens not only destroy ozone in pristine environments, they also do that over polluted coastal regions. In this study, we computed the ozone loss over coastal regions in different parts of the world due to halogens, and we projected that ozone loss to the end of the century. And as you can see, in certain regions of the eastern United States and Southeast Asia, the halogen-driven ozone loss increases towards the end of the century in something between 20 and sometimes 80%, depending on the RCP scenario that we use here. And this, in this piece of News and News, the journal came up with was portrayed as a natural control on ozone pollution. So we're destroying ozone in pristine environments, also over polluted coastal regions. That's the troposphere, but in the stratosphere, these reactive species are also injected to the stratosphere through convective uplift in the tropics. And along the way, they're destroying ozone, and once they are in the lower stratosphere, in the tropics, they also destroy ozone. This is an example of a very recent paper where we put together natural halogens and anthropogenic very short-lived fluorocarbons to see whether they had any role on the recently identified negative ozone loss trend in the tropics in the past 20 years. Just notice that this negative trend was associated until now to dynamical processes associated to the strengthening of the brew adoption circulation. And what we found here was that neither natural halogens alone nor anthropogenic short-lived fluorocarbons alone do anything to ozone in terms of this trend, but combined in concert through cross reactions, they account for about a quarter of the negative trend in the tropical lower stratosphere. And we projected that into the future. You can see this here, and things get worse towards the end of the century, so that this quarter, this 25% gets larger towards the end of the century, and I won't get too much into the details here, but one of the conclusions in the paper, because of this concerted role between natural and anthropogenic, one of the conclusions in the paper is that anthropogenic short-lived fluorocarbons should be regulated if we want to recover the ozone layer in the low latitudes. I stay in the stratosphere, go to the stratospheric ozone hole, where these natural halogens also have an impact in the springtime stratospheric ozone hole. So these natural halogens, we have 0.7 ppds of iodine, 5 ppds of bromine, reduce about 10 to 20% of ozone within the ozone hole, in the lower part of the hole, in the lower stratosphere. So that's a lot of ozone for just a few ppds of halogens. And one plot I like, although it's not very beautiful, is that these natural halogens actually expand the size of the ozone hole by about 11%. This is shown here in green. Anyway, so as you see through these examples, this very reactive natural chemistry affects ozone in the global atmosphere. But how about methane? Okay, so there's two ways to oxidize methane in the atmosphere. The main one is the reaction with the hydroxyl radical. And to a lesser extent, methane is also oxidized by reaction with chlorine atom. So we add halogens to the model, then we are enhancing the loss of methane by reaction with chlorine. But as we have seen, halogens destroy ozone, which is the main precursor of OH in the troposphere. And so what we do here is that the halogens indirectly reduce ozone, and that wins. So the net effect when adding halogens to the atmosphere is an increase in the methane lifetime and in the methane's relative forcing by about 10%. So you may think 10% is a small amount, but 10% methane is equivalent to the methane emissions over the last 30 years. That's what you would be missing in your model if you don't have this chemistry in. So, okay, so we've seen that this chemistry affects the concentration of very short-lived climate forces. So let's look now into how that translates into relative balance calculations here. So this stuff has been in CSM for a number of years, and in this very recent paper, we just computed the effect on the relative balance. Here you have how halogens increase the methane and its relative effect because they increase the methane lifetime, as I showed earlier. So this induces a warming. They reduce ozone, as you can see in these two columns. The left one is the pre-industrial scenario, the right one is the present day. And in terms of aerosols, which I haven't talked much, and I'll explain now, they reduce the secondary aerosol formation, and so they reduce the aerosol cooling effect, translated here in a positive signal. That's why it is in red. So why are halogens reducing the aerosol formation in the atmosphere? The reason is in their effect, indirect effect on the hydroxyl radical concentration. Here is the percentage difference between adding halogens for the pre-industrial and the present day scenarios. You see that in the troposphere, halogens induce quite a significant reduction in the OH levels. And so, as a consequence, they reduce the OH-driven secondary aerosol formation, and having less aerosol formation means that the halogens reduce indirectly the aerosol cooling effect. Okay, so if we summarize everything into a globally integrated number, we can see here for present day the different short-lived climate forces and their effect. On the y-axis is the relative effect in watts per square meter. And you can see ozone in green here, which is the dominant effect. Methane is in orange. And then you also have here the warming effect, stratospheric water vapor. Methane oxidation in the stratosphere leads to the formation of water vapor. So if methane is increased because of the presence of halogens, then also stratospheric water vapor concentration increases. That induces a warming. The aerosols, as we saw, they also induce a warming, essentially because we reduce the aerosol cooling effect. And what you can see here in light blue is the net effect. So the negative relative effect of ozone compensates for the positive, the other terms, and that gives you a net cooling effect of 0.13 watts per square meters. So if we now compare this to the pre-industrial and the two future scenarios, RCP 6.0 and 8.5, you can see that the net effect actually is not constant. This is not a dynamic picture. This is actually variable. In particular, if we focus in the difference between the pre-industrial and the present day, you see that this cooling effect has been amplified since the beginning of the industrial era. And the reason is very simple. It's because we have more halogens now than in pre-industrial times. And why do we have more halogens now? Well, one reason is obviously the anthropogenic emissions. But interestingly enough, that's not the main reason. The main reason is that the natural emissions from the ocean have been amplified due to the increase in tropospheric ozone. So let me exemplify that for iodine. So a few years back, we looked into the levels of iodine in this ice core in Greenland, and over the last couple of hundred years, and you can see that since 1750 to about halfway last century, the levels remain fairly constant, but then since 1950 to about present, they tripled. And that was quite an interesting discovery back in the day that we explained because of the increased ozone pollution and sea ice decrease. Let me explain this very briefly. So, as Rafa mentioned earlier, ozone deposits over the ocean, oxidizes iodide, and produces H1 and I2 that phase equilibrate back to the atmosphere. That's a natural cycle that's taking place. Now, if you increase ozone due to the anthropogenic influence, that cycle gets enhanced. So more ozone gets deposited and more iodine comes out. So that's something we hypothesized in this paper in 2015. And this ice core record actually came to demonstrate that indeed the iodine levels in the atmosphere have increased quite a bit in the last few decades, and that's what we call the anthropogenically amplified natural emissions. And let me look now at this relative difference in the relative effect of the three present and two future scenarios compared to pre-industrial times. Very briefly, as we move into the future, the methane relative effect increases, quite interestingly. For ozone, it stays relatively constant, although it depends on the future projections. And then for aerosols, this is highly nonlinear across the different aerosol types, time and space. So if we put everything together in this plot of the relative effect relative to pre-industrial times, this is present day, you can see here how, again, the term that dominates the overall relative effect change is that of ozone. The light blue is the net effect. But please notice here that the shaded area means the contribution of anthropogenic emissions to this change in the relative effect with respect to pre-industrial times. And you can see here that the main signal of this change with respect to pre-industrial times corresponds to the what we call ANE, the anthropogenically amplified natural emissions. That is the thing that has driven the amplification in the cooling effect of halogens. So that's the overall conclusion from this plot, that the net halogen-driven cooling effect has been amplified since pre-industrial times due to the amplification of natural emissions. So I'm wrapping up here. Again, for the past 20 years, we've been making these measurements along with other groups. Now we know that short-lived halogens are ubiquitous in the global atmosphere. And now we have a reasonable understanding of their sources, their chemistry, and how that chemistry interacts with the abundance of short-lived climate forces and how that translates into this net cooling effect that I mentioned. So what we show here is that natural halogens exert an indirect cooling effect on climate. The variability in this net cooling effect across the different climate scenarios really reflects the complex, highly nonlinear chemical interactions between halogens and short-lived climate forces. This newly, I remarked, this newly identified cooling mechanism is actually not accounted for in current climate models, such as those used in CEMIP or IPCC assessments. And indeed, CESM is the only climate model currently with a full representation of the sources and chemistry of short-lived halogens. So this is the final slide. And again, I don't want to repeat it too much, but we have identified that natural halogen chemistry exerts an indirect cooling effect on climate through the chemical interactions that I showed. And perhaps importantly, this cooling effect has been amplified since pre-industrial times. So thank you for your attention.
Thank you very much, Alfonso. Yeah, this is great. And Eva has a question. I think the mic is right there, so you can come to the middle.
Showed the maps of changes in OH, and the conclusion was that in general you reduce OH, and that reduces methane oxidation and increases methane lifetime. But there still were areas, especially over land, that OH was increasing, and I was wondering why, because that's obviously gonna locally decrease methane lifetime, right? And that's where we emit methane.
Yeah, that's a good question, Eva. Yeah, to make things more interesting with this chemistry, what I showed is relevant for the marine and polar environment. When you are over continents, the effect of halogens is slightly different. The effect of halogens on ozone is slightly different. And that is because of the presence of chlorine nitride that forms following the uptake of N2O5 on a chloride-containing aerosol, producing ClNO2 that accumulates overnight, and then at sunrise photolysis, giving you Cl and NO2, and that NO2 produces ozone. So over continents, the presence of halogens actually lead to an increase in ozone, and with it, to an increase in OH. And that is the feature that you notice in this plot, where OH is broadly increasing over continents while it is substantially reduced over the oceans and the polar regions. I guess that was your question, right?
Ask a follow-up question.
Sure.
So, like, given the fact that the impact on ozone and methane would depend on the emission scenario, is there like the future scenario where the total combined impacts of halogen emissions is to decrease methane lifetime, so that actually they are good for the methane?
Yeah, you can see here that no matter what the climate scenario is, the presence of halogens in your model leads to an increase in the methane lifetime and its associated relative effect. It changes slightly from the past to present and into the future, but it is positive despite the climate scenario used. No worries.
Yeah, let's move on to the next talk. Thank you. This one is, the next three ones are online, I think. And the next one is by Zheng Lu. Hi, Zheng, you're here? Great.
Yeah.
And he will speak about, can biomass burning aerosol-induced surface cooling be amplified through sea surface temperature cloud feedback over the Southeast Atlantic? Okay, we see your slides. Go ahead. Thank you.
Okay. Let me change to the pointer. Yeah, thank you, Simone, for introducing the title of our presentation. The biomass burning aerosols are important for the global climate. They account for 3/4 of total global carbonaceous aerosols and 1/3 of global black carbon. As climate is getting warmer, the more extreme fires are predicted to occur in the future. So the biomass burning can serve as shortwave absorber and also cloud condensation nuclei. Therefore, they can greatly change the global relative energy budget through the aerosol radiation interaction and the aerosol cloud interaction. So the stratocumulus cloud deck over the Southeast Atlantic are constantly under the influence of biomass burning aerosols, which are emitted from the South Africa, especially in the June, July, August, and September. So the stratocumulus cloud decks can strongly reflect shortwave radiation and have small effect on longwave radiation. So therefore, it's very important to understand how the biomass burning aerosol affect the cloud properties of stratocumulus in this region. Many previous modeling studies demonstrated that the semi-direct effect of biomass burning aerosols increase the stability of low troposphere and enhance the cloud amount. Our previous study also demonstrated a possibility that aerosol indirect effect can increase the brightness of cloud deck. So no matter which effect is dominant in this region, we know that biomass burning aerosols can cause a strong cooling effect. So in these studies, the ocean's role is often not considered. We know this so-called SST low cloud feedback is often studied in the context of global warming. Here, we would like to examine this feedback in the context of cooling effect caused by biomass burning aerosols. So our initial conjecture is like this. So the cooling effect can causing colder SST, and which leads to stable boundary layers, then enhancing the stratocumulus cloud. To test whether this conjecture is correct or not, we conduct simulation. So in this study, we use NCAR CESM 2.1 with 2-degree resolution for the simulation to examine the role of SST cloud feedback. We conduct 2 groups of simulation. The first group is fully coupled component set, the B component set, and also the atmosphere component only, the F component set. So for each group, we run 2 experiments, one with biomass burning aerosol emission in Southern Africa turn on, and the one with turn off. So as shown in this table, we can see we totally have 4 cases. To eliminate the other aerosols effect, we run pre-industrial 1850 condition. So for fully coupled simulation, we run the simulation for 200 years with the last 80 years for analysis. And for atmosphere only case, we run it 12 years with the last 10 years used for analysis. So moving on to the results section. So this figure shows the time series of difference between the 2 fully coupled cases averaged over Southeast Atlantic. So in the upper panel, we have 3 cloud properties, liquid water path, cloud droplet number concentration. This is what column integrated, and also the cloud fraction. So in the lower panel are the surface temperature difference and the cloud relative effect. So the solid triangles on the axis indicate the mean difference values between the 2 fully coupled cases, and the diamond indicate the mean difference between 2 atmospheric only cases. So firstly, we can clearly see that this 20 to 30 years oscillation cycles. So we see the difference in cloud fractions fluctuate between the -2 to 2%, with the average value slightly smaller than the one in the atmospheric only cases. The column integrated cloud droplet number concentration between fully coupled case remain positive. This because the biomass burning aerosol transported from the Southern Africa, which can act as a CCN. However, the increase in fully coupled case is lower compared to that in the atmospheric only case. Also similar for the liquid water path. So to our surprise, the biomass burning induced cooling effect is actually smaller in magnitude if the SST cloud feedback is considered. For example, the difference between the 2 fully coupled cases is -3 watts per meter square, while the value is -4.8 for atmosphere only cases. So this contradicts our initial conjectures. We will explore the reasons in the following slides. And another interesting point is that we can see the changes in cloud property anti-correlate with the surface temperatures, indicating the positive feedback between the two. However, we also see that at some point the direction of this positive feedback just reverse. So we will examine why in the following slides too. So to answer this first questions, why the cooling effect become weaker in fully coupled case, we first examine the cross section of biomass burning aerosols ratios difference and cloud fraction difference between the two on-fire cases. This cross section figure is also imposed with the difference in wind vectors. We can clearly see much less biomass burning aerosols are transported over the ocean in fully coupled case. So we found this is actually due to the stronger sea breeze in fully coupled experiment as the result of much cooler SST in the fully. So in contrary, the SST is fixed in the atmospheric only case. So because much less aerosol transported to the over the stratocumulus deck, so the aerosol semi-direct effect and aerosol indirect effect will become weaker, so leading to the lower cloud amount. In the upper panel, we show the AOD difference field. The first column shows the difference between two fully coupled cases. Average over 80 years. The second column shows the difference between atmosphere only cases, average over 10 years. And the third column shows the difference of difference. So again, we can confirm that less biomass burning aerosols are transported over Southeast Atlantic, especially near the equator region and along the 20 degrees south. So we believe another reason for weaker cooling effect is actually caused by the reduced surface moisture flux. So the reduced surface moisture flux is directly caused by the cooler surface temperature over the Southeast Atlantic. So next we try to find the evidence of the sea breeze effect on biomass burning aerosol transport from the observation. So here we use 20 years of NASA MODIS AOD retrievals and ERA5 reanalysis data of surface temperature. We calculated the sea-land contrast for both variables. The time series of surface temperature is detrained to eliminate the effect of global warming trend. So the result does show that cooler sea surface temperature tends to lead less transport of biomass burning aerosols to the sea. So the correlation coefficient is 0.48, passing the 95 significant test. So next, we would like to address why the positive feedback suddenly reversed the direction. So we first determine the year of this turning point and select 2 5-year periods before and after this turning point. So we found that the reversing direction of positive feedback is actually caused by the ocean current anomalies. We plot in these two figures, we plot the difference in ocean currents between the two fully coupled cases, shown as the vector fields. The speed is denoted by this green maroon colors. And also shown in these two figures are the SST difference in blue and red colors. So we found that the cooler SST can generate a high pressure system, which triggers anticyclonic winds, as shown in this figure. So the wind anomalies are translated into the ocean current anomalies. So this anti-clockwise rotation of ocean currents brings a lot of warm water from the equator to high latitude. Therefore, in the second period, you can see the increase of the SST. So to conclude, we found that the cloud-related effect caused by the biomass burning aerosol is actually weaker if the SST low cloud feedback is considered compared to fixed SST simulation. So this is caused by stronger sea breeze due to large sea land temperature contrast, causing the less smoke transport over Southeast Atlantic. And secondly, because the less moisture supply from surface due to the colder SST. And also changes in SST can lead to changes in ocean current. Consequently, the axis heat transport from equator reverse the direction of SST cloud feedback in this region. So the result I present today has been published on JRL. And if you have any questions, and you can send me emails. With that, I would like to take any questions.
Questions? Yeah, I mean, just saying this is interesting, and I think you have used a 2-degree resolution model for this case.
Yes.
But you don't. I mean, the ocean is still, yeah. It's CSM2. Do you expect any changes if you go to higher resolutions?
Yeah, that's a good question. Yes, we expect the result might be changed. But I mean, if we use the higher resolution, the cloud relative effect will be changed. But we still expect to see a smaller cooling effect in the fully coupled case.
Yeah. Okay. Any other questions? And if not, we move on to Wei Wang. Are you here? Yeah. Okay.
Yeah, yes.
Thank you. So he will talk about the impact of horizontal resolution on aerosol modeling over East Asia using variable resolution in CESM2. We can see your slides. Thank you. Go ahead.
Okay. Hello, everyone. Today, I'm going to show some preliminary results about the impact of horizontal resolution on aerosol modeling over East Asia using variable resolution CESM2. So aerosols are important forcing agents and modify the Earth's radiative budget directly through aerosol radiation interaction and indirectly through aerosol cloud interaction. Now, this figure shows the change in effective radiative forcing from IPCC AR6, and the results show large uncertainty in the aerosol's radiative forcing, especially the aerosol cloud interaction. And this uncertainty is associated with bias in simulating aerosols properties. Now, this figure illustrates the regional normalized mean bias in aerosol optical depths compared with aeronaut station observations. And the different colors represent different models. The negative values suggest that models tend to underestimate the aerosol optical depths, especially over East Asia. Previous studies have shown that model resolution affects aerosol emission, transport, water uptake, and aerosol cloud interaction, but further affects aerosol optical depth and radiative forcing. And nowadays, using the regional mesh refinement, higher resolution global climate models have been developed. So in this study, we try to investigate the impact of horizontal resolution on aerosol modeling over East Asia using variable resolution CESM 2.2. The two experiments are conducted in the study at different resolutions. The default CESM2 models use globally quasi-uniform grays at 1 degree. And the VR grays used in VR CESM2 are shown on the right. The resolution increased from 1 degree to 1/8 degree over East area. And both models are free run for 11 years to simulate present day climate, with the first year discarded and the average of the rest analyzed. The topography is more realistic in higher resolution VR CESM2. And the red rectangle represents the eastern China with complex topographic features, such as Sichuan Basin and Taihang Mountain. Over eastern China, the intense human activities produce significant emissions of aerosols and precursor gases. So we focus on aerosol modeling over eastern China. Now, these two figures show the annual mean emission rates of black carbon over East Asia. The total emissions over China are identical in two simulations. But as the resolution increases, the model simulates more inhomogeneous spatial distributions of emission rates. And in higher resolution VR CESM, higher emission values occur over smaller scale regions, such as the scattering points over Taihang Mountains and in megacities over eastern China. The maximum centers tend to increase aerosol concentration gradients near the surface and further affect aerosol transport and distributions. So we next analyze the regional budget of black carbon over East China. The budget of black carbon is split into source and sinks, which are represented by positive and negative values respectively. The process includes emission, dry and wet deposition, and the horizontal transport of black carbon across 4 boundaries, which are included in this red box. The blue and red color represent VR CESM and CESM simulations respectively. For black carbon, the emissions are the same in two simulations. As resolution increases, the changes in dry and wet deposition are less than 3%, while the changes in horizontal transport of black carbon are more evident, with the zonal transport of black carbon decreased by about 10%. Now, this panel examines the impact of horizontal resolution on zonal transport of black carbon over Taihang Mountains. As resolution increases, the variation of terrain height is more evident, especially the mountain peak and the steeper mountain ridge. In VR CESM, the stronger descending motion along mountain ridge tend to inhibit the dissipation of black carbon. And therefore, the black carbon are mostly distributed along Taihang Mountain in the lower atmosphere. The comparison between the simulated black carbon surface concentration and the observation over China suggests that models tend to underestimate the aerosol concentrations at the surface. But as the resolution increases, this low bias is reduced, and the correlation between simulation and the observation becomes higher, which indicates that increasing resolution improves simulated aerosol concentrations. For the black carbon burden over Eastern China, compared to CESM, where CESM simulates more inhomogeneous spatial patterns of black carbon burden at finer scale. For example, the variation of black carbon burden over Taihang Mountains is more evident. In addition, the magnitude of black carbon burden also increased in real CESM, especially over Sichuan Basin, where the diffusion of black carbon is weakened. So we next evaluated the aerosol optical depth simulations. This panel, the simulated AOD values are compared against satellite environments, which are shown in this panel. The top plot illustrates the simulated AOD from VRCSM and CESM respectively. And the bottom plots show the observations over East Asia. The red rectangles represent Eastern China, and the area average AOD values are also given. So both models underestimate the AOD values over Eastern China, but high resolution VRCSM better simulates the aerosol optical depth in terms of magnitude and finer scale distribution. In VRCSM, the increased aerosol optical depth values is consistent with the increased aerosol burden. And over northwestern China, the enhanced dust emissions due to higher resolution also contributes to increased AOD values over eastern China, indicating the uncertainty in dust modeling of their CESM. The increased AOD values further affect aerosol radiation interaction. This panel shows the annual mean aerosol direct effective radiative effects at the top of the atmosphere. The result shows that the cooling effects of aerosols over China increased by about 20% as resolution increased. So the main conclusions are listed below. VRCSM2 better captures subgrade variability and local gradients of aerosol emissions. According to regional budget analysis, the deposition are affected little by resolution, but the transport out of eastern China decreased as model grid spacing is reduced. And higher resolution VRCSM2 better represents geographic features and the topography-induced aerosol transport. Over eastern China, increasing resolution improves the simulated AOD in terms of finer scales, spatial distribution, and magnitude. But where CESM2 needs to be further tuned to reduce uncertainty in simulation, such as dust emissions. So that's all. Thanks.
You, very nice talk. Are there questions?
This is Mary. I was wondering, why do you think there's no difference in, say, wet deposition between the resolutions?
I think for the wet deposition, according to the evaluation of meteorology, both models tend to overestimate the precipitation. So that's which leads to the strong wet deposition. So the changes are very little.
Yeah, and I'm embarrassed to say I don't remember what your fine resolution grid spacing is.
Yeah.
That's 14? No, that's 25 kilometers. 5 kilometers. Sorry, I'm a WRF chem person. I think in 12.5 kilometers. Thanks. Yeah, I'm just a bit surprised that that you don't see maybe like more of a convective influence changing as you change grid resolution. But it's interesting. So I look forward to seeing more later. Thanks.
Yeah, thanks.
Yeah, I had a little similar question, because you do see an increase in the black carbon burden over eastern China, and you don't see an increase in the wet removal. So there must be something happening in, both, yeah, okay. In AUD you saw that too. So could there be different effects that could lead to that you don't see a strong change in wet removal?
Yeah, I agree.
It would be interesting to see how clouds change and rainfall, as well as in connection with the burden, maybe. Yeah.
Yes. I didn't show the precipitation here. Maybe I can take a further closer look at it.
Thank you. Do we have any other questions? If not, we move to the next talk, which is by Jayun Yun. I hope I say that right.
Yeah, that's correct.
Thank you. And so we talk about sensitivity of the climate system to the magnitude of dust emissions and nonlinear responses in CSM. We can see your slides. Please go ahead.
Okay. Hello, everyone. My name is Jayong Yoon, and I'm studying at the University of Edinburgh. Today, I'm going to talk about the climate sensitivity to the magnitude of dust emissions and nonlinear responses in CSM. Dust is one of the most Dust is one of the most important aerosols on the Earth's climate system. It accounts for 1/3 of global aerosol loss, and 3/4 of dust emission come from natural sources. They can alter the Earth's radiative forcing and microphysics and cloud properties. The IPCC report reveals the dust has large uncertainties. So we aim to broaden our understanding of dust impact on climate through these three topics. For the sensitivity study, we ran CSM 1.22 using MOM3 for aerosols. For dust, dust uses two modes, which are an accumulation mode and coarse mode. This table showed the members of experiments for this study. And for increasement of dust emissions, we did not modify any factors for dust emissions. We modified the equation of total vertical mass flux of dust, which means dust emission, by 0.2 times to 10 times in each mode. Before going through the result, we are seeing the how our CSM setting presents dust. Spatial distribution of dust-related variables show asymmetric features. And when you look at the latitudinal profiles, then we can see some discrepancies at the location of peak. For the dust concentration, the second peak of dust concentration in the control experiment initially emerged around 18 degrees north. But when you increase dust emissions, then they move further north. Between dust concentration and AOD, the maximum peak appears at the different latitude. In the vertical profile of dust concentration, we can see where dust particles exist. And as you can see, most particles exist under around 6 hectopascal. Dust aerosols are known as absorbing aerosols. So in response to more dust emissions, then as you can see over the dust source regions, dust aerosols absorb incoming solar radiation and causing atmospheric warming. And the thick dust layer over this region prevent solar radiation reaching at the surface. So the surface gets cooler. Dust source regions are typically subsidence regions, and their air column is much more stable. But substantial atmospheric heating, especially in the low atmosphere, restrains atmospheric stability and generating a thermal low and anomalous ascending motion over the dust source regions. Here we plot 200 hectopascal velocity potential anomalies and a corresponding divergent wind. So this exhibits the upper level divergence and convergence cells shift to westward. When you look at the equator, then we can also find the westward shift of the worker circulation through zonal mass stream function. Conversely, climate responses to reduce dust emissions are the opposite of responses to increase the dust emissions. So we confirm that dust emission can not only change the local radiative forcing, but also affects large-scale atmospheric changing. So next, we also looked at the hydrological cycle. This can be simplified into fast and slow responses. We use the atmospheric-only simulation to compute fast precipitation responses. The fast response is caused by rapid adjustment to initial heating or cooling in the atmosphere. Here, we can see total precipitation over dust source region is dominated by fast responses, but the significance is limited regionally. When you look at the remote area, especially the ocean, the slow responses are very important for precipitation. Over the dust source region, the slow responses offset predominant fast responses. So earlier, we found that dust aerosols have a strong signature on the worker circulation, which is closely related to ENSO phases. So we looked at whether dust can modulate ENSO characteristics and diversity. We used the Nino 3.4 index following this definition. When this condition lasts over 5 months, then we count this period as one event of La Nina or El Nino. Here we can see the changes in average period of events. When dust is increased, then this average period is more prolonged than in the control experiment. But when dust is reduced, then the average period is shorter than in the control experiment. This is represented in the power spectrum and wavelet analysis. You can see in the 5 times dust experiment, they exhibit ENSO cycle at 5 years, but in the control experiment, they showed around 4 years of cycle. And then when you look at the 0.2 times dust, their cycle appears around 3 to 4 years. And also the power of signal has some difference. So you can see the power of a signal in the 5 times dust emission have a stronger power, but in the 0.2 times dust, the power is weaker. Also concentrated power during simulated period is much denser in the 5 times dust, but is less dense in the 0.2 times dust. Then we want to know why the period and power in ENSO are changed. So next we looked at the ENSO diversity using a combined linear regression EUF analysis to eliminate impact on specific regions from the study domain efficiently. The third row represents the Eastern Pacific mode, and for this one, we use Nino for index to get rid of Central Pacific impact and leaves the Eastern Pacific variabilities. For the last row, we'll present the Central Pacific mode. For this one, we use the Nino 1 plus 2 index to get rid of Eastern Pacific impact and leaves the Central Pacific variabilities. Here, the most distinct difference is shown in the Central Pacific mode in the 0.2 times dust. You can see the strong positive occurred over the Central Pacific. It suggests that reduced dust emissions can potentially induce diverse ENSO evolution to the Central Pacific. This is consistent with many other ENSO studies, which highlights that the Central Pacific ENSO has shorter period compared to classical Eastern Pacific type of ENSO. Next question is, what kind of factors or feedback can cause ENSO diversities? So, other ENSO study reveals the thermocline is much important for the Eastern Pacific type of ENSO, but when the zonal advective feedback is dominant, then the center of ENSO can appear in the Central Pacific. In my study, the thermocline didn't show distinct difference among its experiments. So we focused on this oceanic stratification and zonal advections. From in the 5 times dust experiment earlier, we already looked at there's an westward shift of the worker circulation. It means the easterly over the tropical Pacific is strengthened. This strong easterly can drag the relatively cold water from the Eastern Pacific to the Central Pacific and the Western Pacific. So the mixed layer can get cooler, but the subsurface layer can get warmer. It means the oceanic stratification can be weakened. When dust is reduced, then the worker circulation is weakened. So it causes the warmer mixed layer and then cooler subsurface. It means the oceanic stratification is intensified. When you look at the zonal advections, then you can see a zonal advection due to 5 times dust is weakened, and zonal current response also showed some weakening. But when you look at the 0.2 times dust, then as you can see, the zonal advection is slightly stronger, and Jonah current response in the mixed layer is much stronger. It means in the reduced dust experiment, the Jonah adaptive feedback is intensified. Next, we also want to know whether dust affects climate linearly. So from the global mean changes, the surface temperature and precipitation tend to respond linearly. However, when you look at other areas such as North Pole, then they showed some non-linear relationships. So we focus some reasons. So for this one, we used to normalize the standard error maps for surface temperature and precipitation, and choose 12 reasons according to large standard error or negligibly small standard error. So here is the result. As you can see, some area showed linear responses, but also some area shows the non-linear responses. Let me summarize my study. The dust source regions underwent localized substantial radiative heating or cooling in the lower atmosphere. It modulated the climatological subsidence over the regions. Consequently, it led to a shift of the water circulation and its intensity. Responses in the water circulation to dust emissions trigger changes in ENSO characteristics and diversity, especially in the reduced dust emission experiments. The Jonah advection is slightly stronger, and then stratification is also intensified. This can cause the central perspective of ENSO. Although the global mean changes showed linear relationships, it is difficult to conclude that climate responses to dust emissions are linear because, as we already showed, some regions have non-linear responses on the regional scales. Before finishing my presentation, I want to highlight that even if dust impact on climate are smaller than other anthropogenic aerosols and greenhouse gases, understanding their rules is still very important as they determine the background state on top of which anthropogenic aerosols act. Thank you.
For the nice talk. So
Hello?
my question is related to the changes in average period of ENSO. So on the table, more dust makes La Nina even longer than El Nino case. Do you know why they respond differently?
Yeah, that's interesting question. I actually didn't look at the each El Nino and La Nina phases. So at the moment, I don't have the answer, but in the future, I will look at that.
Okay, thanks. Yeah, thank you again, all the speakers, for their presentations, and then we move over to the discussion. Okay, so thank you.
Thank you.
Okay, it's the last session and people get tired, but we can see how much discussion we want and need, and it really depends on you. So we started with some questions, but of course we can extend this list of questions. In particular, one question regarding ChemChem capabilities and developments. We've seen various talks today on chemistry, very short-lived halogens, or TS2, quite complicated chemistry, requiring a lot of computer resources. Then we have, of course, the aerosols, where we span from MAM to chroma, very expensive descriptions. And then, of course, the model resolution, again, going from 2 degree up to very high resolutions. This is a wide span that we are covering in this working group, actually. And then we're coming into the vertical resolution as well, because we have our 32-level model that we go then up to 93 levels, which makes it also more expensive. And then the users, of course, everybody has their different science question, and we want to support it in some way, but we are also limited in the support. So we do need to know what the community needs and wants. At least that's my thinking of this discussion, at least a little bit. And we heard already people talk about this. And maybe, Rafa, do you want to add something?
Yes, I think my vision of what I've seen throughout the workshop is that there was much more discussion on the resolutions than on the chemistry. I mean, at least more details, more talk about that. We've seen really different results, and I mean, people using this low resolution of a few kilometers and lower resolutions of 2 degrees, and it's to keep using that type of configuration, or at least that's why they use it at the first time. So, but efforts and development compromise of what most of the users working in this community prefer or are focused and would like to keep it as a first point.
Yeah, and I mean, we do have a lot of people that develop their own model grid, as we have seen, which is great. We have the Musica tutorials, and people can work on different questions. I think we are moving to the workhorse model, and for the vertical resolution, clearly we will support the higher vertical resolution. The first question is there a need for the 32-level model and the 2-degree model for chem-chem? And I think that's what you're saying is required, and yeah, I open it up for others.
Yeah, okay. My opinion is it would be great to keep using a low resolution and low top model to basically for development of new chemistry, aerosol complexity, chemical gas phase complexity in the mechanisms. It's useful for an initial picture. And I think, I don't know, increasing the complexity of the aerosol, of the chemical schemes, I think it's not as expensive as increasing the spatial resolution and the vertical resolution. So then you can do much more things, much more tests, much more tuning using a low resolution until you get a good point. And once you are confident in that good point, then for sure we need to use the high resolution, because many of the community and all the talk yesterday about the political implications or the society needs, they also require high resolution. So we need to go into that direction for sure. But while doing the development, keeping this low resolution model helps. That's my opinion. But I would like to hear others. Doug, Alfonso?
Yeah, I agree that the 2D is really helpful if you want to run, 100-year simulations. I'm not so sure I agree the 32 level is needed. That seems like an extra model that you don't need if you've got the 58, and you just got to bite the bullet a little bit and spend a little bit more. So that's the only thing is you have a 32, you have a 58, you have a 93, and you have a 130-something level version of the model that we're maintaining. So I don't think we can keep all those resolutions and stay sane.
And the other thing that we haven't, we do go now from our old finite volume 32 level model, which was fairly cheap in regard to now going to the spectral element, which increases already computer time. And that is something we will do. The community will move over to spectral element, to MPAS, to new dynamic cores. And we're probably, I think, not going to support finite volume in newer model versions anyways. And if the model version is developed in 58, you're saying that wouldn't add too much more on the cost side. That's a good point. Alfonso, did you want to?
My comment is not about the, sorry, too tall for this. Sorry. No, my comment is about the chemistry complexity. In my opinion, adding chemistry complexity is not an option. It's a need. If you really want to represent the nonlinearity of many chemical processes that are relevant and feedback to the relative balance, you have to add complexity. So if we agree that we need to add these chemical processes in the model, you may guide us by defining what is complex for you. So what is the threshold where the chemistry becomes too complex because it's just too heavy computationally, or whatever definition you come up with? That would be good guidance. What is complexity to you guys?
And actually then, while you're saying that, we have developed, or Luisa has done an attempt to do a cheaper, 30% cheaper mechanism, and we haven't really asked for questions or comments on that. But that would not include the very short-lived halogens, for example, that you were showing. So that would be a step back in that sense.
Sorry,
right?
the halogen scheme in the model, it's already a simplified version of the chemistry. So it does not represent all the complexity the chemistry has. So as complex as it looks, it's already a simplified version. Just that.
What? Yeah, okay. So, yeah, good. Any other thoughts? I know, Mary? Good.
I just want to bring it slightly different, but still on simplicity. You don't mention the single column model, and are people interested in this community of making use of the single column model to do testing or simple, idealized simulations with complex chemistry?
And was that the box model, right, in that sense too?
Yeah, I mean, SCAM is available. It does run with chemistry. And, I think there are applications, and it might, even starting points with especially boundary layer type chemistry might be that might be a really good spot. And I just was curious if there's a desire for that among this community.
I mean, we have not seen any presentations on this, and maybe people are not even aware of it, and maybe people don't know how to do it, how to use it, and what. So this is something we should do. We should present in next working group meetings about the single column model, that people are aware of it and what it can do. Because, this is a chemistry climate. You can think of radiation, right? You can think about many things you could test in a simple model version, in a single column version. Yeah. Photolysis and other things. Yep. I guess one other question I think I want to bring up here, and that's really something to think about. ChemChem, the 80-kilometer model top, is used for climate simulation and is used for many aerosol application and stratospheric application. Alfonso and Rafa is using it, but now the other model version, of course, is WEChem, our 150-kilometer model, and there are still many unresolved questions. How much science we are losing in an 80-kilometer model with a high model top, and how much, for instance, 80-kilometer may be suited for things like geoengineering studies that we heard about a lot in the WEChem model. So there's a lot of research in that area as well in the model top that we now extended, though, from 40-kilometer to 80-kilometer. So that is something to keep in mind that gives us an advantage already from earlier configurations. Hopefully.
completely agree with that. Yeah.
But
that these 80 kilometers for sure will give you more details than the low top that we've been used to use. But I mean, certainly I think there is a lot of room, a lot of space to compare if which of all of these processes that are being studied require of really running Wacom with the really high top and not this top model at 80 kilometers.
But also the 80 kilometer versus the 40 kilometer model that we are developing both. Yeah. Okay. Any more thoughts? I know we are getting to the end of the meeting, and if people don't have more thoughts, we'll end the discussion early, unless Doug has more.
In Rafa's talk, how resolution affects the processes in the model. In other talks too, I guess. So if we do, let's say a VSL halogen at 2 degrees and 1 degree, and we tune the model for that, we have to make sure that people that run the high resolution, regionally refined model realize that sensitivity, because they're going to go off and run that, and everything's going to change. The amount of halogens that get into the stratosphere or whatever they're doing. So we have to somehow get that message out and make sure people don't use the model in the wrong way, thinking they're just, reconfiguring the chemistry to run at a different resolution, because resolution matters, it seems.
Yeah. Yeah, so the scalability of all of these different things. I mean, we have seen these nice examples, how resolution impacts chemistry in certain regions, and aerosols and transport. And it will certainly impact the sea salt. So if you do put a regional refinement over an area where sea salt emission really matter, then you will get a very different halogen loading in the troposphere. So yeah, that's really something that has to be looked into in other studies, and yeah, if it's used for climate studies and other effects.
Yes, I think we all expect that when running into these ultra high resolutions configurations, for sure you will have a larger variability in the same grid. I mean, because you are dividing this white green. That was a nice nice figure that you show with all the ppb's values for ozone, and this 1 degree times 1 degree, and then the lower resolution. But it's not only the spatial resolution related to the emissions or with transport, but it's also many of these reactions are nonlinear, and the efficiency of the chemistry is changing also at the same time. And I think that's where it will require for users, because each one will use each configuration for different purposes, to really check that many of these developments have been thought mostly for the low resolutions configuration. Whenever you go into these high resolutions, first things will be to double check results are comparable, at least on a first point. And mostly, I really like that when you go and compare into the higher levels, because most of these high resolutions is really important for the surface. But then if you go to the higher levels and you get to see a really improvement at the surface, but then that things behave more or less the same at 3 kilometers or 4 kilometers, then that's a good point to be sure that the overall representations could still be used.
Right, and that motivates the next evolution of our dynamics to have a variable vertical resolution with regional refinement, that you have a very high boundary resolution and then go to broader resolution. If somebody could develop that, that may be useful. Francis is shaking his head. Yeah, but I mean, that's really the point. Where does it matter and how much? Because if we do, and I think that would be a useful exercise to go to actually global high resolution. We heard about the ultra high resolution, but just going to quarter degree for a chemistry run and seeing how much that changes. I mean, you said it may not change too much, but to look at it globally could be another very interesting step to see how much does resolution matter globally. And we do have the nice satellite data now becoming available that we can do a lot of evaluations as well.
Can I make a comment on that?
Yes.
Because you make it sound really simple, and one person doing it looks at just a few things.
Yeah.
It would be really, really great to have the community look at different things in the model to pick out if there's something that we didn't see at first. It's really easy to look at something that's like CEO that's just transported and you don't really expect too many changes, but what if it's something that much more sensitive? And yeah, just a thought, someone look at wet deposition, someone look at the chemistry, et cetera.
That's a really good point. What we didn't talk about in this today, but we did in earlier sessions, was our evaluation data, evaluation tools that we had before. And we are also developing with Melodies, and Rebecca is also part of leading that, is enhancing our evaluation tools. Two things that we have to look at when we run standard simulations. We're talking about that for WebCam or the mid-top model, for the high-top model. We need it for the low-top model, that once you run your new simulation, you don't have a hard time looking at general diagnostics as well, that we can all feed into this. And yeah, we did have a tutorial in our Chem meetings that we have weekly, and everybody is welcome to join those as well. We had recently a tutorial on the new atmospheric diagnostic set that is more a climatological comparison. How can we run it? How can we actually feed in more diagnostics that everybody then can run and look at? And I think that's maybe really important while we go to all of these new scales, and that's right, to make it easier for people to see if they screw something up somewhere else when they do their development in one region. Yeah, that's a good point. We didn't have in this working group meeting. Eva, you have a point?
Yes, about your point to going to like global high resolution. So isn't the problem that it's not just increasing the resolution on the model, but you need to increase the resolution of the emission sets. And if you don't get a good grasp on the regional high resolution of the emission stats, it's more like a junk in, junk out. No?
Yeah, so the emissions you mean, right, that we're running?
Emissions, yeah. Well, what you put into the model, right? If you want to go into very high resolution, you have a good high resolution in the emissions sets. And currently they're probably like 1 degree.
Yeah, no, the emissions are much higher, right? We have 0.1 degree, I think, is the standard. And so we are actually already using quite a high emission data set and combine it for the low resolution simulations we are doing. So yeah, and there are, one point was the diurnal cycle. That's more the time resolution is low. We often have only monthly emission data sets, which is maybe okay for some things, but if you really want to look at the chemistry, in some parts you do need potentially the diurnal cycle to capture these things. Yeah, but it's of course also the meteorology. If you do nudged simulations, and that was an example that we saw today too, if you go to higher resolution than your meteorology, is it better to nudge outside your refined regions or other things? So yeah. Yeah, we are almost at the end, Gokhan. Coming in. Yeah, I thought you wanted to contribute to chemistry discussion. Okay, yeah, I think this is really good points, and yeah, well, hope we have we will have our next meeting again in winter, and that's more towards January, February, and at those meetings we went more into the technical details, into melodies and other things. So yeah, please join our weekly meetings if you're interested in, and thanks for the great discussion. I think we'll conclude with this. Okay.
Thank you very much to everyone.
5:15. So, yeah. Everybody, yeah. Yep. If people start sitting down, so we'll have the South Bay and Center Bay open, and we are supposed to have a discussion. The meeting is not over yet. Yes. Well, there's no beer tonight, unfortunately. Don't go there, otherwise they can't. So the workshop is not over. This is the now real work part. We are going to assign work. So the people who are outside, if they are interested in joining this closing session, please. Marika, you can't stand there.
Mic check.
So let's just get started and hopefully, well, I shouldn't jinx it. The idea here.
Mic check.
Oh, they just got out? Okay.
Mic check. 1,
We'll
2.
just wait a few minutes then.
They're
coming in.
Mic check. Mic check. I'm just hearing it from center.
Okay, can you just make
Okay, but we need about 5 minutes.
Yeah,
We'll be good
a
in
few
5
minutes, that's fine.
Check, check.
Next year, we should have probably beer last day too, just beer, so that more people will stay around probably.
Check, check.
Or yeah, most valuable co-chair award or something like that, yeah. Yeah, door prizes or something. So we can get started, I guess, quickly. Okay, yeah, so I have the okay, so we have the Zoom link already. So good afternoon or good evening, everybody. And I just wanted to sort of wrap up the meeting. It just feels like still Saturday, Monday morning, right? We're just starting again, so I'll just present my state of the CSM address. But anyway, so before I forget, I just wanted to thank a few people. And this meeting would not be possible with the last minute scrambling of the CGD admin group in particular. So I would like to thank Elizabeth, Daniel, Bonnie, Kyla, Lori, Teresa, Kaylin, Lara, Ryan, and Shelby. The last two folks are not part of the admin team, but they're in this UCAR, I guess, or NCAR admin team. I wanted to also, I wanted to also thank all the multimedia services folks. They have been in the back, and they are trying to run the meeting as smoothly as possible. So thank you, guys. And then the event services. So this is a bit challenging because the kitchen here is not operational yet. So they had to cater the food from the Foothills Lab to here. So they have been really great providing us lunch, breakfast, and all the breaks and all the beer. So thank you for those people as well. So with that, I think that was sort of, hopefully I didn't forget anybody. And I wanted to thank all the working group co-chairs as well for running the meeting smoothly, and also our task team, whatever the internal chair here, or Monica also for sort of organizing all of the other cross-working group leaders as well. So with that, I will stop. And then if you have, so open mic in a sense, if you have any questions, comments, suggestions, or anything else, so please come over here to, there are 2 microphones. And if there are any people online with comments, questions, suggestions, please do so. So I just wanted to sort of, since this is a community event, I know that many other sort of discussions happened in the working group sessions, but if you want to raise any other issues or concerns, any questions, this is your chance. Well, this is another chance. This is not the only chance necessarily. So if not, we can all go home. So that's also fine early. Okay, go ahead, Marika.
I just wanted to add to the thanks that we should thank Gökhan, who's served as chief scientist for 5.5 years, a long time, and done an amazing job. And he's stepping down soon. So thank you.
Thank you very much. Thank you. And in that sort of spirit, I wanted to thank all the working group co-chairs over the last 5.5 years, SSC members, CAB members. We had good days, we had bad days, but I think we made quite significant progress in my view. So for those of you who are also SSC members and CAB members and the working group co-chairs, we'll be meeting in this room tomorrow at 8:30 for the joint meeting till 12. And then you guys have the agenda. And for those of you who are presenting, I already sent the folder, so please put your presentations there. I'm talking to myself mostly. And then we'll have a SSC meeting in the afternoon tomorrow for 2 hours to wrap up the meeting, sort of go over stuff. And then the CSM chief scientist position is open. The advertisement came out, I think, on Tuesday, if I'm not mistaken. So it'll stay open for 2 weeks, till 27th of June, until 5 p.m. probably. So it's internal, I believe, to CGD. So if anybody's interested in applying, please do so. The job comes with fame and fortune. and lack of hair. Okay, so if there are no questions, comments, or anything else. Nothing? Everybody wants to go home, I guess. Okay. Going once? Do you want to say anything, John? I'll put you on the spot as the incoming CGD director. You can use the microphone there, yeah. Or you can come here if you like. Okay.
It's been really good meeting everyone. I have seen very, very few talks this week. So I've got a bit of a sense of what's going on, and I've got a bit of a sense from talking to people, but I've still got lots to learn. So I'm really looking forward to starting and working with the new chief scientists when they come along, and working out how we keep delivering the capabilities, the modelling capabilities to the community, which is a really key aspect of this work, obviously, and the running. So without having prepared, that's my thing. So just thanks for everyone that's come up and said hello and told me how much I should be worried. But I'm really looking forward to getting going, and so I'll see everyone around in different capacity when I join NCAR in September.
Great, thank you, John. Okay, well, Bonnie, I already thanked everybody. So anyway, she's one of the admins behind the scenes here. So thank you, Bonnie, for all you have done. Okay, well, if no other questions or comments, we'll just wrap up and call it a day. And end of the 28th, right? CSM annual workshop. And we'll see you next year. Thank you for coming, and thank you for your participation in CESM. Thank you. That was short.